Good morning, ladies and gentlemen. Welcome to our fifth conference on cosmology on small scales. My name is Michal Krizek and I am from this Institute of Mathematics in the Czech Academy of Sciences in Prague. There are several sponsors, our institute, of course, then Faculty of Mathematics and Physics. I'm very happy that Pavel Kroupa is here because he helped me to organize the scientific program. He's professor in Charles University as well as in Bonn, and also cosmological section of Czech Astronomical Society. I would like to dedicate this conference to Tuomo Suntola, who is here. He visited our conference also 2 years ago. He was born in 1943, but last time we didn't organize this conference, yes. And he is inventor and technology leader, author of the monograph Dynamic Universe. I would like to circulate it here. Please look at it. He is published in Physics Foundation Society, and he is best known for his pioneering research in material science. And we publish proceedings before conference. Usually proceedings are published after conference, but we publish it in before conference. You can find it in our webpage. And I dedicated these proceedings also to him. We started with Yurii V to organize this series of conferences because we found that there are many indications that the solar system slightly expands, yes? And for instance, the famous faint young sun paradox can be explained by that. There is paradox of large orbital angular momentum of Moon or Triton or Charon. This can be also explained by that. The formation of Uranus and Neptune, they will probably form closer to the Sun, and due to some, say, anti-gravity forces, they are now very far from our Sun. You can explain the existence of rivers on Mars and the existence of satellite Phobos by these tiny, small forces. You can explain by that the tidal catastrophe of the Moon. In fact, Yurii published a paper Yurii V published a paper in 2003 about that. I independently published a similar result 6 years later, and then we decided to organize conferences on this topic. You can explain the paradox of large recession speed of Titan from Saturn, because nowadays we know that Saturn is receding from, Titan is receding from Saturn 11 centimeters per year, but before that, say, geophysicists assume that it is only 1 millimeter per year, yes? You can explain rotation, slow rotation of Mercury in absence of its moons, long existence of rapidly moving satellites below the stationary orbit of Uranus and Neptune, and also long existence of life on Earth, because Sun, our Sun 4 gigayears ago had only 70 or 75% of its today's luminosity. So I'm organizing this conference together with Yurii V, who unfortunately could not come, that's him. Also Hanna Bilková, who prepares coffee, help us with that. And the current standard cosmological model has many problems. They are listed here, so we usually concentrate on the problem of existence of dark energy, or how is it possible that there is very large momentum of spiral galaxies, because at the beginning the universe was homogeneous and isotropic with some small fluctuations, but nowadays galaxies rotate very fast, roughly speaking 200 kilometers per second, yes, which is extremely large energy. And we publish proceedings every 2 years, so these are the previous volumes. You can get them in the lobby. There are some organizational issues. Of course, there are several last-minute changes in the program. Its latest version is in the lobby. We ask chairman of all sessions to keep time. If you can show this, but this is the position of chairman, yes. Time is over. The last day of the conference on Saturday, there will be a walk through astronomical and cosmological landmarks of Prague for all participants. There are many restaurants in the neighborhood of our institute where you can take your dinners and lunches. And moreover, what is very important, all say lectures will be recorded, but if someone does not want that his lecture is recorded, then please tell to me, organizing committee, or directly to Avril Styrman from Finland, that you don't want that your lecture is recorded. So on Saturday we shall go through the old town, and there are many famous scientists, Bolzano, Bernard Bolzano, this is Giordano Bruno, Albert Einstein, Johannes Kepler was here, Christian Doppler, this is statue of Atlas, there was Tycho Brahe, there is statue of Kepler and Brahe in front of Kepler Gymnasium. There is again a plaque of Christian Doppler, which is here in the Charles Platz. And finally, I would like to congratulate to Tuomo for his birthday, and I have a very small present for you, Tuomo, because I know that you are interested in history of say science, yes. So there are some pictures about physics in Prague. Yes.
Thank you so much.
So that's all. Thank you very much.
Xavier is here.
Xavier here.
So the next speaker, the next speaker is Xavier Hernandez from Mexico, and he suggested in 2012 he made a test of gravitation using very wide binary stars. And since that time, quite a substantial project has been written on this topic using the Gaia data, and Xavier will tell us the most recent results as well as the pitfalls in this on this topic. So Xavier, you can begin once you focus on.
So first of all, I would like to thank the organizers for this very interesting meeting. This is the second time I do, and they've always been quite interesting. Okay, so generally we hear about the missing mass problems, generally postulate or presented as a problem that there is less mass in astronomical systems than we see. Strictly speaking, it is a gravitational anomaly. What we see is that the systems, if we assume that we know how gravity is working, then they must have more mass than we see. But we cannot be certain that they have more mass than we see, because all this is occurring at a scale where we really have no direct evidence as to how exactly gravity works. Okay, So, for example, the rotation curves of galaxies, as we all know, there is a substantial gravitational anomaly. They're rotating much faster than the Newtonian or Einsteinian prediction, given the mass we observe. The same happens with collections of galaxies. If one postulates that to explain the first observation we need huge halos of dark matter around galaxies, then it is reasonable to expect that if you put many galaxies together, there will be the same overall sort of mass fraction anomaly, and indeed that happens. And of course, at cosmological scales, we cannot make sense of the structure formation scenario if we don't have this same large fraction of dark matter. However, we cannot be certain a priori if we are looking at failure of standard gravity or at a proof of the existence of dark matter. It could be either. And of course, we all know, even in spite of the periodic announcements to the discovery of dark matter, they always go away. We never hear of the when it's not news when the big prediction is proven to be wrong. But every 6 months or so we hear that dark matter has been discovered. It obviously hasn't happened yet, and the problem here is quite serious. Okay, I mean, as you all know, it's not that we are missing half of the dark matter we need or 90% of the dark matter we need. We haven't ever seen a single particle. Okay, so within this dark matter scheme, we have to accept that the driving causal entity for the structure of the universe is something no one has ever seen a single particle of. Okay, that is unsatisfactory for many of us. And of course, direct proof of exactly how gravity works is really millions of many orders of magnitude, stops many orders of magnitude below the place where any of these anomalies appear. So we really don't know for sure how gravity works at those scales. We haven't done experiments at those scales. Well, the Leaning Tower of Pisa is not 1 kiloparsec long. Okay, and even within the solar system, we're still, and even binary stars that are more or less where you can trace the orbits, they end at a ridiculous fraction of the scale where we need to assume what gravity is doing at this stage. So what is the current scenario? Well, the current standard scenario will tell us that the universe is made up of about 5% of atoms, and then we have 27% of dark matter and 70-something% of dark energy. Now, given the fact that this dark matter has not appeared, not even a single particle, and given the fact that this gravitational anomalies appear at scales where we don't really know we cannot be certain of how gravity works, to a number of us, this whole scheme is beginning to appear a little mythological. And I'll tell you why. All the reasons are the ones that I already mentioned. And what is this? Suppose you make a plot of this is the ratio between the observed velocity of a galaxy and the velocity which Newton would predict as a function of distance, how far away you are from the center of this galaxy. Okay? It is a square of a quantity, and hence in a standard scenario under standard gravity, this is a fraction of dark matter. Okay? The missing amount of matter. If this is 1, if you are at 1, and the line here at 1, then it means you do not need any dark matter. The observed rotation velocity coincides with the predicted rotation velocity. And essentially, you see they are sequences of points. You can trace the sequences which are going up. And those are the rotational curves of several galaxies. Okay? As you go further out, you start requiring more dark matter. In the very center, you don't require any dark matter, but as you go out, these points start rising. And if you ask people doing galaxy simulations in standard scenarios, they'll say, yes, of course, it's a mess. No, you don't see anything other than a scatter of points. Because the fraction of dark matter at a given radius for a given galaxy is a very complicated, is a result of many complicated processes. Well, you have the angular momentum, you have the accretion of matter, you have the redistribution of matter through all sorts of hydrodynamical processes. So of course it's complicated. There is nothing behind this because deciding how much dark matter we have within the radius is the result of the concatenation of many independent processes, many of which have stochastic components, so that would be good. However, if you grab exactly the same data and you change the radial scale, or the x-axis, from radius to acceleration, all the points collapse into a single curve. Okay, this to me is absolutely surprising. I mean, this really is telling you that it is impossible to grab many independent processes having stochastic components, and then somehow ask for the noise to cancel out. Noise doesn't cancel out; noise adds. Okay, from very fundamental thermodynamic principles, this is really telling you that what's going on is not that you have this complicated physics of accretion and dark matters and so on, but that gravity is changing. And the scale at which you require that change to appear is extremely low. Okay, here we are at the one line, so here you don't need any dark matter and or to modify gravity. You need to modify gravity in an acceleration scale below 10 to the minus 10 meters per second squared. So that is orders of magnitude below anything we've ever tested directly, okay, in the solar system or anywhere else. Right. This is an updated version of that same plot. This is work by Federico Relli and Schobert and Stacy McGow. And well, this is already a little old, but anyways, essentially what you're seeing is that at high acceleration, this is now acceleration against acceleration, the acceleration Newton will predict against acceleration we actually measure, and in the high acceleration regime, both coincide. In the low acceleration, we see a deviation, a small deviation, well, not so small, you see a certain deviation, and what's critical is that the spread of the points is consistent only with observational errors. Now, I know we have people of different backgrounds in the room, but in astronomy, you never see a line where the dispersion is consistent with observational errors alone, unless you're looking at a single physical process behind it. You have lots of correlations. For example, the mass sigma correlation between the mass of a black hole and the velocity dispersion of a halo or the bulge of a galaxy or a spiral elliptical galaxy and so on. And yes, there is a correlation, but there is there's always a very substantial spread that is the result of many different processes being involved in a particular correlation. The only times you see tight correlations with spreads that are consistent only with observational noise is when you're looking at a single physical process acting. If you plot the width of a line in a star against the temperature of the star, you get something like this. Okay, so this is very telling us, I think, that what we're seeing is a deviation from standard gravity in the low acceleration regime. However, well, this is a further update, an extremely interesting update, because now it's been updated with data from weak lensing. Okay, so what's out here? Well, here you have a sort of overlap between weak lensing data and kinematic data. They actually match up very nicely, and basically this phenomenology has just very recently been extended by about an order of magnitude further away. Okay. So what I used to find very well, let me first look at this and show you very quickly. Now, of course, I don't know what Newton would have done, but I know what he did. Okay, how did he construct his force law? Well, he grabbed the assumed that he was looking at circular equilibrium orbits, and he used Newton's second law, and he took a critical empirical fact, and that critical empirical fact in his time was called Kepler's laws, and now we would call it the rotation curve of the solar system. Okay, how do planets rotate? Well, this is an empirical fact. We don't know why, that's what nature is showing us. So how do you get the force law? Well, you square the velocity and you divide by the radius. Okay, get rid of the square root here, and then you add another radius down there, and there's your force law. Okay, so that's the force law that you need under a Newtonian scheme to explain the observations. Okay, what if I do the same for galaxies, for this anomalous region? I'll do exactly the same and see what comes out. Well, the empirical data is now this. The rotation curves are flat, There's no radial coordinate here. And there's an overall scaling between the mass to the 1/4 power and velocity. That's called the time-efficient relation. It's an observational fact. Okay? Just like this is an observational fact for the solar system or any other solar system now, external ones. For galaxies, we observe this. Okay? If we want to leave the gravitation with Newton's constant explicit, we have to add a constant with units of acceleration. Okay, let's do the same thing. Okay, let's just square this and divide by the radius. Well, that's the force I need to assume. Since a constant with units of acceleration has appeared, I can now write down dimensionless forces per unit mass by dividing these two expressions by the same notes. And this happens for the Newtonian case, and this happens for the modified case. What an extraordinary coincidence that one is exactly and precisely the square root of the other. Okay, this is what sort of blows my mind. So this cannot be a coincidence. How is it possible that if I just repeat Newton's experiment to infer the force that is explaining the rotation of galaxies, I get exactly and precisely the square root of the one I need for a solar system? This to me suggests that, well, maybe gravity is a complicated affair, and depending on which scale I'm looking at, I get one particular term dominating or another term dominating, depending if I start changing the scale at which I'm doing my observations. Okay? So let's try and test the generality of this approach. If rotation curves of galaxies are the result of complicated baryon physics and dark matter halos and so on, well then, the phenomenology we observe there is the result of all these complicated processes. However, if on the other hand it is the result of a change in gravity with acceleration scale, we should see the same change in gravity with acceleration scale at completely different systems that have nothing to do with galaxies. Okay, so let's look for a system that is in the low acceleration regime and has nothing to do with galaxies. Okay, let's see if we can find very low acceleration systems and then see if they could reproduce this dark matter anomaly or do something else. In particular, if we look at wide-banding stars, we have two solar mass stars which are separated a few thousand astronomical units. They will be in the low acceleration regime. So let's look at these things and see what they're doing. Okay, in principle, it's a straightforward test. Will they be showing Newton's expectation? So will they be showing something different? So as Pavel was suggesting, was commenting, this was an idea I proposed a bit over 10 years ago. And of course, the details of the test are important, and the details sometimes get a little messy. For example, first we need to know what exactly the Newtonian prediction will be. Okay, there will be projection effects, because the orientation of this orbits on the plane of the sky will be random. Then there will be a distribution of ellipticities. We don't know exactly what the ellipticity of the systems is. There will be a range of ellipticities. They're all mixed up. Okay, and then there are evolving in the in presence of other stars, and they're subject to the tidal forces of the disk and so on. So we have to take care of all these things. And then, of course, there might be kinematic contaminants, because some of these stars will not be single stars. There's a hierarchical multiplicity of stars in stellar systems. Sometimes one of these stars will actually be two stars, and all this will complicate matters. So how will we go about it? And of course, we cannot actually trace the orbits of these things, because the orbital periods are in thousands of years. So we haven't got time. We can't wait to actually see all this. All this is there together. However, all this, or most of this, has been calculated and can be calculated. Okay, you can simulate these things. One of the first important simulations in this sense was by Yannick Tremaine, very conveniently in the year before I started with all this. And basically what they did was to grab a population of 50,000 binaries, okay, and evolve them in a Newtonian simulation in the neighborhood, in the solar neighborhood, subject to tidal forces and this and that, and then project them and then take a sort of distribution of ellipticities and all of this. And this is essentially what I get. Each point is an observed binary along a particular line of sight, so now we have a one-dimensional velocity as a function of separation. So I think separation here is in the vertical axis, and this is velocity in some units. And basically, this envelope here is Kepler's law. As this separation gets smaller, the velocity gets higher. And then there is a critical point beyond which velocities, well, everything is very messy and velocities start increasing again. This is obviously the point where the tidal field of the Milky Way breaks with binary. Okay, so those are no longer bound systems. The ones up here are no longer bound. They're too separated. They're no longer bound. And in Newtonian physics, this happens at a very clear position for one solar masses of 1.7 parsecs. If the masses are a little smaller, then this happens at slightly smaller velocities. But we have a clear prediction as to where this should happen. Okay, so that's a clear prediction as to interior to what distance you want to be working. You don't want to be looking at things which are unbound. Okay, so that initially tells you that this is essentially a limit, an outer limit out to which this kind of test makes any sense. Okay, and basically then if they grab those simulations and calculate the RMS value in one dimension for relative velocity between two components, so we have all these binaries, tens of thousands of binaries, and we project them on the plane of the sky, and we ask for this statistical quantity for the distribution of relative velocities between the 2 points. And this is what you get. This is, of course, one where R to the minus half. Comparing scaling, this is the tidal radius of the program. These are unbound systems. Okay? So this is what we have to compare our observations against. Okay, in any modified gravity scheme, you have the same things. So you have to account for all the same things. You have projection effects, you have some sort of effective ellipticity or initial conditions for the problem, so on. So, and you might have contaminants, etc., etc. So you have to take all this into account. But at least, I mean, in the Newtonian case, there's a clear prediction as to what you should see. And we can see that it's very fundamental. When I say modified gravity, well, there are a range of options, and often it is not easy to calculate exactly what the prediction will be, because these tend to be complicated theories. But at least for standard theories of MOND, there is a clear prediction. This is one of the most studied alternative theories of gravity. And here, this is an acceleration mediated theory. So basically, we have to worry about the fact that these two binaries are not in isolation, but are subject to the acceleration of the Milky Way, and hence you are not in sort of what we call a MOND regime. But things are modified in a very particular way. And there is a definite prediction. This is essentially comes from the work of Multimillion in the 80s. And the definite prediction is that things look pseudo-Newtonian or pseudo-Keplerian. You should still see Keplerian orbits, but the effect of gravity or the effective value of G should be boosted by around 40%. So in some particular modified gravity scheme, there is a definite prediction as to what you should see. Can we infer this from the data or not? That's the question. So the first time I tried it back in 2011, we had very low quality data. I was using the best data available at the time, but it was unfortunately not sufficient. This red line is the Keplerian expectation, and as you see, the upper envelope looks rather flat. And crucially, there doesn't appear to be any clear signal at around 1.7 parsecs. But the errors were huge, no? So it wasn't very clear. We kind of suggest that this points were a bit further up than the line, but the error lines were huge. And that was the situation for about 10 years until the new Gaia catalog came along. And the new Gaia catalog is something really fantastic. It's a satellite that looks at stars in the Milky Way, mostly stars in the Milky Way, with very high precision, mostly measuring distances through parallax and proper motions through changes in the position. Okay, generally in astronomy we measure velocities through Doppler effect along the line of sight, but here we're finally looking at velocities on the plane of the sky. Okay, in order to detect that the star is moving on this thing, can we put there? Fine. In order to decide what the velocity on the plane of the sky is, you have to be very careful. You have to have an extremely high precision as to exactly where your satellite is pointing, so that you can see changes in the angle or in direction very accurately. And I say this is fantastic, fantastic in the sense of fantasy, really, because the analogy the guy people make as to the precision with which they know exactly what direction they are pointing is equivalent that if there's someone standing on the moon, they can guarantee that with a laser they could hit that person. Not that person, they could hit the bottom of his shirt. Okay? So that's what I mean by fantastic. So the precision of these observations are really out of this world. Anyways, so we have to start selecting, and here it's that sort of a data mining really kind of problem, because the catalog has 1,000 million stars, and obviously we have to very carefully select the ones we want. Now, we take a sample of extremely nearby stars, just 120 parsecs, really just solar neighborhood. People are using Gaia out to 5 kiloparsecs or so on. This is a mere fraction of that. Obviously, this allows for very high precision in the parallax of the stars and so on. So this essentially defines what a binary candidate comes from. I want two stars whose difference in position along the line of sight is within the errors of the difference of position on the plane of the sky. And this gives me about 7 million stars. However, this is a mixed bunch of things. And first, you want to make sure that these binaries are isolated. So the first thing you do is get rid of any stars, any binary candidates, which have members which are members of more than one binary system. Okay, you get rid of all those. And that leaves you with about 97,000 or so. Then you want only systems where we have the radial velocity. I'm not going to use the radial velocity to infer relative velocities, because the errors on radial velocity are much larger than the errors on the position on the velocity of the plane of the sky. But I'm going to use the relative velocity on the line of sight as a filter to get rid of unbound stars, projection effects and so on. So the population of stars in the Milky Way has a sort of velocity, Gaussian velocity dispersion with about a dispersion of around 40 or so kilometers per second. 40, okay? So the two-point correlation function is also a Gaussian convolution of two Gaussians, and it has a dispersion of around 60 kilometers per second. So if I have a pair of stars whose radial velocity differs by less than 4 kilometers, it's extremely unlikely that they are unbound or that they are flybys, so projection effects. So having the right radial velocity allows me to cut the sample significantly. And then this rule, I think, is an internal Gaia filter that tells you how good the solution is. Basically, the smaller the value, the better the solution is. So this means the solution is very good. We want the solution to be very good because this means that the chances that each of these binaries is in fact a binary itself, each of the components of a binary might be two stars rather than one, becomes extremely small when the single star solution is of high quality. Okay? Signal to noise, etc. So that allows me to sort of clear the sample. Of course, for example, then I also look at the HR diagram of the stars I'm looking at, and I want both stars to be main sequence stars. And here I can spot things like photometric binaries, which will be from a sequence somewhat displaced above the main sequence line. So I made all these cuts. There's been independent studies, for example, this Vyacheslav I, which have studied, given the Gaia data, in what regions of the HR diagram is it more likely that each of your points is actually a binary itself or not? No? And of course, get rid of the brighter stuff all the way up here, because if you have a very bright star, it is easy to miss a dim star nearby. So if both are main sequence stars rather than giants or anything, it is very easy to spot the presence of any contaminant. I'm going to skip this. This is just how do we determine the masses of these things with Gaia and with stellar isotopes and etc. etc. It is now we know the masses of these things down to about 5% accuracy. So we have a very good estimate of what the masses of these things are. And this is one of the first results I got with this new Gaia belief. And now, for the first time, we were able to actually trace the Doppler decline in the high acceleration region. This is about 10 to the minus 2 parsecs, 10 to the minus 1 parsec over here, right? So the type binaries, which everyone expects to be Newtonian, indeed are Newtonian. Okay, this is the RMS that Yang is the main of calculating. This is just the mean. Over here is just the mean, and you can see beautifully how you trace the Newtonian expectation, which obviously is a test. It's a consistency test for the whole procedure. So I'm starting with Gaia data, positions and right ascension and declination and upward motions, and then I have to sort of process all the data significantly, estimate the mass, estimate the separation of it, etc., etc. And the fact that I verify very accurate Newtonian prediction in the high acceleration region validates the whole scheme, and shows me also that I don't have any hidden tertiaries. Hidden tertiaries is a term I used to refer to the cases where one of the stars in my binary is actually a binary itself. I describe how I clean for that kind of thing. However, in the low acceleration, high separation, low acceleration regime, a very clear gravitational anomaly appears. Now, the nice thing about these stars is that we cannot blame dark matter for this. Okay, and the reason is very simple. If we have a dark matter scenario, we know how much matter we need in the halo to explain the rotation of the stars around the galaxy. But also, from looking at the vertical oscillations of stars in the disk, we know how much matter you have in the disk. That's why you need a halo, because essentially the velocity dispersion of stars vertical to the plane of the disk in the galaxy is inconsistent with there being much dark matter local. There is a limit. If you had, if you don't just say the disk is heavier. Okay, the disk is heavier, but the dark matter is not there locally. It's distributed in a big halo that does not mess up the kinematics, the vertical kinematics for stars in the disk. The actual limit is of around. It's not there. It's not there. Anyways, we know that there cannot be more than 10 to the minus 2 solar masses per cubic parsec in the disk. Otherwise, you mess up the vertical dynamics of the disk. Okay. 10 to the minus 2 solar masses per cubic parsec. So if I'm at distances that are below a tenth of a parsec, cubed, well, that's 10 to the minus 3. And 10 to the minus 2 is the limit, so it's 10 to the minus 5. So the amount of matter that you can have within the orbit of the binary is 5 or 6 orders of magnitude below what you have in the in the stars themselves. So to go beyond those crude diagnostic plots, you have to look at the full distribution of velocity and see what we're looking. And that basically means solving this problem, which is also why I spent a year doing 18th century astronomy. So you have a plane of an ellipse in the plane of the binary. You have to project it on the plane of the sky and look at all these things. Basically, the first thing that is convenient is to go to dimensionless quantities. This is the velocity in 2 dimensions in the plane of the sky, and I'm going to multiply it by the Newtonian circular velocity, so that gives me a dimensionless quantity. Okay. Remember the masses, we know them very well, to about 5% precision. The separation we also know very well. The errors on velocity are the largest errors we have to deal with here. Okay, so we need to know the ellipticity of these things. We don't know the ellipticity of these things, but at least statistically, that has been measured. And just very recently, 2022, a big team looked precisely at the ellipticity of these binaries. The way you measure the ellipticity of this binary is very smart. You actually take the relative velocity vector on the plane of the sky, and you have the relative position vector over the plane of the sky. If you take them as vectors, there is an angle between those two things, and that angle constrains the ellipticity. So they've been able to say that this is a separation on the plane of the sky of two binaries, and this is the eccentricity of those orbits. Well, it's not actually the ellipticity. The ellipticity is given by a probabilistic distribution, which is parameters in terms of this parameter alpha. So we know statistically what the distribution of this ellipticity is found. I don't know the ellipticity of any particular one, but I know as a function of separation what the distribution function for the ellipticities might be. Now, if I do this projection, I can calculate the velocity in this dimensionless quantities in 2 dimensions between the 2 components of the binary, and it's given by this thing here. Okay. Now I is the projection of the plane of the orbit on the plane of the sky, an angle which I don't know, and these 2 angles are the projection of the ellipse on its with regards to this angle here. I don't know either. And phi naught is the true anomaly. It's the position, the current position of the binaries, the reduced volume of the 2 stars along. So I don't know that one either. I don't know any of this, but I know them in statistic. Okay, I know these things are oriented randomly. They are not looking for us. They're not waiting for us to look at them. So they're distributed randomly on the plane of the sky. I know that this is a random orientation. The same for this other angle. So the ellipse on its plane is randomly oriented. The occupation of the face occupation, that's distributed according to the duration of the face, and the ellipticity has been measured. So I know this is statistic. Okay, I know all these distributions. So then what I can do is calculate, for example, what the distribution of this velocity should be as a function of, for example, the velocity. How many small velocity binaries I should see, how many large velocity values, and so on. And these curves are calculated for various values of this alpha ellipticity distribution parameter. Okay, and this is gamma, the value of any boosting gradient. If gamma is 1, then the problem is entirely Newtonian. If gamma is above 1, we're seeing an anomaly. Okay, so these are the distributions I then have to compare. That's definitely a prediction I have to compare against the plate. And this is the first thing I did. This was published just this year. And essentially, the blue curve is the best distribution, and the red curve is the observed distribution in the high velocity case, which tells me with this precision, this level of precision, that my data in a high acceleration regime are strongly favoring a Newtonian model. Okay, it's sort of a confirmation that I'm doing everything right. I just grab the full distribution of velocities and compare it against what comes out of here. I do a Cosmological comparison between the 2 distributions, and I ask what is the best fit value of little gamma, and I get 1. Okay, that's some error. If I repeat the same process in the low acceleration regime, I get a gravitational anomaly. I get that the data are immediately telling me that gravity has been boosted by a certain amount, which is consistent with the MOND prediction. These are just sort of the Cosmological best fit parameters as a function of the assumed value of gamma. And for the the different polar curves correspond to different assumptions on the distribution of electricities, which we can keep as a kind of systematic uncertainty. But it's obvious that in the high acceleration regime, all these minima clearly identify something very close to Newtonian, whereas in the Vega-Bratian, the errors are larger and the numbers are smaller in the high separations, but still they are quite clearly inconsistent with Newtonian binding point. There is a definite gravitational anomaly being shown by the data, so there's no way around. Now, I don't know how much I should, 10 minutes, okay. Then I'm going to kind of skip over this point and we can discuss it later if we want. Essentially, how certain I can be that there are located tertiaries and so on. Anyways, essentially, I'm not going to discuss much about that. Okay. If you want, I can explain some recent work that we've been doing regarding being absolutely certain that each of these stars is individual and not a double. Anyway, this is from another sample. It's the same kind of diagram from a sample by Kyung Chai, who's also been working on this, and again you see the same clear consistency with Newton over here and clear inconsistency with Newton over here. This is a small boost we're looking at. That's sort of 20% boost in velocity, which implies a sort of 40% boost in gravity. And as I showed you here, the systematics change with separation. Okay, this is very clean. This is not quite clean, mostly because the error in the data are more or less constant, but the velocities become smaller when you go to the low acceleration. So the signal to noise has been degraded, and we have less signal to noise over here than here. So what if this is apparent inconsistency with Newton is an artifact of using lower quality data? Okay, I want to check that. And the way of checking that is basically constructing homogeneous samples. So I'm going to take samples at different separations which are exactly the same. Previously, we had changes in numbers, changes in this and that, changes in signal to noise. So I'm going to construct samples at different separations which have exactly the same number of stars, which have exactly the same signal to noise values, and which are distinguishable in every case. So I'm using this other sample because it's larger than mine, and hence I can split it up more finely. And these are things like the mass. This is the total mass in the binaries, okay, here, and you see that both the dispersion and the mean values show no change between the low acceleration and high acceleration. The low acceleration bin is wider because I need to include more stars if I want all samples to have the same number of stars. The quality of the single stellar fit is here. This Lua Gaia parameter is exactly the same across the samples, and this is the distance at which I'm looking at the sample. They are all equally distant. Okay, I'm not looking at nearby stars in one case and close by stars in the other. All the samples have been constructed to be perfectly homogeneous. All the systematics are the same. Okay, and the errors are the same. Crucial. The signal to noise value is the same across all samples. And this is what I get. This is the value of gamma as a function of separation for the solar sample. It is noisy. The curve I'm showing is this MOND expectation. It is not bad. It's certainly much better than Newtonian expectation, which is a flat line at gamma equals 1. Okay? And that's not what you're seeing. So even taking a strictly homogeneous samples, the gravitational anomaly is clearly there, and it's clearly favoring this this model where gravity is boosted by about 50% in the low acceleration regime with respect to Newtonian values, which would be a flat line back here. Okay. Well, this is obviously fairly important, and unfortunately, over the past couple of years, Kyung Chai has confirmed my results. This is using much larger samples, Larger samples means the systematics are not quite as strictly well handled as in my case, but even though his systematics his handle on the systematics is not quite as strong as mine, his statistics are much better. Instead of having 500 stars, he has 3,000 stars, and this is the kind of results he gets. On the bottom panel, you see the deviation between Newtonian and this is a low acceleration, and this is the Newtonian. The deviation between you see a dispersion, no? Because again you have obviously projection effects and so on. And at high accelerations, he reproduces the Newtonian expectation perfectly well, very accurately. But at low accelerations, you start seeing a deviation. Okay, these are his data, and now this is the diagnostic plot I was showing. This is the explicitly accurate reproduction of Newtonian expectations in the high acceleration regime, and then a certain transition, and then a very interesting sort of 20% offset in the velocity. So here, and this is what he reports. Now I obtained 1.5 plus minus 0.2. He gets 1.43 plus minus 0.06. So his accuracy, the statistical significance is much larger in this case, but both results are consistent. Okay, and he's got several new papers. This is some of his new papers, and he's doing this again very carefully and looking at how this changes. These samples are not homogeneous. They don't have the same number of stars. They don't have the same signal to noise. So that's something new that I was doing. But in any case, all results are consistent so far. Okay. And I'll just jump to the conclusions. So looking at samples of isolated unbound binaries from Gaia, very carefully selected against chance associations, projection effects, presence of tertiaries, etc., we can derive distributions of velocities and compare them to Newtonian predictions. For small separations, the results are fully consistent with Newtonian expectations, but for large separations, we see a very clear anomaly. A very clear anomaly, which, if we compare against models of this type, implies this. Okay, we get a gamma of 1 for the high acceleration region, and a gamma of something like 1.5 or 1.4 or something like that for this low acceleration region. Now, this is, I think, this is actually showing in absolute clear terms, in terms of empirical data, that you can't really argue with, I think, that we're looking at the validity limit for Newton and Einstein gravity in the low acceleration. I don't know why this should be so. I mean, the existence of a validity limit for any theory of physics is really, I think, natural and to be expected. We actually know that general relativity cannot possibly be the final and absolute answer at all scales. That's been well known for a century, because it's inconsistent with quantum mechanics. So we know that there is a high acceleration validity limit. No? If we reach Planck scales, GR is no longer valid. Nobody expects that at all. Why should it be infinitely valid on the other direction as well? Well, I mean, 200 years ago, Newton thought he had read all of mine. He had read God's mind. No? What my laws are a reflection of how the universe was built by God, and they're universal and absolute. Now we know that our theories are generally good approximations within certain validity limits. Since construction, we knew that GR had a high acceleration validity limit. I think we're finding its low acceleration validity limit. Okay, and of course this means that we no longer having astronomical necessity for absolute necessity for the existence of dark matter, since we now know that the acceleration regime where these anomalies appear is actually a region where standard gravity is no longer strictly valid. I mentioned that results were consistent with with this particular MOND model, but it will also be consistent with any range of modified gravity theories, where the binary orbits are predicted to have some sort of an enhanced value. No? So I'm not saying that this proves MOND, but does disprove Newton? Thank you.
Any questions? Maybe no, wait.
So this is a modification of the inverse square law in effect.
Well, not really. In fact, the prediction is that the force remains 1 over r squared, but the value of g is enhanced by a certain amount.
So you think it's a function of gravity rather than the inverse square? I'm just thinking, does this apply to other force types?
Well, I mean, if you look at the diagnostic plots, what we see is that the velocities are a little enhanced. Okay. You can get this enhancement any number of ways. You can boost the effective value of g. You can change the radial dependence of gravity. No? There are many different ways in which this could be achieved.
Exactly.
I don't know exactly which is the right one, because I've only tested one particular model, which was this gamma going to g going to gamma g. No? If you do that, if you compare against this kind of models, what is it? Anyways, if you allow for gamma to be different from 1, then the best fit solution is for a gamma of 1.4. But obviously, this equation assumes the inverse square law. I haven't tested other models.
Right. Okay.
I don't know what is the optimal modified gravity given this scheme. I only tested pseudo-Newtonian Keplerian equations where there is a boost to the effective value of g.
Yeah, so you're kind of focusing on that it's a change in g rather than
it might be something else.
Space, distance.
Oh yeah, of course, whatever. Yeah. I only tested this particular scheme.
It was observationally verified that galaxies are expanding. MOND does not predict expansion, so how do you solve this difficulty?
No idea. I don't think we are certain that galaxies are expanding. No.
There are several papers with nice experimental data which show it strikingly.
I know they're
1
growing.
kilometer per second, approximately.
What I've been looking is at the velocity distribution of binaries. I don't know. I mean, as I said, what I can tell you is that if you test this kind of a model, you obtain a value of gamma which is consistent with MOND predictions. I'm not saying that means proves MOND to be perfectly correct or anything.
So the expansion of galaxies could be due to accretion of gas, but elliptical galaxies are found to get bigger with time. So that's the observed. It's unclear why that would be happening, but that's in the Newtonian regime. Elliptical galaxies are in the Newtonian regime because they are high mass concentration, but at very high redshift they are more compact than at low redshift. Okay, so that's
Just also the disks are getting larger, but it not necessarily means that the orbits are getting larger. It could simply mean that they are pretty material, as you say.
Yeah, that's why this is a bit complicated. And then you should also mention that you're testing the wide binary, using the wide binaries to test gravitational theory, and you've put it in a very objective, non-theory specific result. However, if you also want to explain rotational curves of galaxies, then it really collapses the possibilities of the theoretical explanation, basically to what a MOND has to. So any alternative theory of gravitation has to be essentially MOND-like, otherwise you wouldn't get
very similar.
Any other questions? About that, you have a question. Imagine that all the very wide binaries are exactly oriented according to the galactic disk.
No.
And I'm just saying, imagine if that were the case.
Imagine.
Yeah, just would that affect
Yes.
this if they were all exactly, planar within the plane of the galactic disk?
Well, that doesn't make them planar from our point of view.
Exactly.
But you're messing with my assumptions regarding the distribution of sin I.
Yes, but how would you have any idea how that would affect the results?
No. I've only tested I've only fitted gamma, assuming the isotropic distribution of sin I. If that will not vary, I will get different results. I don't know what result I will get, but you're meaning I do get a very good agreement with gamma plus 1 in the small. I suppose you could you could get this result artificially by some particular alteration of the isotropy, or by some particular violation of the isotropy assumption. I'm not sure if the one you're proposing will go this way or it might go the other way. Offhand, I can't really tell.
Because one could say you assume some anisotropic distribution, search for what anisotropic distribution you need to make the same effect, and then exclude this anisotropic
depends on what you get.
because of some plausibility argument, maybe.
I don't know anyone has any expectation for wide binaries to be completed in the galaxy, but I haven't tested it. No.
Or perpendicular to them.
Yeah, whatever.
Nothing else? Then we can end, and thank you. So the next speaker is Tomo Sotola, who will speak about his book, The Dynamic Universe. So please begin.
Okay, thank you so much. So good morning, everybody. The name of my talk is The Dynamic Universe. So let's see what is it all about. Dynamic universe theory is a holistic description of the universe. Just like Copernican model was a holistic description of planetary system, now we are getting one further step in by looking the whole space. In dynamic universe, our three-dimensional space is described as a three-sphere, which is the three-dimensional surface of a four-dimensional ball that enables the solution of energy buildup and dynamics of space as a zero-energy process of motion and gravitation. So the basic elements of dynamic universe theory, the three-sphere space and the zero-energy principle, are very well known in prior art. In his lectures on gravitation in the 1960s, Richard Feynman pondered the three-space geometry and energy balance of the universe as follows. On page 10, in a book including his lectures in 1960s, he stated, if we now compare the total gravitational energy and the total rest energy of the universe, lo and behold, we get the amazing result that the total energy of the universe is zero. Why this should be so is one of the great mysteries, and therefore one of the important questions in physics. After all, what would be the use of studying physics if the mysteries were not the most important things to investigate? And further, on page 164, one intriguing suggestion is that the universe has a structure analogous to that of a spherical surface. If we move in any direction on such a surface, we never meet a boundary or end. Yet the surface is bounded and finite. It might be that our three-dimensional space is such a thing, a three-dimensional surface of a four-sphere. The arrangement and distribution of galaxies in the world that we see would then be something analogous to the distribution of spots on a spherical ball. In fact, the dynamic universe is just a dynamical solution to Feynman's great mystery. For that, we need some reinterpretations of the definitions behind the theory of relativity. Let's look at that. In the theory of relativity, the fourth dimension is designated as the time dimension. However, the line element in the fourth dimension is not seconds, so d is c times dt, which means that it's measured in meters instead of seconds. Interpreting the fourth dimension, metric dimension, we are not at 13.8 billion years from the starting point, but any point in space is at 13.8 billion light years distance from a starting point, from a point in common. Geometrically, it means that the three-dimensional surface of a four-dimensional ball is expanding at the velocity of light. So let's continue for that. In the expanding free space, the rest energy of any mass m in space appears as the energy of motion due to the motion of space in the fourth dimension. And the energy of motion of the total mass thus is equal to the total mass times c to the second. The gravitational energy of the three spheres phase is equal to minus gravitational constant to total mass times the mass equivalence, which is almost equal to the total mass divided by the radius in the fourth dimensions, r4. And as stated here, the mass equivalence can be calculated to be 0.776 times the total mass. And at the baryonic center, at the barycenter, and R4 is the 13.8 billion light years as stated earlier. So applying the average mass density, which is essentially equal to the critical mass density in the phase space with the volume, which is equal to 2 times p to the second times radius to the third, we can solve the velocity of expansion, which appears to be equal to 300,000 kilometers per second. So that's indeed what Feynman stated, that there's a balance of gravity and the rest energy in space. So what we can conclude for that, it means that we can look the three sphere as a spherical pendulum. So we start from a large sphere and let the energy of gravitation to be converted into the energy of motion. So we get motion against release of gravitational energy. So it costs nothing to get that energy. And now we come to the turning point and it continues. Then we pay back the loan of the energy back to the energy of gravitation. Interestingly, I recently found that the possibility that the negative energy of gravity could supply the positive energy of matter of the universe was suggested as early as 1932 by Richard Tolman, although a viable mechanism for the energy transfer was not understood or known at that time. So it looks like being a very essential, very obvious way of creating the energy in the universe. So let's compare that to the present model. So now in the standard cosmology, everything appeared immediately from nothing, and time started to run from 0 point. Now we extend the time axis back to the early time, and we start by first contracting, and then we go to the singularity point, and after that we come to the expansion phase where we may pack the energy. And one of the nice features here is that, let's take the pointer here, that we can now get a precise mathematical expression for the dynamics of the expansion, so that we can express the development of the radius as a function of t, and also the development of the expansion velocity, which also determines the velocity of light in space. So we can also see that the zero energy balance requires that the maximum velocity in space is equal to the velocity of expansion. In order to compare that to the standard model, we first make the development of the standard cosmology model more realistic by applying the light travel time, which gives us the curve of the development of the radius here. And by setting the dark energy parameter equal to 0.735, we can find that the average expansion velocity equals to present velocity of light. If we give dark energy a value of 0.9, then it means that it extends the age of the universe. And if we put it to 0, as it was the case with the Einstein-de Sitter model, then in fact we come very much to the same conclusion as we have in dynamic universe, which follows the zero energy, or let's say conservation of energy in the development, and gives exactly the same age estimate, which is 9.2 billion years, same as we have here in the dynamic universe. It is measured with current years. Okay, let's go further. A very interesting observation here is that when we compare the development of the energy, so the energy of matter and radiation in standard model has been essentially constant during all the time here. And as Feynman also stated, today it looks like we have the balance between the gravitational energy and the rest energy of matter. So it means that in the past such balance has not occurred here. In the dynamic universe solution, we have the zero energy balance all the time. And what is very important here is that when we look the early development of the universe, the energy state here has been roughly as it is today, but in the dynamic universe here, we have enormous energy available for a very quick development of galaxies and other structures in space. And I think this is very, very important result here. Also to give one possible answer to recent problems. As you hear, this MIT news is from last week, so there are some ideas of trying to solve the problem with early dark energy to have the quick development. But that's not stuck into this, but continue what it means to have motion in space in our spherical system, which means in this drawing, in this projection, it means a tangential direction. So any mass m has velocity c in the fourth dimension. Also it means that it has momentum mc in the fourth dimension. The rest energy of mass is the energy of motion due to velocity in the fourth dimension, balanced by the gravitational energy, which we can consider as resulting from the mass equivalence at the center of the fourth sphere. Locally, any velocity v in space is associated with a p of c in the four, as I stated, and also the momentum. which means that the total momentum is the orthogonal sum of the momentum mc in the fourth dimension and momentum p in space, which results in the formula for the total energy. When using this expression here, it appears to be necessary to divide c into two parts, which is z0, which is the expansion velocity in the fourth dimension, and c then is the local velocity of light, which in homogeneous space is equal to c0. You can immediately recognize the formula here to be equal with the total energy in special relativity, and also we can calculate from that the total the momentum in space when we look the velocity in space. But what the theory of relativity does not disclose is the effect on the rest momentum. But when we look the total energy balance, we can conclude that the rest energy is reduced by the factor square root of 1 minus beta to the second, and we will look that at a little more detail in the next slides. So the starting point, starting condition, we can consider as being homogeneous space. Homogeneous space, and how can we conserve the energy balance of gravitation and motion when creating motion within space and condensating mass into mass centers? So the trick nature is using is very simple here. So we bend the local space, which means that we can get from the original C0 now. We can divide into two orthogonal components. One is the free fall velocity in space, and a reduced velocity component in the local fourth dimension, which now is bended by a small angle compared to the homogeneous space. What is important here that the velocity in free fall is obtained against the reduction of the local d velocity. So and against the release of local gravitational energy of the falling object, which means that we don't need to bring any new further energy into the system. Looking the symmetry between the motion and gravitation here, we can easily express the reduction of the rest energy in terms of the local gravitation. So it gives an expression which is very close to the corresponding expression in general relativity. Now we don't have that possibility of obtaining velocity in space at constant gravitational potential. So let's look what we need there. Yeah, there's also the same kind of mass center creation may then occur in different steps. So let's think that the first one is let's say Milky Way mass, then solar system, and then Earth, and so on. But let's continue to look the build-up of velocity at constant gravitational potential, which now requires energy input, delta E, which we can express in form in C0 times delta MC. And what is interesting here is that let's take the next one. Any motion in space is central motion relative to the center of the free sphere, which means that the central force created by the motion in space reduces effectively part of the gravitational force resulting from the mass center, And we can see that as we can describe this as a reduction of the rest mass and rest energy. And now we can see the small component which corresponds to the available rest energy for an object in motion in space. And at the same time, it means that the work we do in creating velocity in space is exactly the work we do against the gravitational energy of the rest of mass in the universe. It's the exactly Mach's principle. So now we have a quantitative expression for Mach's principle, and we can really understand that any local event is related, is connected and linked to the rest of space. Now combining the effect of motion and gravitation, we can express the locally available rest energy for a mass object as the rest energy in non-bended space multiplied by the gravitational factor and the velocity factor. And we can show that, for example, atomic clocks and any atomic processes are proportional to the rest energy, or being a little bit more precise to the rest momentum. We can see that the frequency of clocks, atomic clocks, has both a gravitational factor and velocity factor, which is comparable to Schwarzschild solution for time dilation due to gravitational factor and velocity factor. And the general picture, overall picture of the geometry of space near mass centers looks very much the same as we are used to see for the space-time profile of general relativity. But what is now very important is that we can relate any local state to the principal state of rest in hypothetical homogeneous space. We first create the last structures by creating a dent in a system, then smaller mass centers and smaller mass centers as solar system, and then on the Earth system, and then we can come back to our laboratory environment, and ions accelerated in the accelerator. And now what is called relativistic effects, such as the effect on the emission and the clock frequencies, follow exactly the same kind of formula as we have derived in the metric and kinematic space theory of relativity. You may have paid attention at this time we have very important effects without changing the meaning of time and distance as coordinate quantities, which are essential for human comprehension. So we can state in expression of relativity, in general relativity, special relativity, they are based on constant velocity of light and constant rest mass. In dynamic UEs, we have universal time and universal distance. And let's follow first what means having constant velocity of light and rest mass means that time and distance are functions of the state of gravitation and motion relative to the observer. In dynamic universe, when we have time and distance as universal coordinate quantities, then the velocity of light and the rest mass are functions of the local state of gravitation and motion, respectively. Not relative to the observer, but to the energy frame which we have formed based on the zero energy concept. So here we have the time dilation and gravitational red and blue shift, which are the factors for velocity and gravitation. And then on the du side, we have the rest energy expressed now in 4E times C times C0 mc, and it's stated the m, which is the rest mass, conveys the effect of time dilation or special relativity, and C conveys the effect of gravitational and red-blue shift of general relativity. The rest energy or mass here, m is constant and C are constant. And we can see that the system of nested energy frames, which we saw in the previous slide, means a full replacement of the relativity principle, and it explains the local state of rest and relates local to the whole, which is very important, so that there's no separate object in space, but everything is related to the rest of space. And very concretely, the difference can be seen here in the clocks, and explanation for the slower frequency of clocks in motion or close to mass centers. So local gravitation and relative motion reduce local flow of time. That's the explanation in relativity. In du, we have the system-oriented description. The local gravitation and motion reduce the rest energy. And here we can see, in fact, the H0 here means that we can identify when we solve the Planck equation and Planck constant utilizing Maxwell's equations, we can show that the Planck constant H includes the velocity of light as a hidden factor. And once we remove that, we can see that the clock frequency is directly proportional C, which also means, and we can base the equation now to quantum mechanics directly. mc times the difference in the quantum states here. And it also means that once the clock frequency is proportional to C, it means that whenever we measure the velocity of light with atomic clocks, we get the same results. Also, it means that we can now bound together all the well-known gravitation, the well-known experiments on relativity. Also, we can understand why the velocity of light is clocked to a closed system, because the reference is not in space, but is this local fourth dimension. So at constant, when we have Michelson-Morley experiments or things like that, at constant gravitation, which we have a horizontal installation, they experience the same velocity of light. And also now we can relate all the individual experiments, clock experiments in laboratories to the reference clock in the ECE, Earth-centered inertial frame, which is used in all satellite experiments and measurements like GPS, Global Positioning System. And once we have far away reference clocks on planet Mars, or even in Pioneer, which is far away from solar system already, we need reference clock in the parent frames. So let's look at what all this means in celestial mechanics, in Schwarzschild space, in du space. First, we can state that both approaches explains the basic test of general relativity, perihelion advanced bending of light close to mass centers, gravitational lensing, Sapir-Whorf Sagnac effect, emission of gravitational radiation related to the periodic decrease of binary stars and everything else. So that you have the DU book circulating here, but you can also load e-book version from this link here. So let's see. However, there are some very important differences in these two approaches. So orbits closer than 3 times the Schwarzschild critical radius are excluded in the GR solution. However, when we follow the conservation of energy, the zero energy concept close to the extreme mass concentrations, we can find that there are stable orbits that are possible down to critical areas, radius, which in dynamic universe approach is gm to the c to the seconds, which is it's only 1/2 of that in Schwarzschild. The factor 2 here, in fact, comes from the Newtonian boundary condition used in general relativity and in Schwarzschild solution. And also, what is very, very important is that once local systems, theory of relativity is a local theory. So it means that local, in order to conserve the energy in local systems, it's assumed that local systems do not expand with the expansion of space. The situation is different because all local systems are directly linked to the whole. It means that in order to conserve the total energy balance, it means that gravitationally bound local system expand in direct proportion to the expansion of space. So it's very, very essential difference. But let's look first the orbital velocity and orbital velocity and escape velocity here. Okay, the orbital velocity meets the escape velocity at when the radius is 3 times Schwarzschild critical radius. So it really means that there are no orbits are possible beyond that limit. And I have simply taken these equations for escape velocity and for orbital velocity from Foster and Nightingale's book on relativity, general relativity. But what happens in dynamic universe is that now the essential difference comes from equivalence principle, because in the equivalence principle we have the increase of mass of the relativistic mass also in free fall due to the equivalence principle. And in fact, I have traced that is one of the key factors that results the problem here. Here we could see that the mechanism is different. In free fall, we are not increasing the total energy, the energy of the falling object, but we conserve the energy balance, and now we have slow orbits also close to the critical radius, which is extremely important in the sense that now we have the mechanism that maintains the mass of the black hole without any new assumption or any singularity or anything else in the black hole. We have some experimental data of the neighborhood of Sagittarius A, the big black hole at the center of our Milky Way. So there were already about 20 years ago, there were noticed that very fast periods close to the center of the black hole, something like 70 minutes. And when we compare that to Schwarzschild prediction, we can see that the minimum period is somewhere here, 3 times Schwarzschild critical radius, something like half an hour, 29 minutes. The corresponding equation in dynamic universe looks a little bit complicated, but we can see that it matches extremely well with the observations here. And also we can now see the possibility for the low orbits, which means that higher orbit times when we are very close to the critical radius here. Then let's look the expansion of local system. There are plenty of evidence of observational support. Once the observations are cleaned from the interpretations tied to the theory of general relativity. And what we can find here, there are coral fossil and sediment layers where we can count the number of days. There are periods also, the annual period, so we can count the number of days in a year, and that development has been observed almost for last 1 billion years. Ancient solar eclipses for about 4,000 years back, planetary distances, Earth to Moon distance, which are measured, and the geological development of the Earth and Mars. So these are the observations of the length of the day. When we go back in time, in current years, back to 800 million years. The standard model prediction relies on tidal friction and gives an estimate of 2.5 milliseconds per day in a century. But then when we add the expansion of local system, which affects the length of the year, that's the effect of the expanding solar system, and the increase of the length of the year, we need to subtract 0.6 milliseconds, and we end up with 1.8, which exactly match with the observations here. Conclusion: fossil data gives strong support to the expanding solar system. And then the solar eclipses. So these are direct measurements of the length of the day in 100 years here. These two observations are very close to each other, so from the coral fossils and solar eclipses. There are measurements of length of the year with atomic clocks, and the change indicated by NASA is 1.5 milliseconds in 100 years. When we add the effect of the change of the velocity of light, which also affects the clock frequency, which gives a correction of 0.3 milliseconds, which gives 1.8, which now is very, very, very close to the previous data. And here the tidal friction, which I showed in the previous slide. And when we remove the GR predictions here, we have only the DU predictions, which all goes to the same estimate here. 5 minutes. Yes. Sorry, 10 minutes. 5 minutes. Okay. So let's look the local measurements here. The Earth to Moon distance has been measured with laser for about 50 years already. And the result is 3.8 centimeters per year. Also, the transponder measurement, basically similar principle, not in lasers, but with radio signals, which gives, if we interpret the results by calculating the clock cycles, we get an increase of, which is directly proportional to the expansion of space, which means that the orbit of the Earth increases about 11 meters per year. However, the GR interpretation states that the earlier measurements have occurred in a different time frame, so that the clock readings are corrected. They are not counted from the clock pulses, but they are corrected with Einstein effect that reduces, that in fact removes the effect of expansion. And the conclusion is that orbital radii and the Earth to Sun distance do not increase with expansion. In fact, if we use the Einstein effect also for lunar measurements, we didn't get 3.8, but only 1 centimeter per year, because the effect of expansion is 2.8 centimeters per year. And it's easy to understand the faint Yang-Sung paradox, because 3.5 billion years ago, Mars was almost 30% closer to the Sun, which explains the liquid water in spite of the 25% faint to solar insolation. And we can here calculate the development of the conditions on Earth and on the Mars. I have some comments on the cosmological distances, supernova observations. We are not going into detail. Thus, tomorrow morning also, my colleague Petri Lievonen will give more precise data on that, but I simply state some of the basic differences. So in standard cosmology, the co-moving distance, which comes from Friedmann's solutions, is expressed with this integral equation. And in dynamic universe, due to the very simple geometry of space, we have very simple expression here. The light travel distance, same here. Basically, it means the tangential path of the yellow line here, and we get very simple explanation, very simple expression. Very important is the observed luminosity and what is the bolometric magnitude calculated from the luminosity explanation. In standard cosmology, it's based on co-moving distance and double dilution due to the redshift. And this comes from Tolman's article in 1930. And as a real scientist, he at that time says that evidently the Planck equation must be interpreted like this, and evidently the effect of relativity and Doppler effect is something, and he ends up with equation which has double dilution due to here and a higher distance, because in dynamic universe we understand that the distance where we look, we see the object is the optical distance, not the co-moving distance, which means the distance the object has today at the observer's time. And only in order to conserve the energy here, we understand that increase of the wavelength means dilution of the energy, not the total amount of the energy carried by a cycle of radiation. And the very interesting result is that the dynamic universe prediction matches with the bolometric, exactly with the bolometric data which have been drawn with from Tonry's table. So these are magnitudes from each filters, which I have drawn into the graph here. And in the case of standard cosmology, we don't get the bolometric prediction, but something that needs observed change in the observed correction of the observed magnitudes, which are converted to emitter rest frame with co-correction, which in addition to filter mismatch adds the factor of 5 times logarithm 1 log 1 to zit to the observed magnitudes. And now finally I show a few slides how it matches with. So these are the standard model for supernova magnitudes, and then we have the dynamic universe prediction here, and we can see that. Now this works very well, and we can see that there will be change as soon as we can get predictions from a little bit with a little bit higher redshift. And there's one observation now which is 2.9 redshift, and when we put the DU predictions here, it gives a very nice match here. So I will left the rest to my colleague Petri Lievonen tomorrow. I simply state that what we are doing here is that we essentially simplify the total theory structures, and we can follow the historical development which has led to very specified theory sectors here. Is in dynamic universe we can follow the zero energy principle from the very beginning to cover all the parts of physics. Thank you very much for your attention.
One or two questions?
I like very much that your model does predict expansion of galaxies, expansion of the solar system. That's what we observe, so it's important.
Yeah, it's very essential how we interpret the observations.
Yeah.
So
I would like to a little bit argue against your opinion that your model is in strong contradiction with the general relativity. I think that it should be the more correct statement is in contradiction with the standard Friedman metric.
yeah,
We have other metrics in general relativity
yeah.
which can predict the same phenomena in some way as your model.
Yeah. Well, first, I think we all can agree that the nature is what it is, and we do our best to make a description, to describe it in the most understandable way, so that by changing the theory, we don't change the reality. That's fact. But what is essential, what makes the differences between dynamic universe and the standard cosmology and standard physics, we can say, comes from the initial postulate basis. So that now we base the theory on the zero energy balance, which means a kind of double entry bookkeeping of energy. And also we accept starting from a closed entity with the most simplest geometry which is possible, which means the three sphere. And we continue deriving all the consequences from that. So then it's a little bit difficult to make specific reasons why it differs from general from certain predictions of cosmology or relativity. It comes from the postulate basis already.
I think we should move on. So the next, thank you.
Okay.
Next question is Styrman on evaluation of theories and methodologies. Relativistic physics versus the dynamic universe.
So, thank you for the invitation. I'll carry on from where the flow ended. Okay, so topic is evaluation of theories, not just theories, but also methodologies. So it's a relativistic physics versus the dynamic universe. Relativistic physics is abbreviated as RP and comprises the special and general theories of relativity, SR and GR based standard cosmology, also referred to as ΛCDM, and DU, the dynamic universe. So that's the book that circulated there, and you can find the book and a lot of articles, introductions, etc. from the web pages. All right. So, contents, first some background, and then the evaluation criteria, and then the actual evaluation, and then summary, and then we look at more detailed view of some examples as much as we have done. So background, why do I defend DU? Why? So I'm interested in logical and metaphysical systems that try to make sense of concepts such as time, possibility, and truth. And these systems gain credibility from compatibility with contemporary science. So you can say that, okay, now you're doing scientific philosophy, it's compatible with physics. The problem is the comprehensible system requires absolute simultaneity, and relativistic physics just violates it. So I had some choices. Many philosophers, they try to make careers of trying to make sense of relativistic physics or relativistic conception of time. So it is an endless project, and it does not yield an understandable worldview. It does not yield a compatibility with absolute simultaneity anyway. So I decided, no, this is not my cup of tea. I will not spend my life investigating relativistic conception of time. The other option is then try to reconcile relativity with absolute simultaneity, like adding a privileged reference frame on top of special relativity. But it does not work because it violates the relativity principle quite directly. We'll return to this later in time. And then we can proceed independently of physics. Like most of our logicians, like temporal logic, they never mention physics. They just like skip it. And that's great. But if you try to make like scientific philosophy, then it should be compatible with physics. So the problem is that it's not scientific if it's not compatible with contemporary physics. So that's the final option that I chose, that I try to find a system of physics that does the job of relativistic physics and saves absolute simultaneity. And that was then DU, okay. And the problem is that you face serious dogmatism, of course. Everybody says, no, this won't do. It's not the great Einstein. No. So that I must defend DU to make my philosophical systems credible. So that's why I'm defending DU. So I'm not a physicist, and I assume here that Suuntala's claims are correct, and then I draw conclusions from them, and everybody can challenge them. You know, that's what you are here for. You can find problems and tell what's wrong, and I encourage everyone to do that. So now we'll talk about the evaluation criteria, the criteria by which we should evaluate theories. And here we can see a transition from classical to relativistic criteria. You can see the timeline there. Okay. The classical ideal started somewhere around there, came into force, and it was there all through here. Prevailed there. It was respected in the era of classical physics, and it's in short is that scientific theory ought to provide a causal mechanical, or at least a dynamic explanation that elucidates force or energy transaction, makes the explained phenomena understandable, and yields novel predictions. So the criteria has it's changed throughout history. For instance, here due to Maxwell's equations that could not be modeled by these wire systems. So there was no need, then it's changed the criteria, but it still, you still had to have a dynamic explanation. Okay. And then relativistic physics became the paradigm in the first quarter of the 20th century. And thereafter, physicists who conceptualize reality through the lens of relativistic physics, often regarded as the only alternative. So either true or correct, but still like the only alternative. And what has happened is that whenever it has not provided a classically virtuous explanation, the explanation that respects the classical ideal, it has not been falsified, but the criteria have been modified to conform to relativistic physics. These criteria have a lot of common in the general criteria for theoretical physics. So this means that the problems of relativistic physics, they have not falsified, but they have been concealed by legitimizing them. So the criteria have been changed so that the problems are not problems anymore. Although they would be problems if we would respect the classical criteria. And one big sign is that instrumentalism is taken as a whole philosophy. The predictions are prioritized over explanations. This means that the classical notion of understanding a phenomenon by understanding its explanation is like demoted into understanding how mathematics is applied and how a theory is applied in producing a prediction, or how does it create a mathematical description, and very typical in modern theoretical physics. And then in case of relativistic criteria, anomalous data may be disregarded or accommodated with the help of additional hypotheses in an orderly fashion. So I'll show many examples of this soon. And at the same time, rival theories are eliminated in the peer review process because they are inconsistent with relativistic physics. But no visibility in top journals, no funding, and of course they do not belong to physics education. So here's it symbolizes this gauntlet of infinity from Marvel. So this means that you can do whatever you want. You can do like, you just add a parameter, and that's great, but simultaneously you reject everything that's not compatible with your pet theory. So it does not look very fair. And here's what Martín López writes about this, and also this physics essays editor. It's told that this is the reason why he founded the physics essays. Okay, so how to get out of the situation? Well, first, we must see that fundamental theories, they are unfalsifiable. If you can't always complement them, they can explain everything. Like this picture of Quaid. Like any statement can be held, come of may, if you just make adjustments to the system. And Feyerabend, that theory is shape and order facts. So if you just change the facts, you can always hold the theory. So we need rival theories to understand their weaknesses. Here's Thomas Kuhn and Feyerabend. So this first quotation is from Feyerabend's memorial book. The weaknesses of theory do not appear often if the theory is confronted with the facts from its own perspective. But an alternative an alternative perspective is needed, and then Feyerabend continues that the invention of alternatives constitutes an essential part of the empirical method. Then again, the consistency condition eliminates alternatives and is in disagreement with empirism. So it's not really fair to just reject theories because they're inconsistent with the standard theory. And Thomas Kuhn points out that, okay, this has happened in the history, so we need rival theories. So which criteria should be applied in evaluating rival theories? Kuhn proposes accuracy, internal external consistency, broad scope, simplicity, and fruitfulness provide the shared basis. And is approximately correct. I think after Kuhn, there's been much literature about theory evaluation of the criteria. And soon we can see that the classical criteria, if we ask philosophers, classical criteria, they're fair. Because philosophers' criteria, they're much closer to classical than relativistic criteria. So I think it's reasonable to apply criteria similar to the classical criteria in the evaluation. All right. And the evaluation is not comprehensive. I just present some examples where DU respects certain classical criteria while relativistic physics violates them. But it shows that DU is quite good. So, okay, and this is what I've learned from also Martín López, that you have one person working for 25 years. You can't expect that you can do the same job as like thousands, an army of physicists has done in 100 years. So it's kind of, you can't say, okay, now, if you want to challenge the theory of relativity, you have to have an as empirically good theory. But it should suffice that it explains the central phenomenon. So the message is that since minimal resources have produced excellent results, it would be rational to allocate funds for further investigation of DU. For instance, 0.1% of the funds currently allocated to relativistic physics would be enough. If you take that from dark energy survey, like little piece from a dark energy survey. Okay. Then ethical virtues. So data ought not be modified. As Thomas spoke about this conversion to emitter's rest frame in the K correction, that counts as a modification of animal data. DU does not require it. Of course, it's not like, it's not done sort of knowingly or consciously. It's not done, it's just there and nobody's seeing it. But perhaps now, at some point, people will notice it. But anyway, it's data modification. And anomalous data ought to be acknowledged. So, this is like a very hard to accept that what Tuomo claims that general relativity textbook approximations yield murderous escape. So we can return to this later. Okay, we return to this later. But this is the next one is quite easy. That general relativity does not provide a plausible explanation for the evolution of the number of days in a year. So it's not being generally acknowledged. And then applied formulas ought to be derived from a theory or considered its additional hypothesis, its primitives. So Thomas found some unethical conduct in the context of the Scout-D experiment. So there was some non-derived formula applied. So this is just to show that there are some ethical issues. But now let's move on to the main part, the explanatory virtues. But evidentiality or empirical fit, that's the primary virtue. We'll be proceeding to evaluating other virtues only after evidentiality is guaranteed. So theories, that's T, theory's total evidentiality was determined by its accuracy and explanatory depth for each phenomenon in this scope. So predictive accuracy, how well its prediction matched data, and depth, how well it describes the causal factors of the phenomenon, and also consistency can be considered as an evidential virtue, so internal consistency and external consistency. Okay. And the next explanatory virtue is ontological weight. It's a number and quantity of hypotheses in the theory's basic structure and its auxiliaries. So we measure the number of ad hoc or any hypothesis. So we don't have to decide whether a hypothesis is an ad hoc. We just measure the weight, how many hypotheses are added to the theory. And then we can formulate unifying power as a ratio of these two virtues. As a ratio of total evidentiality, how much does it explain, divided by the number of applied hypotheses. So a theory's unifying power is great when it explains several phenomena with a simple, consistent structure, basic structure, and a small number quantity of auxiliaries. Now we focus on the ratio of evidentiality and weight. And the conclusion is that when the basic structures of DU and relativistic physics are considered to have an equal weight, then DU has a smaller total weight, because relativistic physics deploys various additional hypotheses for which DU gives novel predictions. So use novel or temporal null. Use novel is that it was not applied in the construction of the theory, the phenomenon, and temporal null, it was not known the phenomenon at the time of the creation of the theory. Therefore, DU is a more unified explanation of the given examples. So here's like evidentiality of relativistic physics with respect to the phenomena under investigation. So this is the setting. This is considered the same. So they are, I suppose they're equally evidential. Then we just measure their weights. And then, because the weight of DU is smaller, the ratio is greater. All right. So we have to set some initial values. So I just said that both are 1 divided by 1 initially. And now I start with the examples. All right. So baryogenesis, this is easy. So standard cosmology needs baryogenesis for explaining the matter-antimatter asymmetry. So that currently there's no antimatter, only matter. But it's supposed in the standard cosmology that initially there was an equal amount of matter and antimatter, so they must explain why isn't there antimatter anymore. So that's baryogenesis. And du does not require it because it doesn't need antimatter in the first place. So we can, so to speak, explain the current absence of antimatter. Quite easy there. And that adds one, so both explain the phenomenon, but adds one to the evidentiality in both cases. But then du does it with its basic structure, while relativist physics needs baryogenesis. Let's add one to the ontological way. Okay? And then the inflation hypothesis. So, pre-inflationary standard cosmology can explain several phenomena, so the inflation was added. Okay? And because inflation is fast, then you needed to end it somehow. So that's why you needed this graceful exit. So you need some metaphysics to explain that too. In contrast, du does not need the special inflation because its basic structure entails or assumes that it was the expansion was a lot faster initially. That's the curve. So again, the same result. One added there to the metaphysical weight, while this keeps sustained, the sustained one. Okay. Dark energy, we know that. That adds one. Du does not need dark energy. And then K correction. Again. So I try to fit it in this ratio. So K correction is data modification. So I can consider that as an additional hypothesis. It's like comparable to additional hypothesis. So it adds one to the weight of relativistic physics. And then we have lots of hypotheses needed for defending the hypothesis that local systems do not expand. So evolution of the Earth-Sun distance, Earth-Moon distance, and the faint young sun paradox. So in all these cases, the empirical data, it's explained away by adding a hypothesis, or several hypotheses. So there's three more to the weight of general relativity. And then Tom showed the problem with the Schwarzschild metric around a black hole. So as a remedy, Kerr metric was invented. But in practice, that just means that you can decide the rotational velocity of the black hole. So it's just one more parameter. So it adds up. Tom did not show this in his slides, but there's an incorrect prediction of the angular size of galaxies. And when I try to fit it in this ratio, I just assume that if it is corrected, that it will be corrected by another hypothesis. So I just add one more hypothesis to its provisional future correction. Currently, it's not correct. Yeah. Then the Mercury's escape. Again, I add one correction hypothesis, although the problem is not admitted, but when it's admitted, it needs to be corrected. And then it adds a hypothesis. I just try to fit it here because the evidentiality must be the same. So I just add it in the weight. And the evolution of the number of days in a year, that adds one. And then there's no consensual dynamic explanation for atomic clocks or the clock frequencies. There are three rival explanations in general relativity. You can also go to that. So that adds at least adds a little bit to the to the ontology weight, while du gives explanation by its basic structure. And finally, the separate issue. As we know, there's a contradiction between general relativity and quantum mechanics, and then additional frameworks for unifying them. But in the case of du, there's no contradiction, at least not any known contradictions. And the approach of unifying them is not like you have to build additional frameworks on top of them, but it's on a postulate basis, unified on a postulate basis, at least initially. Of course, a lot of work must be done. But in general, it provides another kind of an alternative approach to this problem. So, the general picture is that yes, in the context of the given examples, du is more unified than relativistic physics. Okay, and then 5 minutes. Did I have until 12?
Yeah, sure. Go on some questions.
Okay. Now pragmatic versions. So pragmatic versions theory is labor saving, convenient for use, etc. Understandability, it's understandable. And the problem with relativistic physics is the basic metric makes nature non-understandable, but du, because it's just compatible with absolute simultaneity, at least provides an in principle understandable way, a picture of reality. A single theory is easier to learn than 3 theories, but there's a definite geometry of space. And there's a lot of difficulties in choosing between special and general relativity, like twin paradox. We just had a new article from Michal Krizek this year. It was shared there about the twin paradox. So it's not resolved yet. It still continues over 100 years. Is it a stroke of genius, or is it the sign of a problem? Should we keep on talking about the twin paradox 100 years more? What do you think? Or should we drop the theory that entails it? All right. So the summary: based on classical criteria, du is a better explanation of the given examples. Du's predictions are at least as accurate as those for relativistic physics for many phenomena. It's quite unified. It does not require instrumentalism because it provides causal mechanical explanations, and doesn't require data modification. So we get back to this this picture, basic problem. Classical criteria were transformed into relativistic criteria to save relativistic physics in a way. And now we will, du, and maybe other theories too, respect the classical criteria, which are much stricter. The physics community does not accept it because it's incompatible with relativistic physics that does not even meet the strict criteria. So we need wise policymakers who can see through this kind of a dogmatism in physics. But the policymakers listen to the university professors who are typically committed to relativistic physics. So there's kind of a social injustice, and but we are living in a free democracy, so maybe at some point some policymakers understand this. So this is my hope. And I suggest long-term remedies that teach the philosophy of science in all education programs, and then making a rule in science policy that journals must explicate some sustainable evaluation criteria and also follow them. So to make the wrong right in the long term. So that's it. And now we can go through any example from the list you want. If anybody wants to take a closer look at it, we still have like 10 minutes.
Mercury is very on sheet.
So, does anybody have a comment? Or?
If you could speak about Mercury.
May I comment? Mercury's escape. First, I like to thank the very generous evaluation of dynamic universe theory. But yeah, I simply, for years ago, I compared several equations given for the okay. Yeah, several equations given for the perihelion advance of Mercury, and simply put them into the computer and look how the orbit develops, and let it, instead of looking only a few orbital cycle, I looked for 1 million cycle, and then it gradually started to increase. And finally, when I compared that to what I showed you in the comparison of the escape velocity and orbital velocity, the problem that comes close to the, which is admitted close to the black hole, it doesn't come immediately. It develops gradually. So what happens in 1 or 2 cycles close to the black hole occurs in 1 million cycle in low gravitational environment. So that I would be very happy to somebody to calculate more accurately the Schwarzschild solutions, because I tried about 4 or 5 different approximations that I found in textbooks, and they essentially gave us the same results.
Because during your lecture you mentioned that say supermassive black hole which sits in the center of the Milky Way is described by, or the neighborhood is described by the Schwarzschild solution, yes? And Gensel and his colleagues, they use this Schwarzschild solution also to predict the perihelion shift, or the periastron shift of F2 star, yes?
Yes.
And they said it perfectly fits to Einstein's formula, yes? But the black hole which sits in the center, it rotates surely, because Schwarzschild solution is for non-rotating black hole, yes? So how could they get exact, say, the results for black hole which does not rotate? Yeah. No, this is just comment.
Yeah, that's a challenge for mathematics. I'm not good enough for that.
When you did your calculations, if I so when you did the calculation, did you do them full general? Did you do the calculations of the orbit in full general relativity? Because you need a supercomputer for that.
I simply used equations that are given in textbooks, so that's why I needed somebody to go deeper in the mathematics. But the problem, I could easily trace the problem to the equivalence principle that increases the relativistic mass in free fall. And when I removed that from the equations, then I got the stable result also starting from the Schwarzschild solutions. But I didn't go deep in the...
Well, there are numerical issues, for example, the addition of rounding errors, which play a role.
Yeah, I didn't pay attention.
The radiation of gravitational waves makes it a dissipative system. The probability, did you take that into account? I have no idea if that is relevant, I mean, significant, but if you integrate over 500,000 orbits, potentially it would. So I would be careful with.
I have to be careful, but I'm not able to go deep enough in all issues. but for comparison, I also derived the equation for the spiral path of double stars that emit gravitational radiation. I got practically identical equation with what's called Taylor's equations, with the difference that Taylor's equation accept gravitational radiation also for circular orbits, which is not the case the nature works. But in my solution, the circular orbit was excluded, so that the change in period didn't occur for orbital circuits, which is quite understandable because circular orbits are stable.
Also, you mentioned the unrecognized data modification and decay correction. So I don't understand what you mean with unrecognized data modification.
It means that I studied. In fact, I made the comparisons about 20 years ago when it was a very hot subject to calculate the supernova observations, and I noticed we can notice that the prediction for luminosity coming from Tolman's equations, it's based for too long distance, which is the co-moving distance, and also there's the redshift dilution twice. And it means that the predictions gives too much dimming, and the way it's made comparable with observations is that observations are corrected with co-corrections, which is absolutely necessary for correcting the mismatches of the different filters. But in addition to that, it adds an additional 1 plus z to the second power, which is called correction to emitter's rest frame. Although nobody knows why observations that we make on the Earth must be converted to emitter's rest frame. Can somebody answer that?
I mean, if you're looking at a certain region of the spectrum,
yes,
you have to include this decay correction because you have to correct for the fact that if you're looking at a certain region of the spectrum,
yes,
and the emission is not flat, then you have to include the fact that when things were, you want to correct, you have to compare the same region of the spectrum for things that are emitted in high redshift.
Yeah. So the way I did it, I created the prediction for bolometric observations, and you can't get that from the standard equations without applying the co-corrections. That includes the extra term, extra dimming due to Z.
In general, when you're looking at spectral galaxies or whatever, in general, when you're looking at the spectral galaxies, for example, you have to account for the fact that the spectral emission of the system is not constant in all wavelengths. And if you're looking at something that was emitted at high redshift, for example, then necessarily you have to compare the emitted band at the observers at the emitters wavelength redshift.
Oh yes, yes, but that it has been taken already in the prediction, so the effect. In fact, Petri, tomorrow morning we'll have a more detailed analysis on that. So I'm not sure we are speaking.
With the theory, with the standard theory, it is self-consistent to apply the iteration. It's not a fudge or multiplication of the data. At least it's what you require to compare.
So how do you then interpret the term conversion to emitter's rest frame? Why do you need such a conversion?
That's revolution, essentially.
Okay.
Frequency shift due to.
Maybe we come back to tomorrow morning when we heard that was.
Any other issue or question? There's just one thing. I don't understand the matter antimatter asymmetry because that's a problem of the particle physics, standard of particle physics. How come you solve that? Because you don't have a model. You don't have a model of particle physics, right?
Sorry.
No, it's just because we don't need antimatter at all.
So that's not an issue.
Yeah, the normal matter is balanced with the gravitational energy of the. So the rest energy is balanced with the gravitational energy of the rest of space. So that's the balance. We don't need any antimatter to balance the rest energy over.
Yes, but antimatter is in the standard of particle physics. So you don't have a different model of particle physics, right? So and in general, I mean, the standard model of cosmology also doesn't require antimatter because it's negligible. Well, yes, I mean, you only have the problem during the production of matter in the inflationary phase, where, according to the standard of particle physics, matter and antimatter should be produced in equal numbers. That's the problem of the model of particle physics applied to inflation, and that the problem is that we are observing a model, a universe full of matter, so that asymmetry has been broken, and that is not understood in terms of how the standard of particle physics. We don't know what the mechanism is which breaks the symmetry, and that's nothing to do with cosmology. It is not to current knowledge. So I don't see how that is so relevant here.
Well, can I say, can you have the Big Bang theory without antimatter? Can you have it? I don't think so.
Well, it's an issue of how you produce matter in the inflation epoch. So now, I mean, I'm not an expert on the field theories there, but any field which decays, it's an inflaton which decays and then makes the matter must obey the standard of particle physics, and that should produce matter and antimatter in any theory of cosmology. That's not a particular issue of GR. GR doesn't have that in it.
Yes, but still, if you start from emptiness, du doesn't have to start from emptiness, so you don't need antimatter to start with. So that removes the problem.
You have to explain your particles, and that's the standard of particle physics. And
but Big Bang theory is claimed that it is consistent with particle physics.
It can't be, because the standard of particle physics explains antimatter.
This is the puzzle of cosmology.
Well, sure, the matter antimatter problem is a puzzle, but any theory of cosmology will not solve it, in the sense that you don't have an inherent coupling to a new model of particle physics, which somehow breaks the symmetry. At least I didn't see that directly.
Well, okay, one solution would it suffice if we consider unity of total physics, like general relativity were replaced by du, then particle physics would not have this problem anymore. It would not.
It would, because in the theory itself, it's symmetric. We expect if you have an energy vector which decays and makes particles, it also makes antiparticles, which then have their various
Okay, but what was the original? When was antimatter invented for particle physics? Was it because
I
of
think
cosmology?
the formulation of the standard of particle physics includes that symmetry. And the fact that the real universe doesn't have that symmetry is a problem. That's not solved, yes. But that's not to do with...
It's a problem with particle physics, not GR.
Yeah. Well, ultimately, it can maybe, I mean, obviously one is looking for a theory which couples the two, and that probably will solve the problem, but DU is not a theory of particle physics, so I don't see how that problem can be solved with DU. No, because I could equally say you have a standard Big Bang inflation, and I don't need antimatter because I just make a model full of normal matter. Then I've solved it. But that's not true because the standard of particle physics has the symmetry in it, and so that problem cannot be solved in this way.
Okay, I understand what you mean, but perhaps, okay, let's look at when was standard model of particle physics created? Was it after the Big Bang hypothesis? Maybe the Big Bang hypothesis affected it. I don't know.
No, it's an issue of trying to understand how to explain the normal particles we observe. So both the quarks and the symmetries and the theory, and I'm not an expert on that, I'm not really a particle physicist, but you have to understand quantum field theory. I can't tell you the details.
It's just the conversion of mass to energy.
So
It's just the conversion of mass to energy to mass, at least.
yeah,
And the mass has to balance with the energy. I guess the question is, does the dynamic universe theory require a Big Bang, or is it a constant universe?
It doesn't.
No,
It doesn't require.
Yeah, because it energizes the mass in the contraction phase. So it doesn't need any instant appearance of anything.
So what you're saying is that the matter can exist forever.
So, yeah. Well, mass, but matter, I like to call matter as energized mass. Mass is like a substance for the expression of energy. It's measured in kilograms, energy is measured in joules. So that it's such a difference. If for the matter,
so maybe one way to look at it is what you sort of see in an energy packet that has to know that decays into matter, right? So, but you have to also conserve all the quantum numbers associated with these particles, and that requires you to have antimatter, because there are various constant quantities, and then you can't get out of that easily. There's some sort of symmetry breaking which is not understood. And that has nothing to do with Big Bang.
The question is, where is the antimatter when it is? It's not visible on
Well, in your particle physics experiment, antimatter was curious, right?
Yes, but it's not here in the universe.
Precisely. Yes. So there was a symmetry break in the early universe, or whatever makes matter in the universe to break.
Or that there's another part of the universe that we
But it exists.
do not have access to.
Antimatter does exist.
So no, antimatter does exist, exactly. Yeah. It's produced in a laboratory. No?
Yeah, so it's not just hypothetical. It does exist. It can be created. It can be separated.
Maybe even atoms.
So anything else? Because we should maybe
Just have a quick comment. This is all presenting the climate as an additional hypothesis. I don't agree that it's not a fudge factor. It is part of GR. I mean, in GR you have the Schwarzschild solution, which is the simplest solution, the simplest exact solution that has been found. And then Kerr decided, well, we can find an extra solution that includes angular momentum, but he was not trying to it was not presented, it was not introduced as a fudge factor to understand the orbits of anything. It was just an extra solution which is allowed by the theory. Okay. Given the original GR equations of Einstein's equations, Kerr showed that they allow for an extra solution that includes rotation much before the orbits of Sagittarius-A stars were observed. So it's not another hypothesis that is introduced solve any problem. It is a solution which is allowed by the original theory.
Well, okay, sure, it's allowed by the original theory, but still you need the rotational velocity as a parameter, don't you?
As a parameter, yes.
Yeah, so that's it.
Schwarzschild assumes that parameter to be zero, but everybody expects that things sometimes rotate. That's not, you're not introducing additional hypotheses. It is a fact that things rotate, sometimes rotate. If you assume they don't rotate, then you land in the Schwarzschild solution. But if you allow for the fact that things, as we know, sometimes rotate, then that gives you also a Kerr solution.
Well, it's like quite easy that you can decide, okay, sometimes they rotate,
Well,
sometimes they don't, but you can just adjust the parameter.
Things sometimes rotate. It's an empirical fact, things sometimes rotate.
Yeah, and if your theory
Has some rotation.
Yeah, of course, and then if your theory does not produce the prediction with the non-rotating hypothesis, then you just add the proper rotation.
Well, given that stars are observed to rotate, you can see the sunspots rotating. The sun does rotate. You can observe motion in stars; they rotate.
So the problem with the black hole is you can't observe it rotating, but by looking at systematic deviations of orbits around it, that we could infer if it is rotated. And apparently, according to the solutions of the S star, there does not seem to be too much rotation, right?
No, but it's not surprising that it should require some rotation.
But there are uncertainties, and it's probably still allowed to be rotated to some degree.
Yeah, but there should be some independent measurement of this rotation. Otherwise, it is a free parameter, and you can fit with rotation everything. You say, yeah, this is my observation fits with no rotation, another observation with high rotation. That's not science.
No, that's
It's
not
just fitting. You should have some independent evidence that the object is rotating,
At least
and then you can predict something.
for
Not
stellar
free parameter.
For stellar black holes, given that they come from stars, and given that stars rotate, because you can see them rotating, then it's not an artificial fit. You can think of a population of stars, you can see that the stars do rotate, and then it's absolutely not surprising that stellar black holes should also rotate.
Yeah, but you should quantify exactly the rotation rate
Yeah, well,
in some independent way.
you can do it from the original stars from which those black holes
It's
were.
very difficult because the collapse into a relativistic regime might be, we have to come with it relativistically, right? And then yes.
But at least you
It's
can
gravitational
you can
wave,
measure
emission
from direct.
checks away angular momentum. It's not probably not easy to calculate the rotation of a black hole from the previous condition. You can only measure it, and you can only measure it by having objects orbiting about it. And currently only have the S star, not rho.
Oh, but you can calculate the distribution of angular momenta from stars, or you can actually measure it directly.
But the collapse into the black hole and its rotation is not so clear.
Yeah, not so clear, but it is not impossible. I mean, if you see that stars rotate very necessarily, the black hole will also rotate.
But what's the chance if the collapse is not completely symmetric with gravitational waves?
Yeah, there's going to be some changes there.
I'd like to say that, okay, you said that necessarily the black hole rotate. It's only necessary if you assume that general relativity is true. You know, we have an alternative theory here that does not require a rotation. So how do you react to that?
GGR also doesn't require the black hole to rotate. No, it can, doesn't have to. Shall we go for lunch?
Yes.
So thank you again.
So are you convinced now?
Well, first speaker of the session is Elena. Elena Asencio is talking about clusters of Fornax and all this. Let's see. Please.
Hi, so thank you all for being here and having us the organizers also for allowing me to present my work. So today I'm going to be talking about how the distribution and morphologies of the Fornax Clus galaxies, such as they lack dark matter, or in a more general way. Also going to be showing how one can use dwarf galaxies to distinguish between different gravity theories. So, this is working. So, I guess that most of you have heard before about dwarf galaxies. Dwarf galaxies are the smallest type of galaxies. And depending on the criteria that we use to classify them, like they can be classified in different ways. So for example, let's say that we use their formation and origin in order to classify them. We would have on the one hand primordial dwarf galaxies, and this would be the dwarf galaxies that formed in the primordial dark matter halos in the very early universe, and would therefore be surrounded by a dark matter halo, and would also therefore be distributed in an approximately astropic way or asteroidal way. Another possibility is that the dwarfs formed in the tidal tails that can arise in interactions with larger galaxies, and because the dispersion of dark matter is too high to cluster on tidal tails, these tidal dwarf galaxies would then be dark matter free, and in an LCDM paradigm they would therefore be very fragile and very rare, because it would be very easy to destroy them given that they don't have the protected galaxy halo. Now, another possibility is that we classify dwarf galaxies according to their morphology. In this case, we would have late type galaxies, like for example, irregulars and these galaxies, or we could also have early type galaxies, like for example, elliptical galaxies or spiral galaxies. Now, for all of these types of galaxies, but especially for these spiral ones, we see that they have very, very low stellar mass. But in the objects that compose them, like the stars and dust and all that stuff, it has very high dispersions. So if the galaxy doesn't have enough gravity, doesn't have enough mass to keep these stars together, how can it be that the galaxy is not being dissolved? Like, how can it be that we're still seeing this galaxy? So in the standard paradigm, the explanation to this is saying, okay, but these galaxies actually have more mass than we think. They are surrounded by a dark matter halo, and that's why they are not being dissolved. That's what's keeping them together. Which might seem in principle very nice idea and very interesting idea, but we have a little problem with that. We have several problems, but we can focus on the little first. We have a little problem, which is that in the last few years we have found that the galaxies, the satellite galaxies around the Milky Way and Andromeda and Centaurus A are distributed in a planar way, like forming a very thin plane instead of being distributed in an isotropic way. So from this disposition, one would expect that these satellite galaxies have a tidal origin, but we see that they still have very high dispersion. So how can one explain this? This is a very huge problem for the standard model. It's not really well explained in this paradigm. So that's why we go to different paradigms or different models to actually explain phenomena like this. So an alternative to microwave dynamics, an alternative to standard model or to the dark matter hypothesis is microwave dynamics. So in microwave dynamics, we have a modification of the Newtonian law of gravity presented as a possible explanation to the hidden mass hypothesis. So in this model, we do not need dark matter halos. The boost to gravity is given by a modification to Newtonian gravity. And this modification kicks in the regime of low accelerations. That is when gravity is smaller than 1.2 times 10 to the minus 10 meters per second squared. And the way in which the Mondian gravity and the Newtonian gravity are related is the interpolation function, is this new function that you see over here. So, I mean, there are many ways in which this you can be fitted. In this case, we're going to be using the simple interpolating function because it seems to work very well for galaxies. And it has the following shape. So, the way in which this interpolating function works is, let's say that your Newtonian gravity is a lot higher than your A0 constant. So, if your Newtonian gravity is very high, this means that we will be in the Newtonian regime, and we should not be seeing any MOND effects or anything like that. Then this new function will tend to 1, and G will equal Gn. But now let's say that your Gn is very small, so Gn is smaller than A0. So in this case, your new function will tend to square root of A0 over Gn, and gravity will be equal to gravity in the deep MOND regime. Now, as you might have noticed, the Mondian theory of gravity is a non-linear theory. This has some consequences when you try to solve the Poisson equation. One of the consequences, so the effects that arises as a consequence of this, is what we know as the external field effect. What the external field effect says is that the internal dynamics of an object can be affected by the presence of a uniform external field. Now, what does this mean, or what does this imply in the context of galaxies? So this means that if you have a dwarf galaxy, and your dwarf galaxy is in the MOND regime, the moment it approaches, or the moment it's affected by the field of a larger galaxy, the gravity of a larger galaxy is going to damp the MOND effect. It's going to make the gravity of the dwarf more Newtonian. So the gravity of the large galaxy can affect the internal dynamics of the small galaxy. This is what this implies. So, well, just to explain the same thing, but with a bit of a more visual example. Let's say, what happens when your dwarf is isolated in MOND? If your dwarf is isolated in MOND, its self-gravity is stronger than in purely baryonic Newtonian model because of the MOND boost to gravity. What happens in the dark matter model? In the dark matter model, what happens is that also the self-gravity of your dwarf is stronger than in a purely baryonic Newtonian model because your dwarf is surrounded by a dark matter halo that is giving it more self-gravity. But now, what happens when your dwarf gets close to the big galaxy? What happens in MOND is that the field of the big galaxy dominates over the field of the small galaxy, and this causes the small galaxy to have a Newtonian behavior. It has a weaker self-gravity because its MOND effect is being damped by the big galaxy. And then what happens in LCDM? So in LCDM, you will still have that your galaxy is still surrounded by a dark matter halo. So it will still have a very strong self-gravity in LCDM. So this means that, oops, sorry, I don't need to do that. So this means that in MOND, we expect galaxies to be a lot more susceptible to tides than in LCDM because of this external field effect that makes the dwarfs weaker and that it's explosive to MOND. So it's a good thing that we actually have something to distinguish between MOND and LCDM. So as I was saying, we expect galaxies to be more susceptible to gravitational effects in MOND, so to be more disturbed in MOND. But now the question is, what do dwarf galaxies actually look like? So to address that question, what we do is we look at the galaxies and dwarf galaxies in the Fornax cluster. So the Fornax cluster is the second nearest galaxy cluster to us, like only 20 milliparsecs away. And well, it consists of 12 galaxies of different masses, distances, and shapes. And well, what we're going to work with is a catalog called the Fornax Deep Survey Catalog, specialized on dwarf galaxies. And this is actually a very good catalog, among other things, because it's capable of observing dwarf galaxies that are very faint with respect to previous surveys that have been done in the past. Also, an important thing that this catalog has is that it has a visual classification of the morphology of these dwarfs. So the dwarfs in this catalog have been visually classified as undisturbed, disturbed, or widely disturbed, or unclear. And well, in the following analysis, we're just going to be distinguishing between undisturbed and disturbed just for simplicity. And well, after we apply some quality cuts to this survey catalog, we're left with 353 dwarfs, which should be statistically significant enough to do our analysis. So, as I was saying before, and as you maybe can see from some of the pictures, some of these dwarfs appear to be morphologically disturbed. Now, what could have disturbed this dwarf? So there are many options. One possibility is that these dwarfs were harassed by larger galaxies also present in the cluster. And if that was the case, the parameter that we're going to be using to quantify this disruption is the disruption timescale. So this disruption timescale, which is taken from Vyacheslav I, as you can see, can look more or less similar from our model LCDM, but we have to take into account, of course, that in LCDM, our masses are composed by baryonic mass and dramatic mass, and in MOND we need to take into account that our Newtonian constant should be adjusted because we're no longer in Newton, and therefore the G needs to have a correction in MOND. Another possibility is that these dwarfs are being disturbed from tides from the cluster center. So if this is the case, the parameter that we're going to be using to quantify the disturbance is the tidal radius. So the tidal radius is the radius measured from the center of the dwarf, at which the gravity of the cluster tides, or the effect of the cluster tides, starts winning over the self-gravity of the dwarf. And well, as you can see, formula also looks similar, but we also have to take into account once again that in LCDM we have dark matter and in MOND we have that correction to the Newtonian constant. So, having defined these parameters, now what we do is we calculate the susceptibility of the dwarfs according to these parameters. So, let's say that the parameter that we're considering first is the disruption timescale. So, then we have to compare it with the time that this dwarf has been in the cluster. So, the time of the dwarfs will take to be T Fornax, which is approximately 10 years. We assume that is the time that the dwarfs have been experiencing these interactions in the cluster. So, if the disruption timescale is a lot larger than the time that the dwarf has been in the cluster, the susceptibility to harassment is going to be very small, and the dwarf should not be expected to be disturbed. But now, if the disruption timescale is a lot smaller than the time it takes, the time that it's been in the cluster, then the susceptibility is going to be very high, and we're going to expect the dwarf to be affected by this. Going to the next possibility, which is that the dwarfs are being affected by the cluster tides, we compare our half-mass our tidal radius that we defined before with the half-mass radius of the dwarf, which is the radius containing half of the total luminous mass of the dwarf. So what happens here is, let's assume that our dwarf has a very strong self-gravity, either because it's a MOND isolated dwarf or because it has a dark matter halo. This dwarf has a very strong self-gravity. If it has a very strong self-gravity, its tidal radius is going to be very far away from the dwarf center, which means that its tidal susceptibility is going to be very small, and we expect this dwarf to be very protected at its tides. What happens if our dwarf has a very weak self-gravity? For example, if it's a dwarf that is close to a very big galaxy, what happens then is that its tidal radius is going to be very close to the center, and this means that its tidal susceptibility is going to be very high, to the point where if the tidal radius is significantly small to the half-mass radius, the dwarf could even be destroyed. So, as I was saying before, so this is the theory part. as I was saying before, we actually have a catalog with data with which we can calculate these equations and see what is the telescopicity to the actual real dwarfs. So we apply these equations to the data that we have in the Fornax catalog, and we calculate what is the telescopicity, first according to harassment, and then according to types from the center, in these dwarfs. So here we have 4 plots, the first 2 of them, LCDM and MOND for harassment, and the ones on the bottom are for telescopicity from cluster field. So the main message that I would like you to take from these 4 plots is, on the one hand, that the effect of eta harassment, or the telescopicity due to harassment, is negligible compared to the effect due to cluster types. So these values are a lot smaller than these values over here, which means that harassment effect should be negligible compared to tidal harassment due to tides. And so in the following analysis, we're mainly going to be talking about disruption due to cluster tides. So that's one thing. The other thing that I would like you to take from this is that if you compare this plot and this plot, you will see that the telescopicity values of MOND are about 5 times higher than in LCDM. As I was saying before, this makes sense because in MOND, dwarfs are a lot more susceptible than tides because they have this external field effect that makes them more Newtonian and therefore reduces its self-gravity. So that's for the telescopicity values. As I was mentioning before, in this catalog, we also have a classification on whether these dwarfs look disturbed or not. So what we want to compare now is saying, taking these eta values that we have calculated, what is the probability that the higher the telescopicity, they are classified also as disturbed in the catalog. Like, they are not just susceptible, they also look very perturbed in the picture. So we have that both in LCDM and in MOND, there is an increasing trend. So the higher the telescopicity, the more likely is that in the catalog they appear classified as disturbed. But what we notice here is that in LCDM the trend goes up at etas which are significantly lower than one would expect. And we are no longer seeing any dwarfs at eta values at which one doesn't really expect dwarfs to get disturbed. And in MOND, what we see is that the trend goes up at etas which are perhaps a bit higher than expected. So after seeing this, what we want to ask is, what is the specific eta value at which the dwarfs start being classified as perturbed in each of these models? That is, we want to find the minimum eta disruption value. And the next question that we want to ask is, what is the maximum eta or telescopicity that a dwarf can reach before it gets destroyed? Or in other words, we want to find what is the eta destruction value. So in order to do this, what we do is we build a forward model, which is we basically make a simulation. We plot all possible distances, we combine them with all possible eccentricities, and we just combine everything together and just look at the dwarf from all possible angles to account for possible projection effects. But now we don't just want to have a bunch of random orbits, we actually want to have a system that resembles our Fornax system. So what we do is we assign probabilities to these orbits. So let's say we have a lot of dwarfs in the Fornax system that are a certain distance. So this distance will be given higher probability than other distances, and same with eccentricities, and same with the probability of being classified as disturbed given their telescopicity. And well, what we do is we basically feed these probability functions to the observational data. And well, we do this with an MCMC chain, MCMC method, and this will be the triangular plot summarizing the results. But from this triangular plot, I would like you to focus on the plot that is over here, which is, as I was saying, the plot summarizing the minimum eta disturbance compared to the eta disruption. So for LCDM, the values that we get for eta disturbance and also for eta disruption are very, very extremely low. So first line will be 1 sigma, 3 sigma, 5 sigma. And in MOND, we find that these values are a lot higher. And just to clarify, these are not necessarily the eta values of the dwarf. These are the values, the destruction and disturbance values that the dwarfs need to have in order to match the observations. So if this is the parameter space that is allowed to explain observations, one needs to ask then, but what is the actual eta, or what is the actual telescopicity at which a dwarf gets destroyed or very perturbed? And well, in order to do that, we use involved simulations, like one takes a simulated dwarf and makes it orbit as a potential, and with those simulations one sees the telescopicity at which the dwarf is actually getting destroyed. So for the LCDM simulations, we have that the eta destruction is approximately 1, so it's represented by this orange line over here. And in MOND, we have that the eta destruction is of 1.7 plus minus 0.3, and it's represented by this blue thick line over here. And well, as you can see, in the MOND case, we have a very good agreement with the actual telescopicity and the dwarf gets destroyed, and the telescopicity that the dwarf needs in order to match observations. But in the LCDM, what we observe is that there is a very strong mismatch between what one observes and what one needs in order to match observations. Mm-hmm. So, just to summarize what I've been saying. So, on the one hand, we have that observations of the Fornax dwarfs tell us that some are disturbed, and also that we have a lack of dwarfs around close to the center. We expect that the main process that is disturbing the dwarfs and also destroying them close to the center is cluster tides. Intuitively speaking, we would expect that the moment we have a terminal radius that is of the same order as the half-mass radius, our dwarf should be affected somehow. And when it comes to comparing models, in LCDM we have that Fornax dwarfs should not be terribly disturbed because they are very stable due to the protection of the dark matter field and the self-gravity that it gives to the dwarf. Nevertheless, or however, we have that the dwarfs do appear disturbed. And this would require a stability limit of eta destruction of 0.25, which in other words means that the tidal force should be 0.0016 times the internal gravity in order to destroy the galaxy, which is ridiculously small. And in MOND, what we have is that Fornax dwarfs are indeed expected to be disturbed because of this external field effect that makes them weaker to these kind of gravitational effects. And we do see the dwarfs being disturbed in the category. And we have a very good agreement between the required stability limit, which is 1.88, and the body simulations, which imply eta destruction 1.7 plus minus 0.3. So that's all from me.
Do we have time for some questions? Questions from the audience? Well, I have a question. How do you deal with projection effects, for example?
So we do that with the simulation. With the simulation, what we do is we take the dwarfs and we try to do the calculation from different angles. And we sort of give that as a parameter in order to find the best fit.
And do you calculate the external field effect in terms of all the large neighbors, or only considering the central one?
We decide to focus on the cluster tides. We are calculating the external field effects in terms of the main galaxy, like where.
So only the CBD, the central galaxy. But there are other largest ones around.
There are other galaxies, it's true. We assume that the external field effect caused by these other galaxies is negligible compared to the effect of the central, all the center of the cluster. But yeah.
So then maybe, I mean, here you show agreement, but once you take the other galaxies into account, then you will no longer have agreement, I guess, maybe.
I mean, we don't expect the effect to be this strong. I mean, it's true, I have not done the calculation.
Yeah.
I just assume the effect of the smaller galaxies is not as strong as the one of the central cluster.
Okay.
So can I just to paraphrase what you said, it's rather remarkable because the Newtonian predictions with the dark matter halo lead to a result such that there are far too many dwarf galaxies which show signs of tides. Which can't be the case because of the dark matter halo protection, and MOND gets it exactly right. And this was unexpected, but that just comes out of the calculations in this particular application of MOND, which MOND was not designed to address at all.
Yeah. Yes.
So when you talk about dark matter halo, so what does it look like?
So, no, in the paper where we did this in a more detailed way than I explained here. So on the one hand, we were very conservative, and we assume let's assume that because they are in a very convoluted field, let's assume that some of its dark matter has been removed. But even if some of the dark matter was removed, we would still have some dark matter within the optical radius. So that will be 4% of the total halo. And I mean, this has been taken into account in the calculations. And even just 4% of the whole dark matter is making them very stable. Because, I mean, if you remove dark matter beyond the optical radius, your galaxy just goes away in LCDM model.
Okay, so you suppose that dark matter is only in the vicinity of galaxies, or do we allow it to exist everywhere else too, between galaxies?
There are some between galaxies as well.
Like homogeneously, or as much everywhere?
No. We concentrated around one.
That's around the galaxies. Maybe.
Okay. So what if there would be as much dark matter everywhere?
I mean,
Would that work?
I guess then that would not be realistic, and that would be something else, I would assume so.
Okay.
The structure formation means that the dark matter clumps and in the galaxies form. Otherwise, you would need dark matter. You need dark matter to actually make structures.
And to explain the velocity dispersion of the galaxies and so on, it has to be clustered around the galaxies.
So isn't it spherical just?
More or less.
Somewhere there in a spherical approximately.
Okay. So Pavel is our next speaker.
We just heard that dark matter models have problems explaining the dwarf galaxies in a galaxy cluster. And actually observational data rule out dark matter altogether. And let me first explain why we need the dark matter. So we have two fundamental assumptions in cosmology today, and the one is that Einstein-Newton gravitation is valid, and the other is that all matter is created in the Big Bang. One then compares these, does calculations with these assumptions, compares to observations, for example, the microwave background and galaxy rotation curves. And in order then to hopefully explain the data we see, galaxies, distribution of matter, one has to make auxiliary assumptions, which are, we have to add inflation, we have to add dark matter, and we have to add dark energy to these two assumptions to have a model which is hopefully more or less consistent with the observations. Now, dark matter can be cold, warm, fuzzy, or axion. It doesn't matter because given the observational constraints, even fuzzy dark matter is to basically behave like cold dark matter. The important thing is to note that this here is absolutely the core pillar of the model. So if this is not there, the whole model collapses, and we really have to look for a completely different framework. And so, how do we test for this dark matter? The model has the problem that intrinsically dark matter might not be detectable because it is only supposed to work gravitationally, and it can have a cross-section in the electromagnetic, strong or weak interaction section, which is negligible. So theoretically, we might be looking for dark matter, but we will never find it because while it's there, it's simply not detected in the laboratory. Okay, that's the problem. So the question is, how can we test for the existence of dark matter, potentially exclude it or verify its existence despite not being able to see it in the laboratory? And so the dark matter must be particles that only impact gravitationally. So the strong, weak, and electromagnetic force cross-sections must be negligible by the nature of dark matter, because if this were not negligible, then structure formation as the universe evolves and galaxies form, then structure formation would be completely different to what we think today. So this must be negligible, which is why it's difficult to see dark matter. And how can one test the existence for such dark matter particles which only attack gravitationally? Well, first let's look at the predictions of the standard model of cosmology. The model predicts that each galaxy will have a massive dark matter halo, as Elena just now explained. And this is due to each galaxy growing through many mergers and each galaxy forming in the dark matter halo. So this is the scale of 250 kiloparsec. This is at just after the Big Bang, and this is today. And after the Big Bang, we have many little dark matter halos which condense in the expanding universe. In these little dark matter halos, gas coalesces and makes stars, and these little dark matter halos fall together, merge into a big galaxy. And today we see our galaxy, for example, our Milky Way, which is a consequence of such a merger history. And this is then what the Milky Way would look like. That's the galaxy, and that's the dark matter halo composed of all these little subhalos, which are these little ones here, which have not yet merged, which are orbiting around and are slowly dispersing in the system. And so testing for the existence of dark matter via Chandrasekhar dynamic friction. That's the test we can now apply, and basically it works as follows. We have our galaxy with a dark matter halo, and another galaxy with its dark matter halo enters with a velocity Vm, and we can calculate from very simple principles. This is just normal textbook physics. The deviations of all the dark matter particles in this galaxy through the gravitational action of this galaxy, which leads to a deceleration. So this galaxy falls in and then actually gets slower according to this formula. So this is the deceleration, the change of the velocity as a function of the deflections of the huge number of dark matter halo by this galaxy. And this depends on the mass density of the dark matter halo, and this mass density so the effect does not depend on the mass of the particles and also not on the number density, but it depends on the product of these. So it can be black holes, but then you have a few of them. It can be axions, which are very low mass dark matter particles, and there will be many more of these. This is fixed by the cosmological model. This is not a parameter we can change. So this is very well understood, and this action must be there, this dynamic friction, and so the galaxy gets slower, and that's why it falls in, and ultimately it merges. Another way to look at it is that this encounter leads to dark matter overdensity because of the deflections, and this dark matter overdensity pulls back at this galaxy making it slower. And so this galaxy has to fall in and merge with this galaxy. That is why in this model, galaxies merge, but only if there's dark matter. If there's no dark matter, the galaxies will fly past each other and not merge. And so here's a movie of this effect. We can see two disk galaxies, they have an encounter, and then we can see how the centers coalesce, and that's the merger. Okay, and this only works if there's dark matter, because otherwise they just fly past each other like two stars fly past each other. So we can now look at the large and small imaginary clouds as an application of this test. And we see here the Milky Way on the sky. That's the center of the galaxy. This is the large and this is the small imaginary clouds. They are orbiting about each other, and they are falling past our Milky Way now. At these distances, Milky Way LMC is 50 kiloparsecs, Milky Way SMC is 60 kiloparsecs, this is S, and the distance between these two is 20 kiloparsecs, which means all of them are deeply within their dark matter halo. So this one has a dark matter halo around it, this one has a dark matter halo around it, and our Milky Way has a huge dark matter halo around it, and they're all within their dark matter halos. So we can nowadays, we have exquisite motion and position phase-space Gaia data from this Gaia mission for this triple system, Milky Way, LMC, SMC, and so we can therefore we can calculate the orbits into the past to see if there are solutions which are compatible with the standard model of cosmology. So can we find in-full solutions which are allowed by the theory? And before doing that, we have to find, we see a constraint, and that's this by this group here from Spain, where in 2022 they have showed that the LMC and SMC have been orbiting about each other for a long time. So this is the star formation rate of the small imaginary cloud and the large imaginary cloud. Each time it goes up, the galaxy was making more stars, and when this goes down, the galaxy was making fewer stars, and we can see that these star formation histories are synchronized. So when the SMC had a peak here, the LMC also had a peak, and here, and here, and here, and here, which means that basically we're seeing that there were 5 close encounters between the two galaxies since 3 billion years. So over a time of 3 billion years, they've been orbiting about each other 5 times. Yeah, and this is a severe constraint on dynamical friction. So we've now looked at this problem in this research paper here and calculated whether these solutions are possible. Can the galaxies actually orbit about each other, given that they have dark matter halos? And here's just an example that the gravitational force, and this is the force between the two galaxies, at a distance of 5 kiloparsecs, is very comparable to the dynamical friction force. So the dynamical friction force, which slows down the two galaxies relative to each other in the orbit, is as strong as the gravitational force between, which means dynamical friction is extremely important in such systems. And indeed, the frictional deceleration through dynamical friction is comparable to gravitational attraction between the two. And so we find that there are no solutions. So we search for all solutions allowing for at least one encounter in 1 to 4 billion years. So we are actually very conservative. We are saying we don't require 5 encounters in 3 billion years, but we are requiring one single encounter between 1 and 4 billion years ago. Very, very conservative. And here's an example. This is the best solution which misses the 4 billion. There's one encounter between the large and small imaginary clouds here. Then they go apart again. So they have an encounter, that's at this time, and then they go apart, and then they come together again. And then they start to merge. And this is the only solution we have. And it's still outside of 4 billion years. And it's completely impossible to get solutions within 3 billion years where they go around each other 5 times, because the system just merges very quickly. And so there's no solution of the orbit that explains the synchronized star formation history. A solution doesn't exist in the dark matter framework, and this means there cannot be dark matter. It is completely impossible for there to be dark matter. And so this one test alone, conclusively and absolutely, and finally, much more than 5 sigma confidence, rules out the existence of dark matter. Dark matter absolutely does not exist. And So that was one test, but of course there are many other tests. Xavier Hernandez actually suggested a very nice test on looking at how stars orbit in dwarf galaxies, and the stellar composition already shrunk significantly because of diameter friction of single stars on the dark matter in dwarf galaxies. That is not observed, but there are many other tests. I'm not going to go through them. All of these different tests all show that the problem, the model, the dark matter-based models fail. So we had a talk by Elena just now as one example. And if we now look at the confidence plot, that's the confidence we have in the theory as time progresses. So in the 1980s, we had high confidence that the Einstein-Newtonian model is correct. We had to introduce dark matter, we had to introduce dark energy because those were failures of the model, but those failures were saved by putting in dark matter and dark energy. But then there were further and further failures until today with all these different tests, which all have published tests of the theory. Today we can say that the remaining confidence or probability that this model based on dark matter remains valid is less than 10 to the minus 153. Okay, so any scientist can still today, I assume my model to be true with a probability of 10 to the minus 130. It's actually even less than that. Actually, the standard model of cosmology based on dark matter is the most falsified but believed to be true model ever in the history of woman, man, mankind. This historical situation has never ever been like that in the history of science. It's the greatest crisis in physics ever because the community continues believing in this model. It has the opinion that it's still correct, but it is actually completely ruled out totally, radically. And so dark matter does not exist, and therefore we have to look at the problem of gravitation, because we of course have to explain the observations. So the issue of gravitation, reminder is that Einstein published his theory of Einstein relativity in 1916, using still the same data to constrain the theory as ours did in 1648, because it was just a solar system. Galaxies had not at that time been actually understood to be what they are, and the dynamic scale of the solar system had not been discovered at that time, and so applying Einsteinian Newtonian gravitation to systems beyond the solar system is thus an extrapolation by a huge number of orders of magnitudes. And extrapolations usually don't work, so here's a nice Gnacc experiment going back to Israel Barnick. Here we have the idea that we have a trampoline, and we put a weight on the trampoline. So this depth is the extent of the trampoline when we put a weight on the trampoline. So we put a heavy rock on it and the trampoline extends deep. A small rock, it extends a little bit. So we measure the depth and we have the weight, and we have these three data points. High weight means deeper depth, small weight means smaller depth, and that's our empirical law. Just like Newton devised the law of gravitation, now this is our law describing the dynamics of the system, and we can extrapolate it to very, very, very small masses. And that, of course, likely will not work because quantum mechanical effects in the fabric, so from Valls forces on, affect the way the fabric extends. And so we will have a deviation at very low masses of this depth. So that's computational. So the molecular forces in the fabric begin to play a role, and the system shifts from bulk properties to molecular-based behavior. So that's sort of crystal clear. Very nice analogy and how to proceed now with gravitation. Clues provided by the radio acceleration rate in galaxies. And so we have here a galaxy. And we have a centric balance between gravitation and centric fuel. So according to Newton, at that distance from the galaxy, we can count all the mass we have in there, which we see, stars and gas, and that gives us the acceleration we would have to stay on a circular orbit if only this mass is in the galaxy without any dark matter. We then measure the acceleration because we know at that radius the matter must be on the circular orbit because this is this galaxy. And so we measure the velocity of the matter and we get the actual true acceleration. And we can then plot this actual true acceleration against the expected acceleration.
And if Newton is correct, i.e. Einstein is correct, we expect this to be one-to-one. At every distance, we have this, we can do the measurements. And so this is the data, this is the measured acceleration, the actual acceleration, this is what we expect from Newton, and that's the solar system. So we have here Jupiter, Saturn, Uranus, Neptune, and the Earth is up here, Mars and so on. You can see that's the Newtonian regime, a beautiful one-to-one line, both agree. That's the extrapolation to very small values. And here are the data, the measurements of galaxies in various publications. And we now clearly see this deviation. This is a zoom in on this region. So a very clear deviation, systematic deviation. It seems that the space-time is reacting differently to the matter we put in there in terms of its curvature than we would expect according to Einstein. And this is the actual data, as already shown by Xavier, of the actual acceleration against what we expect according to Einstein. And this dispersion is consistent with measurement uncertainties, which is remarkable. It's very unique in astronomy to have such a beautiful law of nature coming out of the data. If we now look at the sort of a little bit deeper theory, we have here the standard Poisson equation. That's the matter, that's the potential, so divergence of the gradient of phi. And we can generalize that in terms of the P Laplace operator. So that's this. Now we've got the P minus 2. If we put P equal to 2 here, this disappears, and we have exactly this equation. So P equal to 2 is the standard Poisson equation. Now the P Laplace operator is actually very well known in mathematics, and this was discovered by Jan van Altenburg recently. And if we now do this plot, so this is the observed acceleration versus the expected one. So this line is exactly equal to, that's the one-to-one line. That's Newtonian acceleration is equal to the observed one, and the observed systems behave according to this equation, which is P equal to 2 in this formulation. So, and if we now go to P equal to 3, so we put a P equal to 3 there, we can, in spherical symmetry, rewrite this equation into this form. So this is still the same equation with P equal to 3, so this becomes equal to 1, the power, and these A zeros cancel here. In spherical symmetry, we can calculate now what the acceleration will be. So this equation, spherical symmetry, becomes this equation, which leads to the radial acceleration equal to the square root of this. And that we can then see that the P equal to 3 case is equal to the P equal to 2 case times A0, which is a quantity we have introduced for dimensional relativity reasons, and the square root out of that. And remarkably, that's exactly this line here. This line is the solution to this equation if P is equal to 3. So Newton regime is P equal to 2, and we go up into P equal to 3, and we get MOND. Yeah, and that's the Brownian acceleration in terms of Newtonian acceleration. That's what we measure, and that's what we expect, and that's exactly what nature is apparently doing. Now, we can continue, so we have this equation. We can then calculate the actual radial acceleration. So we had that before with the circular velocity. We can now calculate the circular velocity from these equations, and we find that the circular velocity is equal to this expression. And this is the mass of the galaxy in stars and gas, and this follows directly from the P equal to 3 Laplace. It's nothing else at all. And that's exactly the barrier to the Fisher relation, where we see here the masses of the galaxies measured by radio telescopes and approximation from 10 to the 12 down to 10 to the 6 and 10 to the 7. And that's the circular velocity, this value here. And the galaxies lie exactly on this line following this equation. Even the tiny little galaxy like DDO 210, which is only a few million solar masses heavy in stars and gas, lies exactly on this relation. Again, the dispersion of the data is consistent with measurement uncertainties. And so that's follows directly from the P to 3 Laplace, and we can then continue. We can go back to this equation here and now integrate, find the potential
and the potential to start integrating here, assuming spherical symmetry, which is good enough far away from the galaxy, and we find that the potential must be a logarithmic potential of distance. That's the prediction of this theory. What do we see in observations? So that's the prediction that the potential depends on distance according to this logarithmic form, and that is observed. There was a recent paper by Vista et al. 2024. This is actually sensational because these people have mapped the gravitational field around isolated galaxies using weak lensing and found that the galaxies which are positioned here at R0, they have a potential around them which corresponds to a circular velocity which is flat out to a megaparsec. You see, this is 1 megaparsec. Basically, the galaxies generate a potential which is a logarithmic potential until the point where other galaxies start to have an influence. This is sensational because the dark matter models predict a decline which is simply not observed. So this is a verification of a theory which is unprecedented in physics, to my knowledge. Maybe in particle physics there are similar verifications. So logarithmic potentials around isolated galaxies out to megaparsec are confirmed. And so why is there this departure? Why is there a Newtonian and a p equal to 3, i.e. Milgronian regime? Milgrom probably gave the answer already by himself. He wrote a paper in 1999 where he shows that one can derive this change from the quantum vacuum. It's not a very deep physical theoretical paper, but it's an important direction. He was able to calculate from the properties of the vacuum what the transition should look like from the Newtonian to the Milgronian regime, and it's related to how many modes you actually can have in the universe as it's affecting you in space-time. So now going back to the original problem with LMC, Milky Way, and SMC, does that work in this new gravitational theory? So we do the same test as before with dark matter. So we have the large and small measuring clouds, Milky Way, and remember that we had to have 5 encounters in 3 billion years through the star formation going up and down in both galaxies. And the solutions are very, very, very easy. It comes out just like that. The galaxies just orbit about each other. In fact, we have many more orbits allowed, so this depends on the amplitude. It's very easy. The galaxies just keep orbiting about each other because there's no dynamic friction, so there's no shrinking of the orbit. So that's easy, and we can follow the system back in time to 10 billion years as the LMC and SMC are orbiting about each other. So further tests, there's something on star clusters, which I will then just quickly skip. Star clusters evolved by ejecting stars, so this is a fresh young cluster. We can see how it's losing stars by ejections, but what is more important is, for this purpose here, is to say that the stars in the star cluster have a distribution of velocities, and always there are stars which are above the escape velocity, where the star cluster the stars leave the cluster. And the prediction in Newtonian gravitation is that the tidal tails are symmetrical. So there should be an equal number of stars behind the star cluster as in front. So the cluster is moving like this around the galaxy. It's stars which were in the cluster are leaving the cluster in the front and the back tidal tail. They're slowly drifting away from the cluster. In Newtonian gravity, there should be as many stars here as there are there. This is confirmed by many, many calculations. What we observe is many more stars in the front. And that's exactly what this p equal to 3 Lagrangian tells us, and they finished, where we see many more stars there. So let me just then skip the rest of this. We can understand it very nicely in Newtonian and Milgronian gravitation. And I just want to therefore put up the conclusions. So essentially, we now have that MOND correctly describes all observed dynamical phenomena on the scale of open star clusters, galaxies, gigapascal part motions. I didn't cover that aspect. MOND counts as one of the most successful theories ever discovered, and this is not that I like MOND, but that's just a fact of the history of how the topic developed. The growing cosmological structure formation simulations does appear very promising, and it will explain some of these. And which initial conditions to use. Important is that, this is an important point, the single power spectrum is minus, I know. The power spectrum is considered, everybody tells me in the community that any theory I invent of cosmology must be consistent with this power spectrum. Okay, otherwise they don't take any theory. So MOND is not taken seriously because it cannot account for this. And so one thing what we have to remember, we'll feel the questions. So if this is the CMB, no structure, completely flat at the redshift of 1100, and the photons propagate through the universe to us as the universe is expanding, what happens is that they are deflected through weak lensing. So the photon propagates and then there's a gravitational potential and it's deflected. So the photon is deflected, then it changes its energy through scattering of electrons on the way, and it changes energy because as the photon enters a potential well which is developing, it exits with a different energy. So these are well-known effects. And they are foreground, so new photons appear because stars begin to shine. And then we observe the CMB today on the sky. So when we observe the CMB, we have to subtract all these effects to get the actual one over there. But all these effects depend on the theory you're using to quantify these effects, which means that to do this step, we have to account for these, and so the corrections are theory specific. Which means that this is wrong. The initial conditions at z equal to 1100 must be recalculated for every cosmological model separately. We do not know what the power spectrum is at the redshift 1100. We only know it if we assume the LCDM model. For any other model, we do not know what it is, because that's not being calculated. And so that is also now the end.
Okay. We have time for one or two quick questions, comments from the audience. I have a quick comment. A while ago you said that MOND correctly explains all phenomena at galaxy clusters and galaxy scales. I think that has to be moderated somewhat to take into account that MOND does not account for things like gravitational lensing around galaxies, because it is not a covariant theory. No? And it shows that even though it explains much better a large number of phenomena, there are phenomena in the standard scenario which are explained better, which are explained well in the standard scenario, and which cannot be explained with MOND as such.
Well, the statement would be that a relativistic version of MOND will, of course, have light.
Of course.
These have been formulated.
Yes.
So in that sense, the field equation, relativistic field equation, which leads to MOND, also will account for the.
Well, there are actually many options, many GR equations that have a MOND limit, and that have to satisfy things like lensing, etc.
Well, maybe there are two, right?
Well, there are more. Sergio has a few. There are a few of our theories in Italy. Salvatore Caposiello has worked on a number of them as well. Okay, well, in that case, thank the speaker again for a very interesting talk.
Okay, yeah, so hello, my name is Nick. I'm a PhD student here in Prague at the Astronomical Institute of Czech University. And just before I go to my topic, I would like to mention that I'm supported by two grants. The GAP one, which is a grant target for PhD students, especially for travel money, and the action one, which is a collaboration between Austria and Czech Republic. Having heard all the theoretical background from Pavel about MOND, the first attempt is to do cosmology with Milgramian dynamics. So the motivation for that, to do cosmology with MOND, the first attempt, the first answer was the neutrino, the NUHDM model, and how was that motivated is actually given by a study from Sanders 25 years ago, where he was studying gas-rich galaxy clusters, and what he found was that when he was plotting the observed mass with respect to the Newtonian dynamical mass, he found this discrepancy or mismatch between the expectation from the theory and the observations. So when he did the same thing, but with the Mondial prediction, you can see that the discrepancy was decreased, but there was still a mismatch there. So how can you bridge that? How can one do that? Because even MOND cannot perfectly fix the problem. He introduced the idea of a neutrino component that this hot or warm dark matter component clusters only on the galaxy cluster scale. So it doesn't cluster where we have galaxies, but it's a bit zoom out. So this is the basic idea of what we call the NUHDM cosmological model, which unites the MOND phenomenology, because it provides the successes on the galaxy scales with the Bionic-Fisher relation, the Faber-Jackson relation, and the ROR. And what it is added is this slight contribution of there's no cold dark matter, but there's the stellar neutrino, which has a better motivation due to this hypothetical production through oscillations from the standard model of particle physics. And so in our model, the neutrino has a mass of 11 eV, and due to its free-streaming length, it doesn't affect the galaxies, so at the lower scales, but it doesn't affect the CMB either on the very high scales. So as Pavel mentioned before, a little bit about the history of the model, how is that constructed, is that as I said before, Sanders found this discrepancy, and then he postulated, there might be something more motivated by particle physics, and there might be neutrinos actually clustering on the galaxy clusters. And he had postulated that there's a sterile one. Actually, the first idea was a much more massive, like 300 eV. And then Angus took the idea of the certain point, and given, 20 years ago, 15 years ago, given the WMAP data, which, as Pavel said, should be the first, the initial conditions that all the cosmological models should apply if they assume, of course, a Big Bang or inflation, because that's also a conservative idea, as one can say. Then there was another study by Katz, who has done some n-body simulations, but with no gas. And what we did actually last year with Niels and the people in Bonn is we had done the hydrodynamical version of Angus and Katz, and using the Planck data. And my last submitted paper, actually 1 week ago, as I will elaborate more in the next slides. So, as you see, actually in these plots, that's the cosmological parameters. And one important thing to note is that the lambda CDM, maybe this is a little bit small, but you see that the first one is the cold dark matter contribution. In our model, this is 0, and all this contribution from the CDM goes to the omega nu. So this is this one. So this is substituted to the neutrino. And the rest of the parameters, they stay the same. And actually, this is a pretty good fit to the data. Let's elaborate a little bit more. So what's the again, the initial conditions for doing the simulation in order to test if the model has realistic results. These are the cosmological parameters, the omega baryon, so the baryonic contributions, all the stars, all the matter that we see, that we observe in the universe, it stays the same between these models. And as I said before, there's no CDM, but there is the neutrino. Of course, the dark energy contribution stays the same, but we have used the Planck value for the H0, just because on the simulations in our codes, we have used the same metric to calculate distances and what we call the background evolution of the model. So it's an FLRW actually, what we calculate. VNS is the spectral index, and that refers to the inflation. So again, I said the LCDM has a Big Bang and a cosmological inflation too. And this is the optical depth of the linearization. So as we see, this is the plot actually showing that our initial conditions for the simulations are quite realistic. The blue line is actually the blank data, right, what we call the LCDM, and the red line is our best fit to these parameters. As you see, the fit is good, but it is not the optimal one, and that's the motivation for my last submitted paper. But before going into that, just to because we had the opportunity to present the results that we sent. So what's coming out of the hydrodynamical simulations? So you see at the right panel on the above, you have the baryonic distribution, and the lower line you have the neutrinos. At the left panel you have the 200 megaparsec box, while at the right one, both of them, you have the bigger box of 400 megaparsec. So you see that you have a nice distribution like the one of what we observe. You have the cosmological voids, you have anisotropies, you have the filaments forming and galaxies forming onto them. And then, for example, on the right side, you can see that you're reaching the convergence, so you have homogeneity and anisotropy, approximately 250 megaparsec in a lambda CDM scenario. And then on the lower line, you can see that the neutrinos follow exactly the baryons. So you don't find neutrino distributions isolated on the void. So they do what the baryons do. But it was some promising result, but there was, in order to, we analyzed that further, and this is the galaxy cluster mass function. The first conclusion was that maybe the distribution was realistic enough, but the structure formation, so all the galaxies and the galaxy clusters, they appear very late. Very late, it means with respect, for example, to the latest JWST observations, which is able to see structures at redshift 10. This is what it means very late. And then from the galaxy stellar mass function, one can see that we have some giants over there which are not observed. So you have 10 to the 16 solar masses of galaxy clusters that simply we don't see them in observations. Again now, this was a little bit what we have done due to the hydrodynamics. As I said before, the motivation was the initial conditions, and I applied for a grant, which is a collaboration with what's called the Action Grant, and it's a collaboration between Czech Republic and Austria, only between these two bordering countries. And I got this grant, and I stayed in Innsbruck for 3 months. And what we did, due to this fit that we have done in the first paper, is that okay, let's see how probable these two models are with respect to the latest Planck data now. And so we calculate the likelihood the first test was to calculate the likelihood of these two models, and one can see, well, the lower the likelihood, the more confident the model is. And as one can see, the lambda CDM is much more probable with respect to our LCDM. One can see that the fit was good, but it wasn't ideal. So this was the first test, and now the second step was how to optimize these parameters. So as one knows, ΛCDM has, I think, 6 parameters, 3 parameters, and this is what we have done. So we have done some MCMC simulations. It's just a matter of fact, we use the Cosmos package, and yeah, this is the MCMC sampler. And we let the variables vary between some constraints. The first one is the energy density of the neutrinos. The second one is, of course, the Hubble parameter, because this is what drives the first peak of the CMB. The reionization depth, which is also a free parameter for ΛCDM. The NS is the spectral index for the inflation. AS is also related to the neutrino contribution. And then, of course, the last one is related to, this is the A-blank parameter. This is what Pavel was saying at the last point. It is related to how the signal from Prague was extracted. So it is related with the beam of this telescope, the telescope. And then, as I said before, the omega barium stayed fixed, and the contact matter was simply negligible. So we reached the convergence plot, and we managed to get into much more confidence region, but the results were really striking. So with respect, of course, given the planned data, we reached a very low H0, which is, to my knowledge, one of the first assumptions that H0 was the original value, like maybe 50 years ago. And then the reionization depth was decreased, the spectral limit was decreased, and the omega matter became significant. So this means in this model, the universe is much more matter dominated, which of course gives a hint that, that the simulations that will come will have a completely different distribution. This is a much heavier universe, much more matter dominated universe, and much older universe. So given that, this is the optimized seed. That's the major result of the paper. As one can see on the blue points, you have the blank data, the latest one, and then the red line was the line that I showed before, the Wittenberg et al. Paper, that we did it with CAMP. CAMP is a Boltzmann code, just by the way. It solves the Boltzmann equation in even the relativistic limit. And then the green line, just giving you a green light for simulation, is optimally fit all of the data except the last one. This is the last peak. Here there is a slight mismatch over here, which is puzzling, but it's also due to the CMB lensing, which is not actually yet developed in the MOND case. So that gives a hint that the theory needs further development. But since we nailed the CMB, then we looked at the matter power spectrum. Again, the blue line is coming from the standard cosmological scenario. That's contact matter dominated. The red one was the one, our old NUHDM. And then, of course, the line, these two lines drop significantly, and they're very low, such low values, just because neutrinos don't have any power at these scales. So galaxies, let's say, they're over here, so they do not cluster. That's why you don't have any power from neutrinos over there. I'm just plotting that in at redshift 199, because this is the initial conditions for the simulations. But now, more importantly, the transfer function, which is of course related to the power spectrum. Again, this is the cold dark matter contribution. So this is the CDM contribution, the blue one. And since it is collisionless, you have a lot of power at the large scales. Well, at the small scales, at big K. But now you have an excess of power between the green line and the red one, which is important because the results that we had from the simulations give, as we said, big galaxy clusters, too many big galaxy clusters and too many small galaxy clusters. So this excess of power and give us the motivation to do extra hydrodynamical simulation with the optimized parameters now. And then what we the last one, okay. So the last step of this study was to evaluate the cosmological distances with respect to the three models. The black points, they're coming from Pantheon and Sue's data. This is the standard distance modulus plot. And as one can see, well, the ΛCDM and the LCDM, they're actually indistinguishable. We don't see the blue line, it's below the red one. But the green one actually, well, it's very similar behavior, but especially at the higher edges, the earlier time, it's actually even better fitting the data. So a little bit more on the cosmological distances. These are the DHDM DV. These are just a handbook in order to calculate those. Well, we can talk about that. That's the south horizon, the dark epoch. So just a little bit before I go into our result, I want to show that in standard ΛCDM papers, they plot the distances, as one can see at the y-axis and on the x-axis you have the redshift. But they have some arbitrary scaling of square root of z. We see that, for example, in the Wood paper in years ago. And then, which is, the authors actually say that the scaling is completely arbitrary, just to illustrate, or trying to illustrate the match with the data. But in similar studies, they have a completely different scaling. So the scale now completely changes in different power. So of course, well, if you look for to optimal fit anything, you can do that. Well, I haven't. So I just plotted the same parameter, but with no scaling. Just one point that Pavel is always emphasizing to me is that the data, they're all of them model dependent. So if one wants to evaluate the data, first one needs to assume the model. So it's a circular argument, but in any case, there's the data. Our new model is not fitting very well, all of them, but of course it's also the scaling that one can apply. But also when you do that without scaling, one can see that even the ΛCDM cosmological distances, they are not fitting the data that well. So yeah, so that's it. I have just the conclusions. We managed to optimally fit the Planck data. We managed to make the model much more confident with respect to them, but we ended up in a very high matter-dominated universe, which some of the people of the ΛCDM scenario can say, oh, well, we have to exclude that because omega matter is 0.3. But yeah, this, as we said before, this is model dependent. So in order to evaluate more the optimized parameters, we have to do again hydrodynamical simulations. Just one thing also to note is that people have done the same kind of approach, but with Newtonian gravity, and they obtain similar results. So when you do neutrino plus, so neutrino instead of cold dark matter, but Newtonian gravity, they have also too many big clusters and too many small clusters, less massive, I mean. So this might lead the problem to the metric, so not to the gravity, but actually the problem might be in the background evolution of the hydrodynamics. And yeah, so because of our calculation to find a very well, since the H0 is very low and the age of the universe is it's much older, there is a hint from Simati and Moresco that they find like very old stars, older than the age of the universe, of the ΛCDM universe if you want. And just the last note is that due to the high omega matter, I have applied for some supercomputer time in Strava in order to do the actual simulations. Yeah, thank you.
Super. We have time for a few questions.
Could you compare the omega matter numbers again, please?
So the omega matter for the optimized is this one, close to 0.5.
What is
This is the barium is 0.05.
So that remains the same.
Yeah, but it's the same. This is the standard LCDM.
Okay, so one has simply more hot dark matter.
Yeah, more neutrinos. Yeah, much more compared to the old LCDM. But the bariums are the same.
Okay.
And that you can't put more matter into baryons and less into the stellar neutrinos.
You can, but then you have to explain it with observations. Why do you vary the omega barium? Because there are constraints from the BBM, right? There are constraints on the omega barium through the Big Bang nucleosynthesis. You can let the variable vary.
One little bit.
You can, according to the same experiment, but yeah. So there are constraints. Yeah, but then again, these constraints are how they are modeled.
So I noticed that in the regime where the neutrinos were introduced to explain the clusters, but you're short of a high wave number power, right?
Say that again.
You introduced neutrinos to explain the clusters, and you got the clusters more or less right, even excessively right, perhaps.
Yes.
And but you're missing power at small scales.
No, I'm not missing power. The power should be decreasing at small scales because neutrino.
But
no.
Okay.
Yeah. So
But you cannot get. You just at the beginning you mentioned you don't have galaxies forming at redshifts above 4, no?
Yes. So yeah.
So you're missing power at small scales.
This is so I don't know if that depends on the power spectrum. So this is a tricky question. I mean, the structures they are forming very late, but again,
Particularly at small scales, you're missing power.
yes. But this might be a problem with the resolution.
Okay.
Yeah.
I think I know why you're missing power at small scales.
Well, one can't resolve little things which start forming early because the computers are not powerful enough.
So you think it's just a resolution issue?
What do you think?
No, I was discussing some other mechanisms for explaining for obtaining fluctuations in the
This is another.
in the baryonic
This is
regime.
another. Yeah.
We can talk about
We
it
can
later.
talk about it later. Yeah.
Okay, if there are no further questions, I think we thank the speaker again.
I was taken out about the problem which has been discussed in the morning here, and it is expansion of galaxies. When galaxies do expand or not, and we have expanded universe, how is it with galaxies? So, this very popular idea that that is presented in this famous textbook that galaxies do not expand. That we can imagine in the galaxies as pennies attached on balloon, and then when balloon is expanding, then pennies have the same size, and just distances between them are increased. And we can look at this idea in more detail. How it is calculated, how we know that galaxies do not expand. So this is standard idea of the structure of galaxy. We have some bulge disk, and when we consider the Kepler law, then we know that Newton's gravity must be balanced with centrifugal force, and then we obtain the rotation curve, which should decrease with the distance. It was discussed here several times, but what we observe is the flat rotation curve. So there's a clear discrepancy between standard Newton gravity and observations for galaxies. So this strange, of course. But this Newton gravity, in fact, is simplistic. It's simplified because we do not have galaxies in the static universe or galaxies with no other galaxies. And usually we consider galaxies as isolated objects. But galaxies exist in expanding universe. So there's also this expansion. So in fact, we have to also consider this expansion and how this expansion of the universe can affect galaxy dynamics. So under the general relativity framework, we have to combine two metrics. Metric for expanding universe, this is a Friedmann metric, standard Friedmann metric, and metric for local gravitational systems, and this is Schwarzschild metric. And we have, under the general relativity, we have to combine these two metrics. So it has been done, and it is the metric which combines both effects. And you see that if we really take into account gravitational field within an expanding universe, we get standard Newtonian law, but here is also some effect of the expansion. So this is a modified Newtonian dynamics. However, when we calculate how significant is this term, it is in fact negligible. So in fact, and these authors prove that this effect is negligible. So in fact, they say the Newtonian gravity is enough. Okay, if the Newtonian gravity is enough, and then the problem is that we did not solve, under general relativity, we did not solve the problem of flat rotation curves, because standard Keplerian curves decrease with the distance, and they are not flat. So this was the reason why dark matter was introduced as a very simple way how to solve the problem. So we have a big dark halo, and in this way we can fit with the three parameter, and we can fit rotation curves and the density, we get some very large density of halo, and then we can fit flat rotation curves. But this is not the only problem, because dark matter, as was here said, we have many observations that it does not work, that dark matter is not probably a good idea, and it is a really exotic, unphysical term, considered concept. But there we have also some other problems with galaxy dynamics. We have the so-called problem of winding problem in galaxies. We are not able to well model structure of spiral galaxies. And it is shown here that when galaxies rotate and we calculate the morphology of galaxies, we do not get spirals. We get something like this, and there will be no spirals. But there is some solution which is called density wave theory. When the spirals are assumed to be some standing waves, it's a little bit complicated theory, but in fact there are some models which show that we can get for rotating galaxy formation of some spirals. It is questioned if this theory really is possible or not, if it is realistic, and also if these spirals are stationary, but in some way there's some solution for this problem. But there's another big problem with galaxies, and this is that observations show that galaxies really expand. And this here you see two very nice plots from experiments with very huge number of galaxies, which show that size of galaxies increases at the same rate as the universe. So it's a striking coincidence that galaxies really expand according to the same law as according to the Hubble law. So as you can see, that we have really many striking phenomena which we are not able to properly to explain as regards the galaxy dynamics. There were some attempts how to explain this expansion, that there's a possible possibility that galaxies merge during the cosmic expansion, cosmic evolution. Some galaxies may merge, so they can expand. But when we calculate statistics about this merging is really very rare, so it cannot satisfactorily explain this expansion of galaxies. So there's a big controversy in this hypothesis. And there's another problem. If we have two galaxies and they are merging, then their structure, of course, is disturbed. So we cannot observe expansion of spiral galaxies, because spiral galaxies, the structure is not disturbed. Okay, so we have many problems with galaxy dynamics, and we have to find some solution how to solve it. So the one possibility is that the Friedman metric, which is used, as I mentioned, it is combined with the Schwarzschild metric, that the Friedman metric will be substituted by the so-called conformal metric. Conformal metric is different in this term. Here we have a scale of factor, scaling function. So scaling function describes the expansion, and this is not only at the spatial metric, but here it is also at the time term. And if we use this conformal metric, we get another fundamental cosmological equation. This equation is called known for the standard LCDM model. This is for the conformal model. And when we use this conformal metric, we do not need to introduce dark energy, and still we are able to fit supernova data. So this conformal metric is really preferred over the standard metric, where we have to introduce a dark energy. Here we have no new parameter, no free parameter, and still we are able to to fit supernova needle. So it looks that really this conformal metric might work and might be a very good approximation for some cosmological models. There's are some other reasons why the conformal metric is important and it can work, but I will skip it. I just want to show that if we use this conformal metric and combine with the Schwarzschild solution, we get another system of equations for gravitational orbits in the expanding universe. And this is the original solution by these two authors. And if we use now this conformal metric, we get quite different equations. And these equations, when we model dynamics of, for example, spirals, they predict flat rotation curves. So if we combine conformal metric with Schwarzschild solution, we obtain solution for galaxy dynamics when the rotation curves are flat. So summarizing my short talk, I would like to draw your attention to some modification of Friedmann metric. That Friedmann metric, probably not general relativity equations are incorrect. Also to say, if we are not able to model galaxy dynamics, it means that the general relativity is incorrect. No, the Friedmann metric is probably incorrect. If we use another metric under the general relativity, we can obtain, we can find fit with observations. For example, we can explain time dilation during the cosmic evolution. It is here. You see observations of supernovae dilation. We know that we observe different duration of supernovae during the evolution, and it can be explained by time dilation. Cosmological redshift is also a problem of time dilation, and we can explain successfully supernovae dimming. We do not need dark energy. And we are able to really explain also the flat rotation curve. So, in fact, very simple change of the metric can help us to solve many big difficulties and puzzles which we have in cosmology. So dark matter is not needed. Also, no dark matter, dark energy is not needed. If we use just small, we change a little bit this Friedmann method, and the general relativity is perfectly valid. And galaxies, and we are able to predict expansion of galaxies. But it's not only expansion of galaxies, also all systems. So even the solar system is must expand. So also all local gravitational systems should expand. So no new physics and no modification of general relativity is in fact necessary. Thank you for attention.
Okay. Right, so we have time for a few questions now. If there are any comments or questions from the audience?
Maybe a question. Are you suggesting the universe is not expanding, but there's time dilation, or how one is understanding? Because a redshift comes from time dilation, does it?
Redshift is caused by time dilation. Usually, we explain cosmological redshift by expansion of the universe. So we say universe is expanding, wavelength of light is prolonged. But in fact, that's not fully correct, because the frequency of light is changing. If frequency is changing, that's the problem of time. So not only the scale should change, but also time rate must change during the cosmic evolution. So we have to introduce also this expansion function, the scale factor, not only in spatial metric, but also in this time term of the metric tensor.
But that means your universe will be static, but it's evolving through.
The universe is evolving.
But how? It's not expanding, right?
It's expanding. It's expanding. It's expanding, but also not only scale distances are changed, but also time rate is changed. So the standard Friedmann metric assumes that distances are increasing, but time rate is the same. It's constant. It does not change. In this model, also the time rate is changing.
But then the redshift is composed of the frequency change due to expansion and due to the apparent velocity of the receding galaxies, or not. So where does the redshift come from? It's just time dilation in your case. So the one is expanding. The galaxies at a large distance are moving faster from us because of this expansion.
That's how
And so you have a double Doppler shift, like you have a Doppler shift plus the time dilation.
Yeah, something like that.
But then the redshift distance ratios are completely different, right? Because the redshift you see from time dilation plus Doppler shift, but the distance is then much smaller, right? So everything is much closer. Because you have the Doppler shift, plus you've got the time dilation redshift.
Yeah, time dilation should be the...
So you have a much bigger redshift then, at a given distance, of a light distance.
I'm not sure. I have to think about it. Definitely, this time dilation is really very important for this physics, and it changes. It changes completely equations for gravitational orbits.
Yes, I only would like to support this theoretical result by, say, real-life observations, because Christine Martinez-Lombia published in Monthly Notices approximately 5 years ago expansion rate of Milky Way. It is 1 kilometer per second, diameter 1 kilometer per second. And if you recalculate it, you get almost exactly Hubble constant, which is maybe coincidence, but this supports this result.
I would like to comment on the data you show to back up this idea of the expanding of galaxies. They do not measure the expansion of galaxies. Okay, strictly speaking, to measure the expansion of galaxies, you have to take a picture of a galaxy at different redshifts and show it's bigger. What they do is take pictures of galaxies at different redshifts, not the same galaxy. So it doesn't actually prove the galaxies are expanding. It proves that the mean size of galaxies has grown. Okay, galaxies were smaller at higher redshift than they are now. The plot exactly that one there. No, so it is not the change in the size of a single of the same galaxy. It is the
It's not, of course, it's
of
not
course
the
not.
change of the
Then it does not prove
but we have some
a population
set of
or
galaxies
exactly.
in the past, set of galaxies at the present, and we see
They are larger now.
they are larger, and they are larger according to the redshift.
But the standard interpretation, and it is consistent with star formation histories, etc., etc. By the way, this is the size, it's the effective radius of the light, okay? You have to, we know that when the stellar disk ends, we have a huge gaseous disk around. And we know that the gas is turning into stars. So the standard interpretation for this is that as star formation proceeds, the size of the stellar disk increases. No? To prove that the galaxies are getting larger, I think you will have to include the sizes of the gaseous disks. Okay?
Well, in the sense what Michal just said, apparently there is a paper measuring the expansion of the nuclear. How did they measure those? Do you know?
I don't know, but I have the exact quotation in monthly notices.
It would be interesting to take a look at that one.
Yeah.
Because
Yeah.
this refers exclusively to the stellar component. Okay?
Yeah.
And the stellar component naturally grows because the gas is gradually turning into stars.
Yeah.
Okay? So even if the galaxies do not expand, the stellar disk necessarily grows.
But the fair-wise one.
Sorry?
To be fair, one has to say that the elliptical galaxies, which are not forming stars, also grow.
For example, yeah. What happened?
But they grow. They actually.
But very little, not at the same rate.
Very similar, actually. It's quite remarkable.
Yeah, that's here.
Yeah. So this is I think it's a real issue.
Well, there is no reason why this effect
Would have to coincide with 1 plus x.
coincide with the
I know.
rate of the cosmic.
No,
And
I agree.
another reason is also that this theory is capable to describe these spirals.
Well,
That's and this is difficult. This is a very difficult task now for galaxy dynamics to explain these spirals.
yeah.
In fact, it is in these spirals are nothing more than from the gas from this bulge region. I didn't describe it in detail. So this doesn't. But yeah, we have some Vajra region, and from this Vajra region, material, when the galaxy expands, goes to some spiral region, and when the universe is expanding, the space is expanding, these spirals are detached from this inner region and form this nice spiral pattern. Yeah? So this spiral pattern is nothing, it is nice demonstration of the expansion of the universe, of the space. This detachment of spirals is an effect of
I think that if you look at the sizes of galaxies through measurements of a gas, you do not see any expansion. But leaving all this aside, I'm worried about the metric you propose. It's obviously it's a kind of Schwarzschild metric with a scale factor, right? With a temporal scale factor.
Yeah.
So then it is you throw away a Friedman metric, and hence this new metric is not isotropic or homogeneous. You have an R coordinate. Is there a center? I mean, a Schwarzschild metric, there is a center. There's a central point.
Well, could you show it? I mean, why is it not isotropic? And could you show
Because it's Schwarzschild plus a scale factor. So it has a point. Not all points are equal. Things depend on a radial distance from a certain point. No, the G00 and the GTT, the time component and the radial component, they all depend on a distance.
Yeah, right.
Schwarzschild metric, everything depends on the distance, how far you are from the center. No, in Friedman there is no dependence on position. All positions are equal.
in this conformal metric is the same.
No.
Could you show it maybe just to show?
The metric?
Yeah, the one you're proposing, it's Schwarzschild plus a scale. That one, there it is.
Yeah.
Okay.
So scale factor is at all.
Of course, I know,
With terms.
but all these components, for example, the G00 doesn't have a T. I mean, the next one up, the second component that's there on the second column has a radial coordinate, has an R.
Yeah.
What does that mean? In Friedman, you don't have an R.
In
No?
Friedman?
Yes.
This is in Friedman.
No, I know.
This black is Friedman, and the conformal is just that V inside is AP. This is expansion. This is because of expansion. Yeah, this is expansion of the universe, and it is combined with the Schwarzschild metric.
Yeah.
You have to combine both because you have a gravitational system in the expanding universe. So the background is expanding.
So
you
this-
have to
this-
take into account gravity also of the background.
Yeah. So it's really it's a bit like it's a combination of Schwarzschild and Friedman somehow.
Exactly.
It's a solution. It's an exact solution of Einstein equation.
Solution of this.
But what's the meaning of R? You don't have any R's in Friedman.
R.
Yes, R. In Schwarzschild, R is the distance to the center.
Of course, it is a combination of Schwarzschild
Okay,
and
okay.
Friedman.
So
Because
R.
we solve galaxy dynamics. So
Okay.
we solve.
So R is the distance to the center.
Gravitational system.
Okay, R is the distance to the center of the galaxy. Is that correct? You have an R there.
Yeah, it will be. It will be.
It's the distance to the center of the galaxy. Is that correct?
Yeah.
I see.
Yeah.
Okay.
Yeah.
Okay. Yeah. Okay. So it's a proposal to include the expansion
Even into the
into the galaxy or into the central system. Let's say.
and there's another consequence that also solar system should all orbital local gravitational systems should expand. So
Why don't you have an R in the first component then? The alpha has an R.
It's an alpha, isn't it?
Yeah. The alpha includes the R.
But this means that the solar system should also have a flat rotation group, should it not? Should all systems have flat rotation?
So all systems should expand. It's not only for galaxies. All systems should expand because of influence of this background gravity of the universe, which is different.
Then why don't we see a flat rotation curve in the solar system?
The rotation curve of the solar system
Why is it not flat?
Because there is 99% of the solar system is concentrated in one point,
Yeah.
which is the sun.
But we have
But
experimental,
the same happens in the galaxy.
evidence that the solar system is expanding.
Not
No, I'm not talking about-
99% in the center. Well, it is. There is
Yes.
10%.
No, not 10%.
Hello.
No. The disk is exponential. The disk surface the mass distribution of the disk decreases exponentially. So very quickly you have all the masses converge. That's why you expect to see the Keplerian decline. If you expect to see the Keplerian decline in the galaxies, you need to have dark matter to explain the flat rotation curves. If this metric explains the flat rotation curve of the galaxies without needing the dark matter, it should also lead to a flat rotation curve in the sun.
No, that's not that easy because there's a different size and you have different periods of orbiting bodies. Here in the galaxies, the period is millions of years. Here it is very, very fast. So this is not comparable. So this flat rotation curve cannot be in such small system. So, but these small systems are expanding.
Where is this change of scale?
The scale, in fact, it is in some way similar to MOND. That there's some transition between local systems and global systems. We know that for some distance we have one gravitational acceleration, and for larger distances we have another. So in some It is similar in this aspect a little more.
How would this work in a galaxy like DDO 210, which is it's half a kiloparsec big, but it's dominated by dark matter everywhere, even at the center, and it's rotating with 15 kilometers per second. Would that work then? There?
I'm not sure. I cannot now to verify.
It's something one would have to check. And also, the rotation of a galaxy takes 200 million years, maybe a billion years, and that is still fast compared to the age of the universe, right? So
it's but the age of galaxies is billions of years. So during this, it is increasing. So it is not only one rotation, but it is during the evolution of the whole galaxy from the beginning to the end.
the problem I see is that you were arguing that the solar system you expect Keplerian fall off because the dynamical time is much shorter than the age of the universe, right? The age of the sun.
And that's the case for many galaxies as well.
Yeah, because the dynamical times of galaxies are also much shorter than the ages, right?
Certainly dwarf spheroidals.
Especially dwarfs.
You can have velocity dispersions as low as 5 or 3 kilometers a second, and they are completely dark matter dominated. So you need to explain dark matter phenomena at scales where the sound crossing time is much smaller than smaller than the age of the universe.
I focused on standard spiral galaxies.
Yeah.
And showed on modeling that it works nicely.
But that's a problem with many of these suggestions, that usually one doesn't consider the full scale of all the evidence, of all the constraints which we have. That's something one really has to do. And I think this would be very serious, but one has to look at the other systems, dwarf galaxies, expanded solar system versus normal galaxies. So
yeah, but definitely we have many observations which show that really gravitational systems are expanding, and this approach nicely explains this event.
Okay. Well, we've run a little over time. We should be having a conference photo about now.
So, in my talk, I will discuss the existence and properties of black holes. And the topic of black holes is, of course, quite attractive, because black holes are simply very specific, very exotic properties, because of extreme distortion of space-time in their vicinity. And I will review the black hole research and point out some misunderstandings and errors in black hole physics. So, only very shortly, how do we define black holes? So, we assume that black holes are very extremely massive objects with strong gravity, probably formed by gravitational collapse of stars. And the gravity is so strong that it prevents escaping any object from the black hole interior. And it's not only massive particles, but even waves and photons, light. Light cannot. This is standard idea about black holes, that from interior of black holes nothing can escape, even waves of electromagnetic waves and photons. It is assumed that from outer surface of black holes there can be some radiation emitted, and this radiation is called Hawking radiation. and mathematical description of the process possible under general relativity. Okay, so shortly about the history. Einstein developed his equations in the 1950s, and just after this development, Schwarzschild found solution of Einstein's equations for a point mass. And this solution is very, very interesting and points to some very strange properties. He found that if we have point mass in the center here of coordinates, then there should be some sphere around this point, called event horizon. This sphere has a radius called Schwarzschild radius, and this sphere has very special properties. Spatial metric is diverging on this sphere, and time rate slows down to 0. Of course, there were many other researchers working in the black hole physics. Eddington, for example, found another solution. I will speak about it later. And different than from the Schwarzschild solution, and he tried to interpret physically what does it mean, this event horizon. We speak about event horizon. Also other physicists like Oppenheimer and Snyder, they modeled black hole formation. Wittgenstein, Kruskal, they analyzed the Schwarzschild surface as this event horizon. Kerr found solution for dating black holes and so on and so on. So, of course, since black holes are really associated with strange behavior, they were subject to many controversies and misunderstandings. Even the existence of black holes was disputed by many physicists, including reputed cosmologists and relativists. For example, Albert Einstein, for many years, did not consider the Schwarzschild solution as a physical solution. He considered that it must be just mathematical concept, which cannot be realized in nature. And there are also other critics like Fred Hoyle, Wolfgang Pauli, and Martin López-Corredoira, and their objections against black holes were of different kind. So, of course, when Schwarzschild calculated his famous solution, he assumed for mathematical simplification point mass with infinite mass density. There's a question, this is not physically realized, so there's a question if the solution of such a mathematical object can say something about gravitational field of real physical objects. And we do not have knowledge about behavior of matter under very extreme conditions. Also, all information about matter that falls into the interior of black holes seems to be lost forever. That's strange. That's something not very clear why, and if consequences, we don't know all of these consequences about this. Also, there were some problems, explanation how black holes can be formed, and if they are stable objects, physical. And finally, many problems were discussed associated with this event horizon, which is, as I said, a sphere with very specific properties. So let's a little bit discuss in detail the Schwarzschild solution. So the Schwarzschild tried to calculate the distortion of the space-time due to presence of the point mass. That doesn't mean he calculated metric tensor of the space-time. The metric tensor is this GKL, and he assumed that it is spherically symmetric because it's a point mass. This form of the GKL was introduced into Einstein equations, and he found the solution. The solution looks like this. So this ds means this is element of distance in the space-time, and this terms describe metric tensor. Here is distance r, theta, phi, angles, and in the solution you see this rs. This is 2gm over c squared, and this is the famous Schwarzschild radius. And why this solution is so interesting? Because if r goes to rs here, this term is 1, we have 1 minus 1, it is 0. So here, in time term, goes to 0. And here we get this 2 minus 1, so it is infinite. So we speak about very specific properties of this event horizon, that GTT goes to 0, time rate, it is interpreted the time rate goes to 0, the time is stopped at the event horizon, and spatial metric is in group diverges. Okay, so in this way, Schwarzschild found the solution. We can say, okay, the problem is resolved, and this is the standard version you can find in most of cosmological and robotics textbooks. But in fact, that's not fully correct, because there are some other solutions of the same problem, and they have quite different properties. There is a solution which is not very known by Marcel Brillen, which looks very differently from the Schwarzschild solution. You see again, this is a time term of the metric tensor, radial term, and here for angles. And what we see? Again, here is Schwarzschild radius, but if r goes to rs, we get 1 plus 1. There is no 0, and then here is no singularity. So this is very strange, it's a big difficulty. So which solution is correct one? Schwarzschild solution or this one? This solution also satisfies Einstein equations. That's not the end of the story. There are other solutions. For example, Eddington found solution. You see different forms of the metric tensor. This solution contains event horizon. There is an event horizon, but not at the Schwarzschild radius, but at 1/4 of the Schwarzschild radius. And there is no singularity at the Schwarzschild radius or at this radius at the event horizon. There is only singularity at r equals 0. So this is a big mess about the physics of black holes and what we have to believe, which solution is the correct one. Later, there were found some other solutions. We speak about harmonic coordinates. This, for example, in Weinberg's textbook, this solution contains event horizon and half path of the Schwarzschild radius, and it is singular also at this half path, one half of the Schwarzschild radius. And finally, this Stephen Crowthers, Australian physicist, found that, in fact, there's an infinite number of solutions which satisfy Einstein equations and are spherically symmetric. So we do not have just one solution structure. There's infinite number, and all these solutions look differently. So this is a really big difficulty how to work with this because does it mean that general relativity is a theory which yields some unique solution, an ambiguous solution? Any useful theory should yield for some specific physical problem one physical solution, not infinite number of solutions, otherwise it is not useful. So there are many open questions, and it initiated debate, long time debates among relativistic community about uniqueness of the general relativity, about how to manage this infinite or many different solutions of the same problem. And if we use exclusively Schwarzschild solutions, why? What are the reasons for using Schwarzschild? Because he was the first? That's not a very good physical reason. Okay, so of course then there are questions if these singularities which are associated with Schwarzschild solutions, if they are really physical or just some artifacts of used coordinates. Okay, so the community debated about this problem for a long time, and after that it seems that it arrived at some common solution, and the solution is as follows. Okay, the Einstein equations are coordinate invariant. It should work for any choice of coordinates. That's the basic principle of general, not only equations of general relativity. Well, any physical theory should be invariant to choice of coordinates. So it means that we can use different coordinates to solve the same problem, and of course, because we use different coordinates, the solutions will be different. So these differences are apparent. They are just mathematical. They are not physical. They are just apparent. Okay, at the first sight, it looks like it could work, but still, and it was pointed out by Fromholz and his colleagues. But for theoreticians, maybe it is satisfactory explanation, but for experimental physicists, we should know, okay, so which solution I have measurement, which solution I should confront with my measurements. Yeah. So I have to use some coordinate system. Does not, coordinates matter, coordinates really matter. It is stupid to say that coordinates does not matter. Okay, so let's a little bit speak about this point in more detail. So let's have two solutions: Schwarzschild solution, Brillouin solution. Schwarzschild solution has this event horizon and singularity. Brillouin solution has no horizon and no singularity. Both use coordinates like distance, angles. Of course, they are different. This distance is different than this distance. They can be recalculated, but to be correct, we should say, okay, this is R prime, this is R double primes, for example. They are different. These are parameters. Yeah? They are not exactly the same. They do not have exactly the same meaning. So, which one is the reference one? Why we use the Schwarzschild solution? Why we do not use this one? Of course, if we use this as primary, we can find some transformation of coordinates, and we will obtain this one. But the same works vice versa. We can use this as primary and we will derive this one. So how to resolve this problem? The problem can be resolved when we understand concept, the properties of curvilinear coordinates. In contrast to Cartesian coordinates, there we have just one frame, one coordinate system, and one base, one system of basis vectors. Here we have two different bases, vector bases, contravariant and covariant. For each curvilinear system, we have two coordinate bases, and these vectors, basis vectors, are non-unit. Cartesian coordinates, we have unit basis vectors. Here are non-unit. So we can decompose vector. This is physical quantity. We can decompose vector into in the covariant basis vectors. Then we here should use a contravariant component. Or if we decompose into contravariant, we here should use covariant. You see that there is always the sum, is a scalar product of covariant and contravariant quantities, upper and lower indices. They differentiate between covariant and contravariant quantities. And the invariant, physically invariant, coordinate invariant quantity is always sum of these upper and lower indices. This is the reason why ds, is the element of distance in space-time, is invariant, because it is calculated as a sum of covariant and contravariant quantities. But covariant quantity is not in coordinate invariant. It depends on coordinates, on choice of coordinates. So it is usually solved in the way that we have to normalize these base vectors. I said that base vectors are not unit. So we have to normalize them to be unit. If we normalize them, then the components will be really physical. And this normalization is looks like this. So we have to multiply it by some scalar factor, by some factor there. And we get in this way, we evaluate these components in physical system, and we get physical or proper components. So for people who are familiar with Cartesian coordinates, it looks like it is trivial. But still, it is quite surprising. The relativistic community mostly ignores this problem. So let's go back and let's look now at these two solutions, which are different, and we can arise some confusions which one is correct. There is no problem, because this is ds, this is this one, this is metric tensor. Metric tensor is covariant, so this is covariant metric tensor, this is also covariant metric tensor. They are not invariant. So if we use some coordinates, we will get different metric tensor, because it is not invariant quantity. It is not physical quantity. So in fact, there is no problem and no discrepancy that we have two different forms of the solution, because this GKL depends on coordinates. Okay, but we try, as from Waltz emphasized, we try to find a physical solution. So this is not a physical solution. This is dependent on coordinates. We should find a physical solution. And how to do that? That's not complicated. In fact, it's trivial. We use equation of geodesics. This is very simple. ds must be 0. Let's calculate a problem of determine speed of light, proper speed of light, at some distance from this black hole, from some massive body. as a function of proper distance. So we use the geodesics equation. This is 0. We will calculate the radial speed of light. So this theta phi is on 0. We get that this is 0. We can calculate contravariant velocity. This contravariant velocity should be recalculated to physical velocity by multiplying by this factor. We can calculate proper distance from this coordinate distance. We get proper speed of light, we get proper distance. So we are able to calculate proper physical quantities from the Schwarzschild solution. No, this is not Schwarzschild, it was recalculated. And this is the solution. You can see this is proper distance as a function of coordinate distance. Here, the coordinate distance is normalized to Schwarzschild's radius. So we see that for distance, coordinate distance less than Schwarzschild radius, proper distance has no meaning. So for R, if we speak about interior of black hole, there is no physics. This mathematical construct, there is no proper distance. The proper distance is not defined. Proper distance is defined just for R larger, equal or larger than Schwarzschild radius. Okay, so let's do the same for the Bramall, for this brilliance solution. Again, we can use these coordinates, calculate physical quantities. And now the key is, okay, so we used Schwarzschild coordinates, we calculated physical quantities. We used another coordinate system, brilliant, calculate physical quantities. If general relativity is unit theory, then these two physical solutions should be the same. And now this exciting moment of my talk, we compare these both solutions, and they are the same. Here I show two plots, but this is in fact the same plot: log scale and linear scale. And this is the proper speed of light as a function of proper distance. And both solutions yield the same physical relation. So it means that the relativity community was correct. Coordinate systems, we do not bother about coordinates. We can calculate we can use any coordinate system. But we have to recalculate the solution to physical quantities. And if we do that, we can use any of coordinate system and we get the same solution. And how this solution looks like, you see that the speed of light at the mass point is 0. And then it rapidly increases to some value. This is normalized, it is the value of the speed of light in the vacuum without gravity. You can say, okay, it looks strange because proper speed of light in general relativity is usually assumed that it's constant. And here it is varying. How is it possible? But we have to be very careful which speed of light we think. And because we are speaking about, because we usually speak about speed of light measured in some frame, and the frame is free falling. Free falling frame means that the body is in free fall and that it is subject of no force in free falling systems. And in free falling systems, due to Einstein equivalence principle, we can assume that this system is Lorentz frame and the speed of light does not affect by gravity because we do not perceive the gravity. But when I spoke about the speed of light, this is not this case, because I tried to find the speed of light at one point which is fixed with respect to the body generated this gravitational field. It is not free falling frame. The frame is not free falling. It is fixed. at some fixed distance, I try to find the speed of light. And of course, then the gravity is perceived, and speed of light must be different. It is not constant. And this is not only my deduction. It is emphasized also by Einstein in his famous book. He says that law of constancy cannot claim an unlimited validity. It is just if we disregard the influences of gravitational field. So it is in these free-falling frames, but not in non-inertial frames. So what is the results of these solutions? Okay, specific properties coordinate systems are really not important. All coordinate systems yield the same physical solution. But this physical solution is not the Schwarzschild solution. That's wrong. And speed of light is not constant, and it increases from 0 at the body and goes to C at the infinity. And the solution is regular at all distances. There is no event horizon. Event horizon was introduced by this coordinate, Schwarzschild coordinates. It is missing in the physical solution. So what is the big? This is surprising. It is a big error when in cosmological literature and the relativistic literature too, that the Schwarzschild manifold is identified with the physical solution, with the physical space. It is not physical space. These are just parameters. R in the Schwarzschild solution is not distance. It is a coordinate, it is a parameter, it is not physical distance. When we recalculate the Schwarzschild manifold to physical space, we get that this sphere contracts into one point. So this domain is unphysical. There's also consequences, very fundamental consequences. For example, we have some coordinates like Kruskal-Sekeres coordinates, which were established to understand and to study behavior of the solution inside the black hole. But inside the black hole, there is no black hole volume in physical space. This is just point. So this is artificial. This is just mathematical constant. There is no physics behind it. So there are fundamental consequences for black holes, of course, because black holes in this way, as we define that objects which capture photons, they do not exist. They cannot, and no object can capture photons. There is no physical surface around some massive bodies which can serve as event horizons. So Schwarzschild radius is no physical meaning. When we speak that sound, that equivalent radius of sound for the Schwarzschild black hole is 3 kilometers. That has no physical meaning. You can forget about it. So, and the speed of light, because we do not have objects with infinite mass density. All physical objects have some limited mass density. The speed of light near any object will not be 0, it will be positive. So from any object, photon can freely propagate into the space. That's not possible that it will be captured. So summarizing my talk, it's really surprising and unexpected, but the concept of black holes is false. Of course, massive and supermassive non-radiating objects exist. There is no problem. We have supermassive black body in the center of our galaxy. It is not black hole. That's incorrect terminology. It's a black body which radiates. Anybody radiates. It doesn't mean that it should radiate on an optical spectrum, because it is cold. It radiates on large wavelengths. Yeah? And we should be very careful about coordinates. Coordinates, space deformation, physical quantities manifolds, these mathematical objects, we have to be very, very careful about interpreting in physical terms. This is just mathematics. This is it is easily can happen that it has nothing to do with physical objects and with physics. No massive object can capture photons. And what is interesting that this is not only my result. There are some cosmologists and physicists who pointed to this problem, the black hole fallacy, but so far these people are ignored. And there's also interesting consequence. Wormholes are very much related to black holes. So also wormholes. There's an unphysical concept. Thank you.
So, questions? So thank you very much for this excellent work. So I have been studying Suntola model now currently. So I may have some very specific comments on a few of your slides. So could you put back to this Schwarzschild solution and the proper speed of light there? Because we might be into something. Yes. A little bit back still because it is the, yes, here. So because I can comment on Suntola model, the proper physical speed of light there, well, there's this square root minus there, yes, square root minus rs divided by r. Now you see that in rs there's 2 gn divided by c squared. That is the rs. So actually Suntola proposes that far from that critical radius, you actually can approximate that square root by exactly 1 minus gn per c squared. The 2 disappears when you take the square root away. And that actually is the it is the like exact approximation far from the Schwarzschild radius. So that is really interesting that far from Schwarzschild radius, where we usually do physics and where we usually see our experiments, for example, see the observations. Now the Suntola model actually agrees with this.
Oh.
Yes. And then you also see that if you take the square root away there, then the metric becomes more symmetric. Because you see now in the metric, there's on the top line, there's 1 minus rs divided by r. But if you take away the square root, it becomes to the second power. So everything becomes second power, and it's similar to the harmonic solution by Weinberg that you showed. So I'm very pleased to see this because I'm currently studying Suntola model, and this seems that there's now something in this. And I'm also interested if you are into these solutions. So is there something that now rules out Suntola model? So like, can that square root be approximated by taking it away and then taking the factor of 2 away? We might need later to do this in Blackboard, but this is really specific now. And I know that those are like exact solutions from Einstein field equations. So it then you usually don't do that kind of modifications. But Suntola has approached this problem from different direction, and he gets like really like specific ideas. Really.
Of course, it's very interesting.
Yes.
So many similarities.
Yes. It was really nice to see that harmonic solution by Weinberg. I haven't heard, because usually you heard just like Schwarzschild solution. You don't heard this.
From what I'm hearing, then this removes the idea of Hawking's radiation.
Oh, yeah, yeah. Hawking's radiation in this way is around. That's very unfortunate that the community simply identified this Schwarzschild radius with something real, and they did not aware about this recalculation that it is only mathematical. There are mathematical coordinates, and they should be careful about recalculating into physical coordinates. Yeah.
Any more questions? I have a comment. Mike Pavel will add to this. That there was, because of on the beginning of your talk, you were mentioning the history of the black holes. I think there was a person in Bonn that was considering that black holes was burning disks.
Yeah, that was Professor Quant.
Yeah, so there is like a point that you have maybe to add there, right?
Professor Wolfgang Quant. He also had the hypothesis that black holes were not black holes, but they were burning disks. So it's just that as the matter fell into this position of gravity, just from the pressure, it just went away. So that was from the idea of Wolfgang Quant, who also did not believe in black holes.
Yeah. Was in the 80s or something like that. Right?
Long ago, yeah.
Yeah. So, anything more to add?
Well, I should just maybe say that I also think that the physics ends at the Schwarzschild radius, that's what you're saying. The inside doesn't exist. But practically speaking, there is essentially a black hole, right? I mean, you will never get out.
You cannot get out because the black hole physically is point.
No, I mean,
There's no volume.
In the object which is there, which has obviously gravitating mass, if you go too close to it, there will be no chance to get out anymore.
No.
You need too much
If
energy.
there's it can escape from any photons, can escape from any
Well, they might escape, but they have so they're so gravitationally redshifted that basically nothing comes out.
That's wrong. That's wrong. There is no volume of black holes. So there is no interior of
Yeah,
black
there's
hole.
nothing inside.
There is
Come
nothing
out.
inside because this point physically it's a point.
The
It's not.
surface of that object, you cannot get away from that surface.
It has no surface. Surface is point.
The gravitational field is too strong. You will never get out.
This is the standard. Yeah. You hear repeat standard idea about black
So
hole.
you're saying you can build a rocket to get out of it, to get off that surface.
There is no surface. There is a just point.
Well, if
Event horizon is point. It is not surface.
But
There's zero radius.
however, they can accrete. If you throw something in, the mass increases.
If you throw to the point, you have 2 mass points. They can merge.
Exactly.
That's all. But it is not inside. There is a just point. You
But they
can.
do accrete. If you throw something in, the mass increases.
Mass increases. Yeah.
Exactly.
Mass increases.
Okay.
Yeah. Mass increases.
it will not get out.
It will stick together. It will stay there.
But you do not. You do not go through some surface.
No.
There is no surface.
Well, wait. I mean, if you you go in and out again.
Yeah. It depends on velocity for massive particles and for light.
You're saying
Light
that-
can escape from anybody.
So particle falls in, becomes highly accelerated to that, whatever you call it, and then it flies out again.
It goes very nearly to the point it is hyperbolic orbit, for example.
So how do you explain the shadow of the black hole in M87?
Okay. I do not know details. I only know that some physicists very much like to discover something, so they tend to believe that their images are something, and I don't think that that it is correct picture. We do not. It does not any picture about black holes is not realistic because black holes are not. This is just a black body. This is a picture of black body, not black hole.
What they're seeing is you've got an extremely hot accretionist which is radiating, but then they say region where the photons don't get out. They go orbits around them.
This is a black body, but not black hole.
Yeah, so maybe final comment.
Aren't you saying that the black hole can't be formed?
Pardon?
Aren't you saying that a black hole cannot be formed? You know, it just doesn't exist.
It doesn't exist.
It's not because the collapse would always be the theoretical collapse of gravity would just ricochet away because it's the point of any material that was collapsing.
So what do you call the object then? Sagittarius A star? What is that?
Well, astronomers have a lot of fancy names, so we can think about one. So let's thank the speaker once again. So Professor Krizek will have the last talk of the day.
Mr. Chairman, ladies and gentlemen, 4 years ago I had a paper in this pink proceedings about some paradoxes and general in special relativity. At that time I showed such a picture that or such a phenomenon that if the clock is approaching you, then you see higher frequency, yes? But according to special relativity, you should see lower frequency because of time dilation, yes? And this means that the Doppler phenomenon is much stronger than time dilation, yes? And moreover, in Lorentz transformation, in Lorentz transformation there is no Doppler effect. So I will show using a specific example of the twin paradox. I will have two twins, or they needn't be twins. This you can replace it by just clock. Yes, these are atomic clocks. And the time dilation may lead to a mathematical contradiction with equivalence principle. In particular, we prove such a strange relation that tau is less than t. T will be the proper time of Adam, which will stay on Earth. Yes, we shall have here Adam. This is Adam staying on the Earth, and Bob will move, yes, and tau will be proper time of Bob, yes, and from time dilation you get such an inequality, tau is less than t, but from equivalence principle you get that t is equal to tau, yes, because if Adam stays on Earth, so he feels gravity, gravity acceleration is g, small g, and if if Bob flies with the same, acceleration, then they should be equal, yes? So you see that there is some strange relation. And it will be subject of my talk. So very briefly, special theory of relativity is based on the Newton's first law, and Einstein had two postulates The first postulate says that laws of nature have the same mathematical form in all inertial systems. This is called relativity principle. And the second postulate or assumption is that the speed of light is the same in all inertial systems. So we shall have two inertial systems. S prime moves along axis x with a constant speed. This speed is less in absolute values, it is less than the speed of light. And if the origins of these two systems meet, then we fix that the time in one system is zero and in the second system it is also zero. This is famous Lorentz transformation, which appears in Einstein's paper. It is in fact only one-dimensional problem in space direction and in time, this time, and these two orthogonal coordinates are, say, do not change. And here is the famous or well-known Lorentz factor, which is always greater or equal than 1. So first objection is that I don't think that in real physical universe all systems should be equivalent. Yes, because according to this postulate 1, there is no preferred inertial system. Yes, so all systems should be equivalent. But if you would travel by some relativistic speed, say larger than 5% of the speed of light, then you will see that the galaxies in front of you become blue, but those which are behind you become red. Yes. So this is one example that there is some preferred system. Another reference system can be connected with cosmic microwave background. Our sun moves with respect to cosmic microwave background with the speed 370 kilometers per second, which is small speed. Yes, it is not a relativistic speed. And moreover, there is another system which may be assigned to gas which is between galaxies or dust which is between galaxies. It also does not move. Yes. So that means that there exists several preferred reference systems which are associated with our physical universe. And you can easily find that all systems are not equivalent. Yes, that you move with respect. And these systems cannot be deleted. Yes, they cannot be eliminated under any circumstances. They are just there. Yes. Concerning the second postulate about the constancy of speed of light in all inertial frames, so now it is bypassed by defining that C is just this number, yes, and that's it, yes. This satisfied exactly. So now from Lorentz inverse transformation, which looks very similar to this transformation, there is only you exchange these primes here, and instead of minus you have plus. It is very easy to find that this is inverse Lorentz transformation. This is just simple matrix multiplication. So you obtain a famous formula for time dilation. Yeah? So there is this inverse value of the, say this is proper time of, say, Adam, and this is proper time of Bob. So by this formula, clock at rest is the fastest. I will show you now classical experiment, how it is, classical twin paradox, how it is explained in books. So we have here, say, Adam and Bob is flying to, for instance, this is red dwarf, which is Proxima Centauri, yes. So if Bob flies with constant speed to Proxima Centauri, he can transfer his say time, proper time, to Charles, which moves in opposite direction with the same speed. And if they so this is if you just substitute to this relation for time dilation, if you substitute the values when v is equal to 80% of the speed of light, then this factor will be 5/3. So if you substitute to this formula, you find that this is only 3 years and this is 5 years. Then they exchange the information, and this is for Charles. This is symmetric with respect to the horizontal axis. So Adam will have 10 years, but here Bob 3 years, Charles 3 years, and this is called clock's paradox. Moreover, if Bob and Charles would fly by smaller speed, then there are 4 dots or 4 intervals, here 3, here 1 only. So if Bob and Charles would fly more and far away, then the time would be shorter and shorter, yes. So it is a little bit counterintuitive. So you get the so-called reverse triangle inequality, yes. This and that, this and this is smaller than this. This is very strange, yes, because I'm a mathematician, and in all, say, reasonable metric spaces, the triangle inequality is valid, yes. So this, say, Minkowski space-time is not surely, for instance, Hilbert space or any metric space in mathematical sense, yes. Sorry, yes?
Isn't Charles moving towards Adam and Bob is moving away from him?
No, they only have transmit information about, because I want to avoid infinite, say, accelerations, yes. Everyone travels by constant speed, yes.
Yes, but Charles is moving towards Adam and Bob away from Adam.
Yeah. Sorry, I didn't understand now.
So Bob is redshifted relative to Adam and
No, okay, so Bob is red-shifted from Adam, and the one is blue shifted. Yeah.
So that compensates. The clock for Charles goes.
Of course, these say Doppler phenomena compensate. I agree with that, but there is, at least according to Einstein, there is this time dilation, and time dilation is something extra, which is not as strong as Doppler phenomenon. Doppler phenomenon is much stronger than just time dilation. Yes, this is what was in my first slide.
But they're moving at a constant speed, so they are in initial frames. And how come there's a time dilation?
No,
The only thing you have is the Doppler effect, nothing else, right?
No. This is just application of this formula for time dilation. This is a standard, say, picture which can be found, for instance, in Penrose book, yes? And now let's look to another picture. So now assume for a moment that our space is represented by fixed sphere S3 sphere, which was also Einstein's idea. Yes, first he had universe which was fixed in time. And so locally here is Adam, and locally it is Minkowski space here. So if Bob goes around, this is great circle on the sphere S3. So then Bob, then Adam's time is goes quicker than Bob's time, yes. And when they meet, then this time of Adam will be larger than Bob when they meet here. This is according to time dilation. Of course, this is not Minkowski space, it is curved. But here, it is converse. Bob is fixed, and Adams moves around. And you get completely opposite inequality, yes? So there is no, yes?
The Lorentz transformations are only valid in Minkowski space.
Oh, okay, this is what I am talking now about. Yes, exactly. So when said there is no time dilation effect in S3, but on the other hand, according to special relativity, time dilation exists in E3. So this corresponds to this Minkowski, yes? So it is strange that how it is possible that in, say, the clock does not know if it is in, say, S3 universe or E3 universe, yes?
It does. The clock knows.
No. No, I'm saying that there is something strange, yes?
Adam, in the left case, Adam is not in an inertial frame, right?
No, it is not inertial frame. I'm only saying that if the universe would be flat, then you have, according to special theory of relativity, there is time dilation, but if it is sphere, then there is no time dilation, because you get contradiction, you get opposite, say, inequalities, yes? So, I will skip perhaps this. This is a book about how beauty leads to physics astray. This means that we often identify very beautiful models with reality, but reality is very often different, yes? So in Minkowski space-time, a very strange property holds. Yes, the straight line segment between two events is longest. Yes, in Euclidean space it is shortest. Here it is longest. And now my last example. According to general relativity, the difference after 1 year between clock of Adam and clock of Bob is only Bob is outside the gravitational field, Adam is in the gravitational field. This is famous formula in this say book and TV. Is only 0.2 seconds. So it is almost negligible, yes, such a small value. And now I will consider such a diagram. So Adam stays on Earth with Adam, and Bob is flying in this direction, and he will have constant acceleration plus g, yes? So we will go that way and then return, accelerates back, yes? So his, say, work line is such a hyperbola, and so he will feel the same acceleration through the whole flight, and now, if we denote by t the proper time of Adam and by tau the proper time of Bob, then there are famous regular coordinates. This is for distance, this is for time. This is in fact, instead of formula for time dilation for special relativity, we have this formula now between time t and tau. This is proper time of this, yes. And these frames of Adam and Bob are not physically equivalent because time runs at different rate in each frame. Now, my last example is that according to regular coordinates, the proper time of Adam is such a value if you substitute to that formula, but for Bob it is 1 year. Yes? So there is difference between these two numbers. This is t equal to such a number, and here is, and this is due to equivalence principle. Correctly, we should reduce, as I told you, that if you are in Earth and outside Earth, there is very negligible difference between proper time. And moreover, if you slightly increase the gravitational acceleration, so this is something between Earth and Jupiter, you get that 2 is equal to 1, yes? So this is the contract. And I can do such a contradiction on arbitrarily small interval, yes? Our relativists, the people who work in relativity, they say, oh, it holds locally, yes? You must consider it locally, but I can do this contradiction on an arbitrarily small interval, yes? So
The example was Bob went one way and then the other way. There's acceleration of 2g at least. I was have to turn around.
No, there is constant acceleration. This is Bob, yes, there is the top of the rocket, and he goes by very fast speed. And when he meets Adam, he just slows down, and then accelerates.
Yes.
It is really constant acceleration on the whole work line. So that's all. So my final remark. I didn't see any papers criticizing the theory of numbers, theory of graphs, theory of groups, theory of probability, theory of matrices. I really do not know any paper. But there are hundreds of papers continually criticizing special theory of relativity. I will skip this example. So if the phenomenon of time dilation does not exist in the physical universe, then our optimistic prospects for habitation of exoplanet will be significantly limited. This means that we are not able to reach, say, Andromeda galaxy within 15 years by only acceleration which is equal to, say, gravitational acceleration of Earth. So, okay, so I'm finishing because cosmological model is based on the general and special relativity. There are many papers. Is special relativity wrong? It was published in Nature. Dingle, is special relativity right or wrong? Nature. Einstein relativity is absolutely wrong, and so on. So many people found that it is not as good as it is supposed. Yes, my time is for you. Thank you very much for your attention. Yes.
You are proposing that there is no such thing as time dilation, right?
No, I am saying that it is problematic. Yes, I am claiming that it is problematic.
I wonder about acceleration with accelerator experiments or muons in the atmosphere.
Yes, there are hundreds of papers that criticize, that confirm that there is absolutely no problem with special relativity. Yes. I'm giving you mathematical contradiction. Of course, I cannot say, design some experiment which should show that this time dilation exists or not. I'm saying that there are mathematical problems, yes? There are, you can prove that 1 is equal to 2, yes? And if you can prove that 1 is equal to 2, for me, that such a theory has no sense, yes?
Okay. Thank you very much again.
Welcome to our second day session. Also welcome Yurii V, who Yurii is one of the organizers of this conference. So we are happy to have you here at this moment. Okay, we start with Petri's presentation. He speaks about spherical models of the universe. The audience is yours, Petri. Thank you.
All right, wonderful, very nice to be able to be here. So we will spend the next half an hour talking about hyperspherical models of the universe, basically working in the wonderful research idea world of Suntola. We will mostly concentrate on supernova observations. Then we will briefly discuss pulsar timescales, and then the concise mathematical ideas of Suntola. It depends how much time we have. So there's we collected a small preview of the mathematical visualizations. You can go to that link, css.2024@physicsfoundations.org, or mark it to your notebooks. And it's not a stable link, so I recommend not to rely on the link, the link stable, but it shows the current research that is going on. So there's mathematical visualizations. It's hosted by the Physics Foundation Society, which is a non-profit association, small association in Finland. And we are looking for building a research consortium and collaboration around these topics and ideas of Suntola. And we already have a few institutional research partners, such as a project in the philosophy of physics at the University of Helsinki. So please contact if you have ideas. So let's discuss science first. So we make guesses, and from guesses we derive consequences. And this is often thought about as a theoretical work, and often consequences come instantly into your mind, but also there are things where you need to make decades of meticulous work to get publishable results on mathematical journals, for example. Then experiments are really important, and this is often referred to as experimental work, and they're the correspondence with reality is important. And now in all of this line of inquiry, you have sources. So you have, usually they are like primary sources and secondary sources. The secondary sources are not like secondary level in a sense, but they are not primary in the sense that they are directly the observations. And in many cases nowadays, the theories and the sciences are so complex that most of our sources are actually secondary. And so they are through like other parties in a sense. The theories, methods, and even the observations are so complex that even if you work at some astronomy like a laboratory, you seldom go to the actual data, the actual hardware. What does it do? But going to the primary sources is important, but it's laborious. And then when building models, it's really essential to try to concentrate on essential complexity. So in models, really often in all technical and other developments, you get accidental complexity into models. And this is like quite ordinary for mathematicians, because you aim for the essence, because you sense that there might be something that might have been said for the first time. And then That's like important, and then you go for the essence. But also the accidental complexity is such that you have to deal with it. So now here's one example, like motivational example of accidental complexity and essential complexity, like determinant in matrix linear algebra. You all learn in technical, like freshman mathematics class, Leibniz formula, Laplace expansion, submatrices, how it works. And then you learn that the determinant is the product of eigenvalues. It's the proportional to hypervolume spanned by rows of columns. And suddenly it unlocks so much like intuition. What is it about matrix linear transformations between high dimensional spaces? Why does the determinant go to zero when the hypervolume collapses to zero? And this is one way of conceptualizing, like, because you can get to the essence. Also see factorizing, and this is important in Suntola work, because often you have, x squared, but if you express it as a like separate product, then you suddenly get to see that there might be some possibilities of variance. And also if you have, let's see if I have here the slides. Also, if you have like matrix and inverse matrix, it becomes really important to think what is actually happening, and especially in really large, like this is like a motivational expander, but large factorizations, you have things you have done to the, for example, in early phases of the model, and then the end, you somehow the factors can cancel each other out, and this is really difficult to look for. So there's essential simplicity and accidental simplicity that we need to be like careful about. So some things might look too simple in a sense. So towards the theme, for example, in this theme, so the light travel distance, so the look back time in standard cosmology, there's different terminology there. So with that parameter, this 0.2629, and you can calculate extra digits there. In flat space condition, so then the omega n and omega lambda equals 1, and there you have removed the other parameters, so that it's not multi-criteria optimization, it's just one criteria optimization. And then you can express it in closed form, the integral, and then you can externalize it when the z increases without limit. You look as far as you can. The integral becomes unity. So it's a mathematical thing. The integral there becomes unity, and the distance, the light travel distance, becomes Hubble distance. And it's an interesting thing, because in a sense, this should be like empirical parameter, but purely by mathematical construction, you can get an extremal point that it's actually a little bit too close to the current like experimental values. And then if you use that as an experimental value fitting the distance modulus, it doesn't fit well. So if there's something in the like structure of the standard cosmology model, then this might give a hint that it somehow perhaps linearizes the model, those current like experimental parameter values. And it's a big thing. So here's just to contextualize this discussion. So here's a picture from Perlmutter, supernova, dark energy and accelerated universe. It's from Physics Today, almost 20 years back, but still like very relevant. So usually in this you have a redshift, and already in this conference we have discussed what the nature of redshift, what it is. Then you have time, billions of years from today. You have linear scale of universe relative to today, and then you have relative brightness of the supernova in this. And then you fit for example, supernova observations. You fit the models to this data. So now to be more explicit, the redshift is usually modeled as the increase of wavelength, so it affects all wavelengths. So you have a model or like a assumption that the emitted or the source wavelength is something, and then the observed wavelength is increased by this delta lambda, and you just divide those, and that is like the easiest way to conceptualize the redshift. And in many standard like conceptualizations, you link it directly to the scale of the universe. So that's why you can draw this picture. So, for example, when redshift z is 1, then the scale factor is 0.5 in this model. Then the time scales, the t, it can be in different time scales. So there's cosmological time, there's in general relativity, there's proper time, coordinate time. Some of them are linearly dependent, so it's easy to transfer from years to seconds, but some are non-linear. And then the scale factor, it's very often expressed as A, at current time it's 1, so it's like a normalized scale factor. But more and more, I don't know more and more, but for example, in review of particle physics, they use R directly. So it's sort of left as is, and it's only normalized when you need to normalize it, which is quite nice. It feels like you don't lose information from the start. And then these luminosities, this brightness of supernova, they are often expressed in magnitude. And this is a like historical development in a sense that the magnitudes have been like standardized or made before like current high-tech observational instruments. So that's kind of a logarithmic transformation to the actual fluxes gives the magnitude. And it's a bit unfortunate because then it loses the physical units, or at least it increases the possibility of accidentally operating on those magnitudes in such a sense that you lose a little bit of the idea, like what is energy actually like observed. So now the dark energy survey, 5-year full dataset, was released just a couple of months ago, and it's really, I so much appreciate that they release the data to be able to analyze it and see the data. And these are huge projects. You can see, for example, here the desk collaboration. They are on the by surname on an alphabetical order, and still there's 59 additional authors not shown. So I really appreciate this work. And there the data release in the GitHub folder where there's data. So there's the light curves, and you can see the academic reference there. So now this is one plot of the data. So let's look at this. So here's the features. So DECAM is the dark energy survey camera. These cameras, they are in northern Chile, ground-based telescope. And there's the observations through G filter, R filter, I filter, and Z filter. And there's very specific technical specifications available for this filter, what they actually what the physical characteristics are. Then you have so-called flux cal, and so this is a calibrated flux density. It's calibrated such that the AP magnitude 0 point is 27.5. So it's in a sense already gone through the magnitude system. So even though we would like to have like physical measurements in a sense that they would have physical units, because this is radiation, light that you are looking for, and radiation is very understandable, already modeled phenomenon. So you model, for example, these lights here with radiation, you have steradians, you have irradiance, you have this. All the units are certain or known. But here they use these Fluxcal units. And then the redshift is such that it's measured from the host galaxy spectrogrammatically. So these observations here, one point here, it's a few seconds to a few minutes. I don't know the actual the exposure time for one photo, but it's a photo of a supernova, and so these vertical bars here, they express the light curves. So the supernova starts like quite dim, and then it goes to its brightest point, and then it dims back. It takes few weeks to few months. You can see the light curves online. So each of these is one supernova. And then I have plotted it so that the alpha, the transparency, is such that on the peak magnitude day, it's the brightest, and then otherwise it fades down. So then you can see that you have these envelope curves here. And by modeling these envelope curves, you would know about the physicality of this cosmology, or this physicality of space, how energy propagates, presumably, if you can model those like peak magnitudes. Usually you go through quite difficult processing, like light curve fitting and stuff, but I wanted to use the raw data. And now here's the reported error bars. So it's like near where the filter or where the light hits the filters, like low redshift towards the higher redshift, where the error bars are much lower. So this can be quite noisy. So you can make different kinds of like quality cuts to the data that I have not made, just to be like sure that I haven't done any like too much reduction. So this is now the Suntola model. So Suntola model that Suntola expressed in his book, The Dynamic Universe, it fits quite well without too many parameters to this data, to this like almost like physically observed data, because this has been processed in many ways, but it hasn't been like combined to one magnitude yet. So it's sort of raw. So I can go through this what happens. So you have so-called hyperspherical optical distance. We can go through what Suntola means about this. And you can bracket the hyperspherical at this point because it's really algebraic, really simple optical distance. Then you have the Hubble distance, which is 13.8 billion light years. It belongs to this optical distance definition because the optical distance saturates at Hubble distance in this Suntola model. Then we use supernova spectral flux density template. So there are flux density templates which are physical. So in a sense that they are ergs per second, so watts per area per Ångström. So it's really like a physical idea of how supernova flux density looks like. It's estimated at 10 parsecs and at day 0, because we are estimating the highest speed of supernova. Trying to model how the supernova light radiates through space and dims at the highest speed. Then we use the absolute magnitude distance of 10 parsecs because it's in the density is defined there. Then we use just inverse squared distance dilution. So just this optical distance, we just dilute this inverse squared like ordinary radiation, because the sphere, not speaking about free spheres, but ordinary like radiation propagates so that the area dilutes in distance squared. Then the wavelengths are redshifted by 1 plus z. So at each redshift here, we like redshift the spectral template with 1 plus z. So if, for example, here in the when the redshift is 1, the redshift template is doubled. So because that is what is observed when you look those emission and absorption features in spectrograms. Then we use these Icahn filters bandwidths in Ångström. So actually we don't need to use the transmission curves. We just need to know where the filter starts and when it stops in the wavelength bandwidth. So we can take from the spectral template, redshifted spectral template, already that bandwidth. Then we have to, because this is now physical prediction through this model, because then we have physical prediction of the watts per area. But then we have to go through this magnitude system, because this, even though this is original data, it's expressed in this magnitude. So we have to convert it to AB magnitudes, and so this is just a definition, it's not a parameter. Then we have to use flux cal 0.3.27.5, which is also just a definition. And then for some reason, we need to use as an absolute magnitude minus 19.253. This is from Pantheon Plus paper. Usually it's minus 19.3, but here, because there was this more specific available, then we use that. And only with those, so there's only basically one parameter in a sense, this Hubble distance, that you can fit the data. And now this is a very subtle point, but there are two scenarios for this redshift dilution. So this black line here, it's actually, there's the redshift dilution is 1 plus z to minus 4th power. And we think that the first is just technical, because when you redshift the spectral template, you need to have first dilution of the energy density, so that the energy integral stays invariant. So then it actually implies this 1 plus z to the 3rd power, and in VU, in Suntala model, it then implies that in absolute units, the redshift dilution is 1 plus z to 5th power. And this is a really like a subtle point, but I just mention it here because when you get into these kind of theoretical models, then you get to new kinds of definitions, and you can like explicate some problems better. So this is something that we are currently studying. And now the red line here, it's something that actually in Suntala model, Suntala thinks that where the observations should be, like physical. And this is a really subtle and difficult point, because these are like expressed as reported fluxes, but they go through that processing, and we would need to have a really like a big like research effort to understand the whole physical pipeline where these data are gone through to understand the meaning here. Could there be this kind of a dilution? So now I can briefly show some details. So here's the spectral flux template for supernova. We take the day 0, we redshift it, so it hits these filters. These are the actual transmission filter curves, but we don't need to use them because they have been inverse transformed to top of the atmosphere fluxes already, and there have been other helpful against that. Then we dilute it at least once to keep the energy density. Then we analyze what happens if we dilute it twice. It's a difficult situation because AB magnitudes are defined as constant energy densities on the frequency space. But if you convert that to wavelength space, it actually becomes these curves, and these are the exact curves. So the supernova template P actually happens to follow the AP magnitude curve. It's just a happenstance, because these don't belong together. But it complicates the analysis, because then the AP magnitudes are the same in all these things, all these scenarios, because it's just makes things so really difficult. That's about those inverse and stuff. It's really difficult to think what is going on. And now the model, how the hyperspherical optical distance works, it's so simple. So actually, you just think that you linearize the expansion of space. So the scale relative to today, you just assume, just that's a mathematical assumption at this point. You just assume that the scale factor expands or largens at the speed of light. So at the same time that the universe has existed or expanded, the scale factor has expanded the exact same amount. So then you get the optical distance when you see one observation. You just define this d, and now because of the expansion, the r0, so the current radius or current scale factor, divided by the scale factor what it was at the emission, it's now defined as the redshift. So these are then linked. And now from here, you can solve the d from here. And this is the optical distance. And this is like there's only one parameter here, the Hubble radius. And it's linear. And in mathematics and in sciences, whenever you see a possibility for a linear model, you should go towards it, because it's scale-free. So now when we are in this Cosmology of Small Scales conference, the same relation, if it turns out to be true, it works on the smallest scales here, because it's linear. And also linearity gives you tremendous amounts of expressibility in analysis. And now the luminous distance that I showed, it's just that you have the luminosity at the 10 parsecs, you have distance at 10 parsecs, then you have this optical distance at whatever you are now observing the distance. And then you have this dilution factor of the redshift. And when you put that here, you get this relation. And this is now the relation that was fitted to those observations. So there are no intervals here. But this is the difficult thing, is that we need discussion, like what is the true exponent here? And it's quite technical, because in Suntola model, the supernova template, it actually is higher energetic if you go back to history. So it's higher energetic exactly at 1 plus z squared. And so it cancels out these terms, and you still get the same result as now. All right, and this is something that needs like studying. I'm not claiming here yet anything, because I know that the K correction, for example, it's a really like technical thing, and it's needed, it's used. But you can see how Suntola wonders about these things, because if you go, for example, to Reese's famous paper from 2002 or 2004, in that era you still usually use Vega magnitudes, and in tables you specifically express the K correction factor. And now they also express the redshift, and if you plot the K correction against redshift, you get exactly this 1 plus z squared dilution. So even though it might be really like coincidence, due to, of course, you need to shift the higher redshift observations to to this frame here, but it's also seen that it's exactly that dimming that is now perhaps, but that is Suntola claimed here. And because these go so nicely on top of each other, all these terms, it needs really like rigorous work to go into this. Yes. Let's see if I have here. Yes. And this is, I would just leave it here, but this is that you can also convert the fluxes to magnitudes, and then you get these usual like distance modulus plots, where the Suntola model it perhaps goes nearer. For example, this new observation, 2.903, but it's just one observation. And in this crowded region here, if you go towards more and more detailed models, where there's dark energy and others, it goes towards this Suntola models, at least like qualitatively. But I haven't made any fits here. I just used the Hubble distance, so it works. It's like really simple formula that needs studying because it's almost geometrical. There's no stuff. All right, but I will leave it here because I wanted to go with these empirical results quite like detailed. So.
Okay, thank you. So we have a few minutes for short questions. Yes, please.
Hello.
Yeah.
So I would like to ask how about, because I didn't quite understand about the Melia model. Is the Suntola model predicting or deriving the Melia expansion too, or not?
Yes. So I can. Yes, it's a, but it's a very subtle thing. So I would. Could I show the website quickly?
Yes.
All right. So here I have collected some visualizations. Right. Now let's see if it will work. All right. So it doesn't work here, but you can go to the website, and there's a specific kind of a differential equation that predicts the expansion factor in this kind of a cosmological timescale. So there's different timescales in cosmological timescale. But then there's also in Suntola model the SE system, so the second, is affected such that the speed of light and the expansion is constant in like local timescale. So in that sense, you can in local timescale that you usually use when you discuss experiments, there the expansion is linear in Suntola model. Yes. Sorry that is, but you can go into the website and discuss with me about this. Yes. Yes. But I must emphasize that this is derived from completely different kind of assumptions than general relativity. So it's like you can just at this point it can be handled as a mathematical like phenomenological model, but it's quite well defined. So you can as a mathematical model you can study it. Yes.
Okay, thank you.
Okay.
Hello, I am Juan De Vicente from FIEMAT Madrid. It's a pleasure to be here. I want to thank the organizers for giving me the opportunity to make this talk. And I'm going to talk about the static interpretation of Friedman-Metz Robertson Walker metric. I will start with the empirical science of a static universe I have detected in photometric receipts. I'm going to describe a new approach for photometric receipt, its cosmic receipt inference, and its derivatives on cosmology. And finally, I will talk about the static interpretation of Friedman-Metz Robertson Walker metric. Well, I have detected some empirical signs of a non-expanding universe in photometric receipt, there are different approaches to photometric receipts as machine learning methods or simplistic methods. Here, we're interested in those methods that provide a linear relationship between receipt and magnitude. That is the case of slow ensemble early data release, where they perform a regression on magnitude to colors. So, for example, we have a regression on magnitude, that is, the receipt is a linear relationship of magnitudes. Then they perform a local fit to neural network on a training sample. It has been applied to a slow ensemble and it produces very good results. Let me show my contribution to this field, that is DNF, galaxy photometric receipt by directional neighborhood fitting. We perform also a regression on magnitudes, so we have the same linear relationship. We also perform a local fit to neural network on the training sample, and we have two improvements. That is, the directional neighborhood, we take into account magnitudes and colors in the same metric, and we perform a relative fitting that allows us to remove outliers. Well, it has been the reference sample in that survey and has been selected among the algorithms to be used or to be implemented in LSST. Well, these methods produce very good results, but they are local fit. So we cannot extrapolate to other areas of magnitude, other magnitude space. So, since we are interested in obtaining a general relation between receipt and magnitudes for the complete sample, we are going to resort to cosmological relationships. That is the case of the luminosity angular distance relation, that is GL over DA equal to 1 plus C to gamma. This relationship was first derived by Etherington from general relativity in 1933 for a local or non-expanded universe, has DL over DA equal to 1 plus C. And it was separated for an expanded universe with the economic concept, has DL over DA equal to 1 plus C squared. Well, we are going to use this cosmological relationship to derive a new photometric receipt method. That is the relationship. We can define the luminosity distance as usual, that is the square root of the luminosity over 4 pi FL, where FL is the flux we measure. And we can define also the angular distance, that is the distance at emission, as the square root of the luminosity over PA FA, where flux FA is the flux that we will reside from a galaxy in a universe, we will reside in a static universe from a source at a distance this A and without receive. If we divide both expressions, the luminosity dependence is removed. If we apply the luminosity distance relationship, we obtain this expression. We can take logarithms, and we found three terms. The first term is the luminosity magnitude. We can measure it. The second is the angular magnitude. And the third one, we can define what we call receipt magnitude, that is 5 gamma log of 1 plus C. Since we can use multi-wavelength surveys, we can put this expression in vectorial form, and now we can see that the angular magnitude only depends on luminosity and initial distance. Luminosity and initial distance, this is the flux of magnitude, and on the other hand, the receipt magnitude depends only on receipt. So they are orthogonal. That is important in this method. Let us cooperate with this relationship. if we multiply the relationship by V gamma, a unitary vector deviation of n gamma, we can see that this term goes to 0 since they are orthogonal, and these terms take the value, the scalar value n gamma. So we find this relation. Now we recover the receive value, that is this one, and we finally obtain this relationship. And note that we have found, or there exists, a simple relationship between intensity and magnitude that should meet all galaxies. So, if we have a survey where we are able to measure the spectroscopic receive, and we have a survey that we are able to measure the magnitudes, we can fit with this formula, we can fit the vector of parameters, V gamma, and then we can extrapolate to other areas of magnetic space. We have performed this regression in the Slura sample. Data is 15, 1.2 million galaxies. We have used the bipolar magnitude that are account for the flux of the bulge, the most luminous part of the galaxy, and we have found a good correlation between receive and magnitude for any value of gamma. So the methods is valid for any value of gamma. In powerful photometric receive methods, if we can train in one area of magnitudes, we can extrapolate to others. But that's not all. Note that we have assumed that the gamma is unitary. And what is the value that made the gamma unitary? The value that made the gamma unitary is gamma equal to 1. That is non-expanding universe. Well, we can see the same in another way. We have here the formula, and we can ask how far any gamma is from data. We can apply the receive reconstruction method. That is, we perform a regression to compute the gamma, perform a regression, we know the spectroscopic receive, we know the magnitude, we perform a regression, we obtain V gamma, then we normalize V gamma, and inversely reconstruct C gamma with inverse formula. And we have performed this receive reconstruction for gamma equal to 1 and gamma equal to 2. And we have found here the scatter plot. We have the spectroscopic receive, the reconstructed receive, and it is well performed for gamma equal to 1 and not so good for gamma equal to 2. That is good for non-expanding universe. We have extended this test for different values of gamma, and we have found these plots where represent the bias of delta C and scatter of delta C. That is the difference on the spectroscopic receive and the reconstructed receive. And we have found that the minimum is found gamma equal to 1 in both bias and scatter. So we can say that the Sloan data support a non-expanding universe. And we ask now, can this result be explained within general relativity and Friedman-Lemaitre Walker metric? Well, let's first to show the weakness of expanding interpretation of Friedman-Lemaitre Walker metric. Expanding universe rests on Einstein field equations and Friedman-Lemaitre Walker metric. Being R is important, being R are common coordinates. But note that the energy momentum tensor that appear in this equation and the observable luminosity distance that does not appear in these equations are not related by Einstein field equation, in spite of both treated with energy fluxes. We need, what is required, another ad hoc equations to relate theory and observables. That is the common equation that is from general relativity. That is, dl, luminosity distance, is equal to the common distance, like 1 plus c. And what occurs in a static universe, or non-expanding universe, different from the Einstein static universe where A of t is equal to 1. Well, with the non-expanding Friedmann-Levin-Walker universe rests on exactly in the same equations. Einstein field equations and Friedmann-Levin-Walker metric. But now with a different interpretation of R. R is not the common coordinate, but is the luminosity distance coordinate. And let's have to analyze this equation with this view. Assume we have a galaxy, the observer, at an angular distance or initial distance, which is the same in a static universe. And assume we have light rays, since we are talking about light rays, differential tau is equal to 0, and since we are in a non-expanding universe, the angle is also 0. So we can apply these values to the Friedmann-Levin-Walker metric and obtain the relation. We can now integrate from time of emission to time of observation on one hand, the temporal side of the equation, and we can integrate from 0 to dl. Usually we have here dm, but note that we are now considering r luminosity distance coordinates. So we have here directly the luminosity distance. And now assume the simplest case where k is flat, is equal to 0, so for a flat universe, and we obtain this relationship. So note that we have to relate the luminosity distance directly with the energy momentum tensor. Note that both are related with energy velocities. So we do not need an additional equations to relate theory and observation, as it occurs in an expanding universe. And let us to analyze this equation. Well, we can consider the current c, the speed of light, is constant, so we can move the c outside the integral and define delta t prime as the integral from time of emission to time observation, differential tau over A of t. And now, with this definition, we have dl is equal to c delta t. On the other hand, we are in a static universe. The initial distance, dA, the angular distance, or is the same as the initial distance, is equal to c delta t. We can derive both equations and have dl over dA equal to delta t prime over delta t equal to 1 plus c. So we have recovered the Eddington equation for a local or non-expanding universe. And note that this has been derived directly from Friedmann-Levin-Walker metric. How we have to interpret A of t? A of t is now a time dilation factor, but it's not the radius of an expanding universe. The other case, maybe c is not constant. In this case, we will have a variable speed of light with constant time. So c of t is equal to the current speed of light over A of t. And how we can explain the receipt? Well, we have the frequency is the common frequency of atomic emission line, but note that since the speed of light is higher at the beginning, we have the wavelength is also higher. So that is the wavelength that we observe now. It was already at emission was this value. Along the travel to Earth, this wavelength does not change, so we can see it at reception, but since the speed of light is dropped up to the current value, we have that the frequency has lowered. So we observe here that we get the frequency at the wavelength that are usually measured. And on the other hand, we have to preserve the gross atomic structure, since we have assumed that at emission we have the common atomic emission line. Since we have the speed of light is 1 over the square root of epsilon sub 0, mu sub 0, that are the electric permittivity and magnetic permeability, one of the two have to change to have a variable speed of light. We consider that should be epsilon sub 0 to remain constant to preserve the gross atomic structure, the Coulomb law, and it is the magnetic permeability who has to change. So we have a variable magnetic permeability. If we relate it with the scale factor, it's not now the scale factor, but it's scale factor, it is equal to square root of magnetic permeability. Well, to sum up, we can interpret the Friedman methods of Walker metric in two ways. In an expanding way, we have coordinates co-moving coordinates. The other six are constant co-moving coordinates. A of t is the scale factor, and c is the residual to scale factor. But note that in this case, we have another equations to relate theory and observations. And we can interpret the Friedman methods of Walker metric as a non-expanding universe. In this case, the coordinates are velocity distance coordinates. The other six are constant velocity distance coordinates. A of t is a time deviation factor or a square root of permeability, magnetic permeability. And c is the residual time deviation factor or by the speed of light affecting to the magnetic wave period and hence wavelength frequency. So we have presented an empirical support of a non-expanding universe, and the non-expanding universe can be explained with the same equation as that model, exactly the same equations, but with a different interpretation. If you want to know more about this method or this theory, you can visit this archive paper. Thank you very much.
Okay, thank you, Juan. Are there any questions? Yes, please.
I didn't quite follow everything, but if I interpret what you are saying, so is the following correct? Are you suggesting that you see evidence from expanding universe, but not for the associated magnification with redshift? But so in the usual expanding universe, you have a magnification effect with distance. And if I understand you correctly, then you see evidence for expanding universe, but not for the magnification effect.
No.
Or am I completely wrong?
What I see is this relationship. Well, this relationship takes the value gamma equals to 1, and gamma equal to 1 corresponds to a non-expanding universe. That's defined as here.
It's going to square redshift, right? So how do you interpret the redshift if it's not expanding?
But it's a very
How interpret the redshift? Yes, I can explain here.
Sorry for me to explain it again.
I can explain it again. The redshift. Here I can explain the redshift. We have common atoms, and then we have atomic emission lines, the frequency of these emission lines. At emission, we have that the speed of light is higher, so lambda c is also higher. This is the wavelength emitted. that we see now, since it does not change along the travel to Earth, we find the same wavelength at reception. But now, along the time, the speed of light has dropped, and now we have the current value of speed of light. So the frequency has dropped, and we obtain the values that we measure now.
Okay, so it's the speed of light which is changing. That's
Is the speed of light which is changing, and not an expansion of the universe.
but is it correct that it looks like a flat space-time where the as we apply so the angular distance corresponds to the velocity distance without the magnification effect, right? This is that.
We perform a relation between the velocity distance and angular distance, and we fit it with data, and then obtain the value gamma equal to 1.
Okay. Can you show the Friedmann vibration? Friedmann metric.
Sorry.
Yeah.
Yeah. So if I understand well, you explain cosmological redshift as a time dilation. It means that you change the Friedmann metric and you insert the AT, the scale factor, into the first and the term c squared dt squared. There should be the a function of time and
Well,
scale factor.
I use exactly the same.
Also, the AT and the spatial metric, you remove this. So you change metric, and you should do that, I think, to have consistent explanation.
I do not change the metric. I only.
This metric is for expanding universe. So if you speak about the non-expanding universe, you cannot use this metric. This is
Well,
why? Because A is the scale factor, which is increasing, and it increases distance. You speak about time dilation, it means that your factor AT is not at the spatial coordinate, but at time coordinate.
Yeah, it's true if you interpret R has the common coordinate, but I interpret R has the velocity distance coordinate. This is the change that made the.
Yeah, so you interpret R in a quite different way. Okay.
It's the interpretation of
So
R.
it should be emphasized, of course.
Thanks.
Why do you prefer a change in light speed over a time dilation explanation?
I do not prepare any.
You don't do it. It's
Something to be detected, we measure in period.
Okay, any other questions? So thank you, Johan. So then we are ready to move online. Harry Desmond, are you there?
Hello, yes, I am.
Okay, welcome to our meeting.
All right, so thanks very much for the invitation to come and talk to you. Again, sorry I can't be there with you in person. So I didn't see the MOND talks yesterday, but I hope I'm going to sort of follow on from those by digging down into 3 tests of modified dynamics and how they relate to one another. So those are the radial acceleration relation of galaxy dynamics on kiloparsec scales, the Cassini test of gravity in the solar system on AU scales, and the wide binary test on parsec scales that Javier, I think, talked about yesterday. So the question I'll ask is where do these 3 pieces of evidence collectively point with regard to MOND, and what do we need to do to make sense of them all simultaneously? Okay, so I'll start on the larger scales with the RAR. So hopefully this cropped up yesterday, but just in case it didn't, I'll briefly introduce it. So the RAR relates the acceleration sourced by baryons in late-time galaxies, G bar, to the total dynamical acceleration, G ops, measured from the rotation curve. So if you measure these for many points on the rotation curve of one galaxy, you trace out one line on this plot. And then if you repeat that for all the galaxies in spark sample, you build up this full diagram, where the average error bar size is shown by the blue cross here. So the reason it's interesting is it has at least two features that seem rather strange from the perspective of galaxy formation in LCDM. The first is its shape. So at high acceleration, g-orbs becomes equal to g bar, while below some characteristic acceleration around 10 to minus 10 meters per second squared, it starts to deviate from that 1-to-1 line, but in a very regular way. And the second is the observed scatter is rather small, and in fact, by some accounts, it's fully explained by the observational uncertainties, which means the intrinsic scatter is almost negligible. But in MOND, the relation is very natural. So here you have Newtonian dynamics at high acceleration, so that if there's no dark matter, g-orbs naturally equals g bar. While as you go below the acceleration scale a naught, eventually force effectively become proportional to the acceleration squared, which produces this logarithmic slope of a half down here on the line. So the Newtonian and deep MOND regimes are connected by something called an interpolating function, or IF, which is this mu in here. The most common ones are these ones that I've shown in the plot here, potentially including something called the EFE, the external field effect, which is the way in which MOND violates the strong equivalence principle and causes the relation to tend back to a slope of 1 at very low acceleration. So the first question I want to ask is, to what extent exactly does the RIR support modified dynamics over lambda CDM? And I've tackled this in a number of ways over the years, which I don't have time to discuss, but I'd be happy to talk separately about the lambda CDM prediction for the RIR, and also what exactly the relation's functional form is. But here I'm going to focus instead just on its intrinsic scatter. And that's crucial because in MOND, the RIR is essentially a deterministic relation that follows directly from Milbaugh's law, while in lambda CDM it has to emerge from the messy process of galaxy formation. So roughly, calculating the intrinsic scatter just means subtracting the observational uncertainty from the observed scatter of the quadrature. But the reason, statistically speaking, this is tricky is that most of the error bar that I show here is actually coming from uncertainty in galaxy properties that link the G bar and g-orbs values across particular galaxies' rotation curves. So those properties of the galaxy are mass to light ratios of gas, disk, and bulge, and the distance to the galaxy and the inclination. And that causes correlated deviations from the RIR, like these points that you see, some outlier points on the plot, which means that this uncertainty can't be assumed to be Gaussian and uncorrelated between the points. So as a very simple example of that, if the mass to light ratio of the galaxy scatters up, then G bar has to scatter up across the rotation curve. But if you analyze this relation, assuming that the uncertainties are independent between points, that would imply that that increase in mass to light could cause one point to scatter up and the next to scatter down, which doesn't make any sense. So the proper thing to do to quantify the intrinsic scatter in this relation is to constrain these parameters of the galaxies jointly with the parameters of the RIR itself, which propagates the uncertainties correctly as systematics and maps out at full degeneracy through the RIR parameters. So I'll model the RIR here using just a simple interpolating function, whose only free parameter is the acceleration scale A0 to MOND, along with an overall intrinsic scatter. So for 147 galaxies in the spark sample, of which some fraction of them are bulges, that means you have almost 800 parameters that you need to infer simultaneously to do this, which is essentially impossible for most Markov chain Monte Carlo algorithms to handle, but it's fairly simple using this more advanced technique called Hamiltonian Monte Carlo, or HMC. So the idea here is to plug the data into an HMC sampler using the priors on the galaxy parameters from the spark error model, and then derive posteriors on them plus A0 and the intrinsic scale. So what I'm showing in the plot here is the best fit is taking the best fit galaxy parameters from this inference and using them to transform G bar and g-orbs according to these formulae to produce what I call the underlying RPR. which is essentially optimized for the choices in those global galaxy parameters. And I overlaid those points on the original, what I call the prior RAR in gray, which is just what you get when you allow those nuisance parameters to take their maximum a priori values. And the best fit simple interpolated function is shown in red. And all that's left of the statistical uncertainty is this tiny error bar here. So you see that the correlated deviations from the line have gone away by doing this. The uncertainty has got much smaller, and the intrinsic scatter has got much smaller too. So it's become incredibly tight. You could do this in a few different ways. The different prescriptions for the external field effect, for example, doesn't make much difference. The upshot is that the relation wants the classic value of A0, 1.2 by 10 to the minus 10 meters per second squared. But what's interesting here is that the intrinsic scatter has gone down from this 0.08 dex that it is if you assume the uncertainties are all Gaussian uncorrelated between points, to 0.034 dex, doing it this better way. And that's just an 8% uncertainty on G obs at a given G bar, making this relation possibly the tightest known in galaxy astrophysics, one of them at least. And there are other possible uncertainties from, for example, disk thickness and spatial gradients in mass to light ratios that could easily make this zero. Okay, so still on the topic of the RIR for a second. This is a bigger topic, but I wanted to say a few words before I move on to solar system about one other project on the RIR that I spent some time on, which is trying to get at this notion of fundamentality in galaxy dynamics. So basically, given the extreme tightness of the RIR that I just showed, we might wonder if it's somehow special among the set of dynamic correlations of late-type galaxies. And in this paper here, I proposed these 4 properties that a relation should have to be considered fundamental. So it can't have significant residual correlations with any other variable, because then you could form a tight relation by including that variable. Has to be the tightest projection of galaxy dynamical parameter space, and be capable of accounting statistically for all other correlations. And it has to be unique in that no other partially independent relation possesses these properties. So I made a bunch of tests to get at each of these 4 things. I've only got time to show the first one here, so asking whether there are residual correlations hidden in the RIR. So this plot here shows the partial correlation coefficient of G obs at fixed G bar with all the other galaxy parameters in the Spark database, as well as the external fields. So it's telling you how strongly G obs is correlated with each of these fixed G bar. If the RIR alone was the relevant correlation, all these secondary correlations would be 0. So the real data is shown in red, and in blue is mock data that is Spark-like in every way, except its dynamics is, by construction, set entirely by the RF. So these blue bands then show the uncertainties that you would get just from uncertainties in the data, assuming the RIR was the only relevant correlation. And you can see that the red points are essentially typical draws from those blue distributions. Now you might be concerned that the residual correlations could be washed out by uncertainties in data. So I've also shown the results in green for mock data generated by a different dynamic correlation. And you can see that in that case, you should find significant secondary correlations in here, which would disagree with the data. So one other way of getting at that question is to ask whether it's possible to improve the prediction of G-obs by knowing something other than G-bar. So what I've done here is I've trained a nonlinear machine learning model called an extra trees regressor on the Spark data, and calculated the accuracy with which it can predict G-obs by knowing various things. So along the diagonal, it's allowed to train on just one of these, one feature, and along off diagonal, it's allowed to train on 2 features. And the color bar shows the accuracy that it obtains, with lighter being better. So what you see from this is that if you know G bar alone here, that gives the lowest loss, so that's the best predictor of G obs. If you add in any secondary variable on top of G bar, it doesn't help the prediction at all. In fact, it typically makes it worse because the algorithm gets confused by the irrelevant information. So taken together, these tick off the first point here, that the RAR can't be improved by adding any other variable, at least any other variable we have access to observationally in this data set. And you'll have to read this paper if you want to see how the RAR also satisfies the other three criteria of fundamentality. Okay, so that's it for the first topic. From that, the evidence looks great for MOND, in the sense that the RAR really does look law-like, as you would expect from Milgrom's law. But of course, if the RAR has to, sorry, if MOND is going to work, then it has to work everywhere, not just in galaxies. So now we're going to move on to two tests of modified dynamics closer to home. First is to look at the motions of planets in the solar system. So the solar system is deep inside the gravitational well of the Milky Way, with a strength of around 2 A0, which means you don't expect to see the big boosts to gravity that you do in rotation curves from MOND. But it turns out that the direction of the external field pointing towards the galactic center introduces a quadrupole into the solar system's gravitational field, which has a measurable effect on the orbits of some planets. And Saturn has a fairly big perturbation, and as luck would have it, the orbit of Saturn was measured very precisely by the Cassini spacecraft around 2010. So from the Cassini data, one can extract a measurement of the quadrupole of the solar system gravitational field. That's described by this Q2 parameter here. And in fact, Cassini measured no quadrupole at all, consistently with 0 within 1 sigma. And that requires the transition from deep MOND to Newtonian regimes to be very sharp, such that the solar system at 2 A0 is essentially completely Newtonian. So the idea here, this project, is to ask how consistent that is with the RAR that we just showed in modified gravity interpretation. So what I did to do that is generalize that underlying RAR analysis that I just showed to use a parametric family of interpolating functions like this. So this generalizes the simple interpolating function I was using before by adding some new parameter delta, which is a shape parameter that controls the sharpness of the transition between the Newtonian and deep MOND regimes. So the larger the value of delta, the sharper the transition, with delta equals 1 being the same simple interpolating function that I showed before. Okay, so in each of these panels here, the blue posterior is the same in each of them, and it shows the constraint on A0 and delta from this interpolating function that you infer from the Cassini measurement of the quadrupole. The little ellipses show the constraints from the RAR under different models for mass to light ratios, which are 3 different panels, and different assumptions for exactly how the external field effect behaves, which are the different colors within each panel. So the basic upshot here is that if you use the fiducial mass to light ratio model of the galaxy data in RAR, the values of A0 and delta are completely off from what you have to satisfy the Cassini constraint, which is about a 9 sigma discrepancy. Things get a bit better if you allow the centers of the priors on the mass to light ratios to float and constrain them from the data. So the fiducial prior centers in SPARC are 0.5 for the disk and 0.7 for the bulge. So these are kind of different. These are the best fit values you get if you allow them to float. And in particular, it's quite surprising that the disk mass to light should be higher than the bulge. So this seems like a rather bizarre solution. In principle, you get an even bigger improvement in the consistency between the RAR and Cassini if you arbitrarily remove galaxies with bulges. Although in that case, the preferred disk mass to light ratio is then even larger. So essentially, the upshot from this is that you have to do some rather a priori unwarranted and strange things to get the RAR to agree with Cassini in modified gravity interpretation. So that doesn't look very nice. The final test that this connects to is the white binary test that Javier, I think, described in detail yesterday. So as you heard then, the idea here is to search for the roughly 20% boost to orbital velocities that MOND produces in wide binary systems in the solar neighborhood in the gravitational field of the Milky Way. Now, there's something of a controversy about this test. Javier probably told you that it gave strong evidence for MOND. There's another group led by Q and Che that finds the same thing. But there's yet another group, Vanek et al., that finds, using the same Gaia data but different methods, that actually this data supports Newtonian gravity rather than MOND. It doesn't support this 20% boost that MOND will predict. So I don't know enough about wide binaries to weigh in on that. I don't want to do that. But I can show you that the Cassini measurement is consistent with the null detection of Vanek et al., not with the detection of Hammer. So Vanek et al. Parameterized the effect of gravity on wide binaries using this parameter alpha graph here. The way this works is it interpolates between 0, which is what you get from Newtonian gravity, and 1, which would be a classic MOND solution. So their inference from Gaia produced this constraint, which, as you can see, is consistent with 0 and is strongly inconsistent with 1. So that's the evidence that the data supports Newton rather than MOND. Okay, then what I want to do is show how that relates to RAR and to the Cassini measurement. So what I'm showing in these plots is the posterior predicted distributions for alpha graph from my fits to the RAR. So basically, what distribution would you expect to find from alpha for alpha graph if you would only measure the RAR and done the fit to that? So again, I'm showing the 3 different mass to light ratio models. The fiducial model wants some alpha graph that's quite near 1 because it just likes regular MOND, essentially. Whereas these other mass to light ratios, which increase consistency with the Cassini constraint, prefer smaller alpha graph just because essentially they're more Newtonian in the gravitational field of the Milky Way. And in fact, only with this a priori very unexpected model where you just remove bulges and allow a very high disk mass to light ratio does the RAR become consistent with this null detection from Gaia, which is shown by the grey dashed line. Okay, now Javier will simply tell you that this inference is biased, and the Gaia data does actually prefer a much larger alpha graph, probably consistent with MOND in this left-hand panel, for example. And that would be fine if you neglected the Cassini constraint, which I'm not showing yet. But another way of looking at this is to use the constraint on the A naught and delta from Cassini to predict what you would expect to find for alpha graph, to see how consistent those two data are. So that's what I'm showing here. So again, this dashed grey curve is the Vanek et al. Posterior on alpha graph. And the other curves are the posterior predicted distributions for alpha graph from Cassini under 3 slightly different families of interpolating function, but they will essentially give the same result. So what you see from this is that within the context of MOND, the Cassini measurement implies that gravity has to be really nearly Newtonian at the field strength probed by wide binaries, actually with even more constraining power than the Gaia data provides according to Vanek analysis. So if you took these results at face value, they wouldn't actually even need, you wouldn't even need to do the wide binary test, because you would have known from Cassini 10 years ago that it would give a null result. But of course, that's not what Javier and Q find. They find effectively some alpha graph that's way over here to the right. So that means that some explanation is needed as to why they should be allowed to violate the Cassini constraint. So one simple solution to that could be to try to fine-tune the shape of the interpolating function to make it Mondian within galaxies, to satisfy the RAR, but then highly Newtonian in the solar system. And what I've said so far sort of leaves open that possibility because I've only considered these smooth Gaia families that have one additional shape parameter besides A naught. But of course, there could be further degrees of freedom in that. It's just a phenomenological thing that has no theoretical motivation in MOND. So we'll spend a little bit of time trying to understand whether that can work. What I'm showing here is a new interpolating function that follows the RAR IF at low acceleration up to a new acceleration scale AA trans, at which point it abruptly transitions to Newtonian behavior. So that's what's shown. It follows RAR IF, and then at some point, bam, it just becomes Newtonian, and then follows the Newtonian path. I also marked on the acceleration scales spanned by the galaxy data, which is from top to bottom dotted, and the acceleration field of the solar system. And then over here is what we would infer for the Cassini quadrupole Q2 parameter as a function of A and trans. So basically what you have is that if you want to satisfy the Cassini constraint, you need this new parameter to be less than A0, roughly, which corresponds to the green line in this left-hand plot. And that would make this entire range of accelerations that are probed by the galaxy data completely Newtonian, which would have a big adverse effect on the RAR. And even if you could get that to work, it would wipe out the one-sigma wide binary test, which is at a similar field strength to the solar system. So I think it's a big challenge to find some modified gravity solution to the RAR, the solar system quadrupole, and a non-null wide binary test simultaneously. Okay, so I think that's it. Let me just end with my conclusions here. So this is what I've shown you. If you properly account for correlated uncertainties in the RAR of a spark sample, you find some tiny intrinsic scatter of 8%, and basically perfect agreement with what you would with the simple models that people have been exploring for 40 years. And furthermore, the RAR appears to be the uniquely fundamental relation of late-type galaxy dynamics, because it can't be tightened by including any other variable, and it's the strongest dynamical correlation which can count the amount statistical. That seems highly unexpected in LCDM. But then just when you might be prepared to declare victory for MOND, you find that it produces this 9 sigma discrepancy with the Cassini measurement of the solar system quadrupole, and that measurement implies Newtonian behavior in wide binaries, which supports the null result Banach against Javier's, and there's at least no simple way of rectifying or reconciling those three measurements, which means I think for MOND in its traditional modified gravity guides to work, it needs some kind of epicycle like screening or some additional variable beyond acceleration that's relevant to make it work. And I'll stop there. Thanks.
Okay, questions in receiving. Hi, so thanks for this nice talk. I just have a question. By how much do you have to change the direction of the external fields from the galaxy in order to make the MOND effect in the solar system within the Saturn orbit go away?
Yeah, I didn't look at that explicitly, but I think you would have to change it by quite a lot larger than we know what the direction is, what the galactic center is. There was the degree of freedom I included. I think it was in Aurelian East's original analysis of this, but he concluded that that wasn't really something that was a...
Yeah, well, if you're, I would suggest to do that, right? Because you are reaching fundamental conclusions, so you need to be able to answer that question. Exclude a possible change of the external field direction from the galaxy, because the sun is not in the mid-plane, and the galaxy has a warp, plus it's probably oscillating in the vertical direction. There are Gaia data showing that, so there are these complications which one has to take into account, right? For testing for these very, very subtle issues.
Yeah, I can look more at that, see if that could help you.
I have a couple of comments. First, regarding this controversy in terms of wide binaries, you mentioned that there is this Banach paper that gives the opposite result to what Q and I have been claiming. Well, first of all, it is of course just a single paper, whereas I've been publishing a series of papers on this point coming to a system solved as Q, all independent. And you said you didn't want to weigh in on the controversy of being an expert. However, precisely for non-experts, I just recently wrote a very extensive rebuttal on monthly notices of the banning paper. And even though you're not an expert on that, you're certainly a scientist and you know statistics, it is very clear from the banning paper that the two models being compared are within the errors of each other. So they are within sort of a one sigma result of each other, and yet the claim in the banning paper is that one model, the Livonian one, is accepted over the MOND model at more than 19 sigma. I don't know if you've ever seen such a thing in science, it's just 19 sigma. Just by eye, I mean, if there is a 6 sigma preference, the preference is absolutely obvious and evident. In the banning paper, both models being compared are within the noise of each other, and yet the claims for a 19 sigma result. This comes from a thoroughly inconsistent use of statistics given the error structure of the data being treated. And this has been explicitly shown in a paper I recently published with Q in monthly notice. I really advise you read this paper before stating that you are incapable of making a judgment as to which of these two groups is right or wrong, because it is very clear. Now, regarding these studies you have presented, well, first of all, I would like to commend you on your work on the RAR. It's extraordinarily readable. It's amazing, and it's surprising how tight this relation comes down to, and I completely agree that this is really pushing us in a direction of concluding that we are looking at a fundamental physical relation behind these acceleration scales. Now, there is a point I really fail to understand in all this. When you say, for example, Cassini is inconsistent with the RAR. It is inconsistent in as much as you try and fix a single and a unique transitional function for those two problems. However, they are extremely distinct problems, not only in terms of acceleration, but other scales are coming in, like the mass and the size, and even the geometry of the problem is very different. Particularly in the case of the wide binaries, I mean, both in the solar system and in the RAR data, the geometry has spherical or at least cylindrical symmetry, which is and static potentials, which is not the case for the wide binaries, where you do not have either of those symmetries, and you don't even have static potential because you have elliptical orbit. So even the potential changes as a function of time constantly. So given that we don't have a fundamental theory for MOND, I don't see at all why one would expect equal transition functions in both of those very dissimilar situations. If you look at other physical transitions, like for example, the quantum to classical regime, and if you were to fit phenomenological transition functions for the heat capacity of a crystal or the black body radiation or whatever, you would get completely different fits at 4 different problems, even though the underlying physics is always the same. So I don't see why you are so fixated upon solving both of these cases, or these 3 cases, fitting them to a unique transition function.
Yeah, so this is what I was alluding to with my final point about there being some additional variable that could be relevant to the system. I completely agree that there's no reason that you necessarily have to have a universal interpreting function. It is nevertheless the case that the modified gravity theories of MOND that we know about at the moment do, so it is at least a valid test of those. And then I think the onus is on us to come up with some other theory that would produce different interpreting functions that would be consistent across those regimes. Because it's not very satisfying to just say, oh, we have this interpreting function here, we have this interpreting function here, we don't know where they come from, they just need to be this in order to satisfy the constraints.
Yeah, I completely agree. I think the current MOND situation cannot possibly be thought of as a final finished product, and indeed what we're showing is one more indication that we're missing some fundamental theory behind it. Just in fact, we have no justification for the transition regime for starters, never mind whether the transition function is one or many or whatever.
Yeah, exactly. It's just that it was sort of phenomenologically, it is phenomenological. You need to have just one, and that's going to explain all the dynamics. And it becomes slightly less easy to swallow if you have to vary that, etc. Of course, there may be some fundamental theory that naturally produces such a variation, but that we haven't seen. So I think, as I say, the challenge is for us to come up. I certainly don't want to imply that these results rule out MOND. I think I was clear that it was, ruling out what kind of canonical modified gravity interpretations of MOND that had a universal interpolating function. But still, it means there's more work to be done.
Yes. Thanks.
Yeah, thank you. Thank you, Harry. I think we are ready for coffee break now.
All right, welcome back from the coffee break. Our first presenter here is Anastasiia Lazutkina.
Yes.
Thank you.
Yeah, thank you. Good afternoon, everyone. I'm a philosopher, I'm not a physicist, and I'm doing my PhD on MOND and LCDM from the philosophical perspective. What I'm trying to understand is why do standard cosmologists not take seriously most of the arguments that we talk about in MOND literature? And so this is kind of the general problem, how to understand this debate. Now, usually how people talk about it is that, well, it's a problem of scales. So LCDM explains cosmology, and then the task is to go downscale to explain galaxies. And for MOND, it would be the opposite, like it works out for galaxies, for the dynamics, and we need to go upscale. But I think that there is a problem with this very common characterization. One is that, well, predictive success of LCDM for cosmology is at best exaggerated, so there are problems there. And on the other hand, we do have, like you heard yesterday, probably about UHDM being able to account for CMB power spectrum, or the extensions of GR that give you MOND as a classical limit doing the same thing. So it's not really just a scale problem. And another thing is that for LCDM, the problem would be not just to explain the irregularities, like we've heard now from Harry about radius toleration relation, but it's also about overcoming the contradictions that it has on these scales. So it's not just providing an explanation, but it actually is modifying the model. But when you look at the conferences that people have and what they're talking about in standard cosmology, they talk about Hubble tension, but have you ever heard them talk about radial acceleration relation, dynamical friction, core cusps, as a kind of thing going on that everyone would worry about? They don't, right? They never hear about these things. Why? So that was my question. Why do you not care about this? So what I'm trying to briefly today talk about is that I think that something happened in the end of the 1990s. Something happened in a way that we shifted from the standard cold dark matter to what we have now, LCDM, in a way that the considerations from cosmology, they started to be prioritized over everything on galactic scales. And so whenever we talk now about the problems in galaxies and galactic clusters even, they would just say like, well, this is not a test for the model. You can't test the model with this. This is not a big enough problem. That's not attention. So since I don't have enough time, I'm just very briefly going to sketch the outline before. So you had basically the first model coming from Einstein with the static universe. And then by the 30s, you had basically solutions for Einstein field equations applied to the universe and explaining kind of the expanding evolutionary universe. At that moment, all the debates were purely theoretical. And when the formulation of the steady-state theory came in 1948, the main kind of difference was how to do cosmology. Because what people did in relativistic cosmology, they started with extrapolating GR to all scales. And so the main criticism of people who worked in steady state was that you can't do that. You can't over-extrapolate a theory. and instead you should like work basically from what you have, from the empirical conditions that you have. But there was nothing kind of to separate those two. So it was about methodology, about how to do science, and about how to do cosmology. And so what was happening at the same time is that general relativity was kind of at its lowest possible. So if you were doing, if you're a graduate student, you will probably be told in the 40s that you should never work on GR because there is no way it's ever going to work. Because there's no way we're going to be able to test it or apply it to cosmology. So it was like, historically speaking, it was very few research activities going on. But then after the war, after the Second World War, when you had all the equipment available, something strange started to happen. So we call it Renaissance of general relativity. People started to work on it. And then you had discovery of quasars and of binary pulsars, and of course CMB. All of this has shifted the view that you do physics in a way that relativistic cosmology could be done, could be tested. Like you can apply it, and it actually is a scientific field. And so what you had by the early 90s is that you already had two like very strong empirical constraints. You had the Hubble constant, which is not a constant, actually, philosophically speaking, it's a parameter, but that's just the way we use it. So you had it kind of, well, different values, but more or less, not as much as before the 90s, it was about like 50 and 100, the difference, but by the early 90s, it was already about, like, agreed to be 77. And then you have baryon density from all three, lithium, deuterium, and helium, and then combined with cold dark matter and inflation, this should have given you the total mass density, so it should have been 1. And the age of the universe would be then 10.8 billion years. But that's not what you observed. So what you observed was that the stars were older, and they were much older, so it was impossible to kind of see how you could save the standard model then, because they were like either 12 billion years or 15 billion years, or you would see the white dwarfs that were 10 billion years, and then you would need to add 2 more billion years for them to become white dwarfs. And then when you were observing galaxies and the galactic clusters, you could talk about the baryon fraction. So people who are now working in standard cosmology, like Simon White, they were all doing that research and kind of extracting the baryon fraction, which would give you omega like to a maximum 0.3, but not giving you 1. So then you have constraints from gravitational lensing on omega lambda, and this would be about 0.7, that you could already use for calculating like structure formation. And because co-emission gave you results of CMB, you needed to connect it with the last structure formation, together with positive cosmological constant. Like this would solve all those problems. But it wasn't just CMB. It wasn't just cosmology. So it was stars, it was galaxies, it was galactic clusters, and it was CMB together with it. But it was like all the scales converging. So now in philosophy of science, when we talk about like when you have good evidence, is when the evidence from different scales converges. You're not selecting different scales, but you know all the given scales. And so by 1995, you were already sure that you need a positive cosmological constant. And so these are review papers that kind of start the time when standard cosmology became standard. So this is from Ostrich and Steinhardt. So they talk about the convergence of evidence starting from basically from stars, from less quasars, from gas clusters, from nuclear synthesis, and so on. And they give you basically the range of models in concordance. And you see that the best one would have a positive cosmological constant. And so that the same review papers from 1995 from Krauss and Turner saying that basically the cosmological constant is back. So as we shall discuss, the observational case for cosmological constant is so compelling today that it merits consideration in spite of its checkered history. And so what is this data? Well, age of the universe, the formation of large-scale structure, galaxies, clusters of galaxies, superclusters, voids, and great walls. The main content of the universe is constrained by dynamical estimates, Big Bang nucleus synthesis, X-ray observations, clusters of galaxies, etc. So the idea is that, again, you're using all the scales for doing that. That doesn't mean that it was the only solution. That also doesn't mean that we have actually a positive cosmological constant. It just means that the way you reason when you have a problem is not that you select certain type of evidence, but you do your best with all the evidence you have. And so when the supernova results came in 1998, it was like kind of a final confirmation, but everyone already knew that. So everyone like already accepted the fact that you needed there. And so that's why it's kind of difficult to say the supernova just changed the situation, because it didn't. It was already playing a crucial role for science. And so, yeah, it's clear that what we now call Anastasiia was already the best fitting model when the supernova data came in and confirmed it to the extent that even most skeptical cosmologists had to take lambda seriously. Now, what happened after this was that, well, you needed to do the CMB fit. And so Stacy Magog, even though he was working in MOND, he did predictions for both, for Anastasiia and for GR, without cold dark matter as a proxy for MOND, because MOND would have no effect on CMB. And the predictions for the second peak from Anastasiia, they were wrong. They were right for GR without CDM for the second peak, wrong for the third peak. But for Anastasiia, they were wrong already for the second peak. And what happened was that you have to change baryon density. And so you see this one of the papers that was very, very kind of popular at the time. So this is 2000, saying that, well, the second acoustic peak, like we need to do something about it. And the only way to do that, to fit it, would be to change the baryon density. Now this baryon density, like, was almost twice as much as you had from Big Bang nuclear synthesis. So the convergence of evidence from different scales and from all the evidence started to kind of be lost because we left lithium out. So you can't say that all your evidence converges to that. And this is very important philosophically, because when you say that all the evidence takes you there, you're basically kind of making a false statement, because it's not all the evidence. Okay, so you change the baryon density, we accommodate CMB spectrum, but something is missing. And I think what was missing was the way to unify CMB with individual galaxies in a way that you would like have one way of talking about this. And I think that what Simon White with Navarro and Frank, what they did, this NFW profile, was exactly the kind of mechanism that allowed for it, because you could use CMB as initial conditions and you could make predictions for individual galaxies. Now, as you know, they came out wrong, and that's what we know is a robust problem. And then the idea was that, well, you can involve a baryonic feedback as a mechanism to explain why the predictions are wrong, the simulations. But because you have to involve the baryonic feedback in order to provide this explanation, you cannot make individual predictions, and you cannot think of galaxies as tests for your model, because they just, they're not kind of type of evidence that could be used against cosmological models for people who work in Anastasiia, because you would need to always think about processes you have never thought before. And so, when I listen to Simon White, he says that galaxies are very complicated objects because you need this baryonic feedback as a mechanism to explain it. And when I go to Pavel to his lectures, he says, no, galaxies are very simple objects. So what do I do as a philosopher? Whom do I trust? How do I understand? And I think the solution to this is that galaxies become more complicated. Of course, they become more complicated when you assume cold dark matter. So in a way, you have a total prioritization of observations. And you could see this from the review articles now. It's not like it's just my view. I think cosmologists, many of them, they honestly speak about this, that the reason we work on LCDM is because of the CMB power spectrum, and especially the third peak. So this is their way of reasoning. And so, just to conclude, I think that this shift that happened in the 90s, it kind of can explain why people who work on MOND, why can't they kind of reach to LCDM cosmologists? It's because they would never think of galaxies as the way to test their models. They would never think about anything except very large scale as a possible test. And now when I ask why, the usual reply I get is that, well, you know, CMB, linear like perturbation theory, that's super simple, but galaxies are messy. But again, galaxies are messy only within the model. But you have to kind of think outside the model.
What binaries are simple?
Why binaries are simple, yeah. So to conclude with quote from Sanders, so there's a tendency for astronomers to regard cosmology as the queen of sciences. A reductionist undercurrent gives cosmology priority over mere galaxy phenomenology. Data such as patterns of anisotropies in the CMB are very well fit by the study cosmological model, albeit with a somewhat strange combination of 6 parameters. Given the precision of the fit, then the theory must be correct, even in its implication for galaxies. This makes most cosmologists dismissive of galaxy phenomenology and its wealth of regularities. These are problems that will be understood in the context of more detailed computations of the baryonic processes in galaxy formation and evolution. Problems for the future. So the question is, well, like, is it justified what they're doing? So from a philosophical perspective, it's not justified. This is a problem. Thank you for your attention.
Now for questions and comments.
Hello. Nice talk. The constraints with that Stacy, the plot where that Stacy did was with Kobe, so it's really outdated. I tried to do that with the model software and I couldn't. So yeah, I don't know how we can trust that nowadays.
Well, we can't trust it nowadays, but
because with no dark matter at all, you cannot fit them. So the mechanism is that it provides these huge potential wells that inside them.
I know
the
this,
barrier.
yeah.
So with that's the first argument of LCDM. That,
I know, yes, but I think that what you have to distinguish when you're talking about the way that the model started to be what it is the kind of situation you were when you made a decision, right? So of course, now you're talking about the CMB like spectrum we have now, but I'm saying that back then, so you had this convergence, right? And you're ready to sacrifice that convergence, and this is a very, very dangerous step. Like, you're basically saying, I will eliminate part of the data because I want to save what I'm working on, right? So this is different. All of this could be wrong now. And actually, baryon density, I have no idea what baryon density is, right? It may be that doubling it was the right thing to do. But were you back then justified to do this? This is a different question.
Yeah, well, the omega baryon is now constrained by different observations, so it's... yeah, I don't know if Xavier wants to add something.
Yeah. Yes. I mean, from a layman's point of view, in terms of philosophy, there's a point which I think I don't know. I would like to know your opinion on how important this point is or isn't in terms of all this debate. What do you think of the lack of detection for the dark matter particle and the way the favorite candidates have been eliminated over the last few years? The whip miracle has gone away. The detectors are now reaching what used to be called the neutrino floor. Now it's called the neutrino fog because there's a hope of seeing through the fog or whatever. But certainly the situation has changed for the worst significantly over the past 10 years, let's say. No? And you didn't mention anything at all. I wonder why.
So I think that non-detection of dark matter is similar to a detection of dark matter. I'm not sure that it would solve the problem. Now why? Because if you don't detect it, like you could still argue, like forever that you can assume something else. You can assume something else. Is it a bad way of doing science? Probably is. Does it mean that there is no particle at all? No, it doesn't. You cannot make that logical step. You can forever search for it. But if you detect that matter particle, this also doesn't mean that it's that matter, because even with the detection, how would you solve all the problems?
No, I agree. But at least you know that. For example,
there's a particle. That's what I mean. It's perfectly consistent to have MOND and axons, right? Like there is no problem. It's just it's the amount of it, right, that matters. But like there's nothing contradictory within the theory that and the existence of like.
If you find cold dark matter particle with the right density, then for example the rotational curve will weight no longer allows for MOND because you know that you have as much mass as you need.
Yeah. So, but this would mean that you would need to explain all the other evidence of the skills, right?
Yes, but okay, I agree.
So,
it wouldn't solve all the problems of dark matter, but it would rule out MOND.
In the same mass energy content.
Yes.
Yeah, yes, but it's not the same mass energy
No,
content.
of course not. No, you
That's
just
what I'm saying.
you have to find them at the right amount, of course.
Yes. I mean, but I'm not sure, if we completely rule it out. I think that, but here you have to think about all those hybrid models. I'm not sure about that, if it will be like something like a superfluid. I don't know.
Mm-hmm. All right, thank you.
Okay, thank you very much. The title of my lecture is that the JEP Webb Space Telescope suggests a positive curvature of our universe due to the space-time principle, and global geometry and shape of the physical universe may be revealed by observing objects at very large cosmological distances. Because for small z, the universe seems to be almost flat, but recent infrared measurements indicate that there exist luminous galaxies at distances z approximately 13, which should not exist according to the standard cosmological model for flat universe. Yes, and I will introduce you three artificial magnification effects which could explain why these distant galaxies shine so much. The observed large flux luminosities may be mere optical effects due to positive curvature of our universe. This is positive curvature of our expanding 3D sphere modeling our physical universe. For Euclidean or hyperbolic geometry, such a flux would be impossible. So first, I will skip this. What is the problem that from Einstein equations it can be derived that the sum of these three parameters is equal to 1, but from observation we know that it is almost equal than 1, almost equal to 1, the sum of these two parameters. And there is a wrong implication that this implies that the curvature, the density of curvature is 0, yes, and that the universe is flat, but the curvature, this sphere can be extremely large. there are a never-ending discussion whether the global geometry of our universe is spherical or hyperbolic or flat. And we show that these large luminosities can be explained by a positive curvature of our universe. So Karl Schwarzschild conjectured in the beginning of 19th century, 20th century, that the universe should be can be described by such a sphere, and Albert Einstein also in his famous paper supposes that our universe is like three sphere with fixed radius. Schwarzschild found that the radius, which is here A, should be approximately this number, but nowadays we can make a much larger estimate because the mean density is approximately 6 protons per cubic meter, which corresponds to this mean density. And there are approximately 10 to the 12 galaxies observed, and every galaxy has approximately 10 to the 11 stars. This means that the total mass of the universe is 10 to the 12 times 10 to the 11, and here I include the mass of our sun. So you get such a estimate, which is very rough. But the volume of three sphere is given by this number exactly, which is volume is mass divided by mean density. And from these two relations, you immediately get such a lower bound for A, and A is now larger than 10 to the 26 meters. So it's extremely large sphere. So to introduce the main idea of this principle, suppose that we will be in the north pole of such a sphere, and that is perfectly transparent. And now I can consider two galaxies. One of them will be at the near the North Pole, and another will be near the South Pole. And so this is written, indicated here. So this angle is theta is 30 degrees, sorry, and this angle is 150 degrees, yes. And they have the same diameter, and this second galaxy is 5 times larger, sometimes 5 times more distant than this galaxy. Yes, but in Euclidean space, this galaxy would have 25 times less luminosity, but in spherical case it has the same luminosity, yes, because you see it under the same viewing angle. This viewing angle is the same, so even though it is 5 times more distant, you see it like it would be close to us. So this is one, example. Second example of magnification, artificial magnification, is that if you compare magnification on the flat space and on spherical space, yes. So you again have two galaxies. Here is one galaxy, here is second galaxy. That one is in flat space, that one is in curved space. The same viewing angle, but now you can, I will show you that we can derive that you will see this galaxy on sphere larger than in flat space, because the distance, this distance can be evaluated as the radius of this sphere times this commoving angle. The angular size is diameter divided by distance for k equal to 0 for flat curvature. But for k equal to 1, spherical universe, you have this relation. This is d equal to, this is in fact this relation. Now I can substitute here this d equal to a times comoving distance, and this is less or equal if I put here sinus, because sinus is always less than this angle, and this is by definition this angle. So you see that this angle is smaller than that angle. So this is another magnification effect. There are, say, maybe I will go back. You see that there are some coefficients d over small d, and here also d over small d. So we can remove them, and then you see that for spherical universe you get such a say dependence on the this comoving angle. This is for flat space, and this angle, this blue, is for hyperbolic. So especially for big co-moving angles, it is very big, this, and there is written ratio between, now I will consider squares, because if I consider luminosities, there is a big difference between co-moving angle and the square sinus of the co-moving angle, and it looks like that. For small z or small co-moving angles, it is equal to 1, but for large, this effect is very big. And finally, I would like to show you maybe I should mention that there are several meanings of what do we mean by universe, yes? So this blue, it is this sphere. This is the sphere of the great circle, because I'm not able to sketch three-dimensional pictures. This red, this is in fact expansion function, which is described by, for instance, by Friedman equation. But what we do observe is we are here, and there is the light cone. So this is another universe, which is observable universe, and these three manifolds are completely different, but we call them universe, yes? So we must carefully distinguish which universe we take into account, whether this yellow manifold or blue manifold or red manifold. I will skip this and finish with this example. So according to measurements of the cosmic microwave background, the redshift is this number, and what was the radius of the universe at that time if it would be described by the sphere S3? So by this formula, which can be found in Peoples, for instance. This is the estimate which I gave you at the beginning, that the current radius is greater than 10 to the 23 meters. Here I substitute from here. So at that time, the radius was approximately only 3 megaparsecs. And finally, this is my last example. There is a very big magnification of Big Bang itself, because it appeared approximately, say, 14 gigayears ago, and it was in a relatively small volume. But nowadays we see the Big Bang, in fact, in any direction on extremely large sphere, yes. So I would stop here because in the afternoon we don't start at 2 o'clock, but 15 minutes to 2, yes. Okay, thank you.
Questions and comments, please.
Yeah, Pavel.
Maybe just what we heard before earlier today that this evidence for the universe is Euclidean.
Sorry, that you?
We had a speaker here telling us that the universe is Euclidean, so there's no magnification. So can you
Yes, it was at the beginning of my abstract. Yes, there is wrong mathematical implication. This is the implication. Yes. So from Einstein equations you get this relation, which is equal exactly to 1. But from observations, it is almost 1, yes? But it does not mean that the universe is flat. It does not mean that the universe is flat. It is almost flat. Locally, of course, it is flat. But not, this is wrong mathematical implication, yes? So, for instance, concerning, you introduced us several months ago lecture that there are, say, massive black holes at z equal to 9, yes? But they can be smaller than you think, yes? Because of these artificial magnification effects of the sphere, yes? This means that these black holes, they are not in the, say, upper part, but they are in the lower part. And in the lower part, you get very large magnification effects. This means that all these galaxies which have z equal to 13 are below the, say, equator, universe equator, not, say, equator on our celestial sphere.
So you're saying that the evidence by Juan De Vicente here is consistent with your magnification idea?
Maybe, yeah. It could be. Einstein also supposed that the universe is C3, 3C sphere. I don't believe to say infinite universe because it would be for me miracle that at all points you would have the same density, same pressure, same temperature or so, yes. It would require infinite speed of transfer of information.
Also, I have a quick comment.
Yeah.
When we are speaking about angular size distances and they have different assumptions, then of course the potential expansion of gravitationally bound systems might come into play when you think about those angular sizes. And so what is it's then important to discuss what is the theory based prediction of early galaxies. Okay, thank you.
Okay, so see you within, say, much less than 2 hours.
So in the afternoon session, we proceed with Professor Martín López-Corredoira from Instituto de Astrofísica de Canarias in Tenerife, Spain. Please, welcome.
Thank you very much. Thank you for the invitation again for this important meeting for alternative ideas in cosmology. I think I'm glad to participate again. Today, I will speak about two hot topics of observational cosmology. The first one is this about the Hubble-Lemaître tensor or non-tensor. And the second one will be about the age of galaxies and hybrids. Hubble constant, Hubble-Lemaître constant, has been measured since almost 1 century ago. At the beginning, the values were very high, the value of H0 were very high until the 1970s, and due to some identified error in the calibration of the distance. But after the 70s, the values became more or less stable between 50 and 100 kilometers per second per megaparsec. Nonetheless, in no moment in the history there was a totally agreement of the value of the Hubble constant among different measurements of different groups. There were always some tensions, some discrepancies. If we plot all the values in the last almost 50 years, between 1976 and 2019, all the values available in the ADS, in the aspects of ADS, which are 163 values, we see the plot that we have here. As you can look here, there are many points which are incompatible with each other, because due to the small error bars, there are points which cannot be compatible with other points, other measurements. So the idea that we have tensions in the Hubble constant is not new. There were always, in the last century, there were always tensions in the Hubble constant. We can carry out a simple analysis of this data, just making a chi-square test. And we see that with respect to the weighted average value, which is 68.2 kilometers per second per megaparsec, with respect to this value, there is an dispersion with a chi-square around 600, which is much larger than the number of points. The number of points is around 160. The probability to have this by chance as a random fluctuation of the points, if we assume that the error bars represent a normal distribution, the probability is extremely low. It's totally impossible to have this by chance, 10 to minus 47. Even if we do a linear fit with the age of these values, we get something better, a chi-square of around 500, but it's still too low. So it's totally incompatible. It's impossible to make all these values compatible with each other, assuming that they represent the true value in the cosmological model, in the standard cosmological model. In order to produce a chi-square with a probability larger than, let's say, 5%, we will need to remove many points. At least 27 points should be removed in order to reduce the chi-square. Removing the vast values that are now plotted here in a different color in this plot, if we remove the values with higher deviation, the 27 values with higher deviation, effectively we get a chi-square around 160, which is in this case compatible with the number of points, in this case 136, and it has an acceptable probability. This is, by the way, the list of points that one should remove in order to make a chi-square acceptable. The 27 measurements with higher deviation with respect to the average. As you can see, there are some points even with 8 sigma deviation, the Sunday Santama in 1990, or the 5 sigma deviation later than in 2008, a value of 44 plus minus 4 by Impey et al. In 1998. So you can see there were a lot of tensions in the past. It's not anything new. Some researchers claim that the measurements of the Hubble element constant before the year 2000 were affected by some uncertainties that were not properly taken into account. The methods, the statistical methods were not totally accurate before the year 2000. But even if we take only the data after the year 2000, so in the x-axis is the number 0, if we take only the 85 points after the year 2000, even so we get a chi-square much larger than the number of points. So still the probability is too low. So it's not only a problem affecting the the data with more than 20 or 25 years ago. Also, the more recent data in the last 25 years are affected by this large dispersion. If you do the same exercise, if we want to get an acceptable value of the chi-square compatible with a normal distribution according to the error bars, we should remove at very least 6 values, these values that I got here. Of course, we can do the same exercise with more recent data. Here we have used the data up to the year 2019, which was the year in which Risk et al. Have claimed that there is important tension in cosmology due to the Hubble tension. So we wanted to examine historically the values in the past. But if we do the same exercise with more recent data, we will get the same inconsistency of the data with each other. For instance, if we take the analysis of the data between 2012 and 2022, 11 years, we get a chi-square 500 or 200 data, which is still a very low probability. In this case, of course, we are dominated by the two groups, the two measurements of the Hubble constant, of the first of the surface supernova, which give a value around 73, 74, and the CMB values, which are around 67 or 68. Two considerations about this simple exercise of the chi-square test. Why do we choose the weighted average value of the Hubble constant as a reference to measure the dispersion? Well, the answer is because this is the value that minimizes the chi-square. Any other value of the Hubble constant gets even a worse value for the chi-square. So it's not. If instead taking 68 or 69 as the reference, we take 75 or 55, the chi-square will be much higher. So the conclusion will be even worse for about the probabilities. The second question is about the covariance terms. Here in this chi-square test, we have not taken into account the covariance terms. And we know there should be some covariance terms because the data are not totally independent. There are some applications of the data, some analysis which have been done with the same data or with the same techniques, with the same calibration, so they cannot be totally independent. Anyway, even if we have applicated data, even if we have more data than 3 parameters, the reduced chi-square should be similar. Duplicating the number of data does not reduce the reduced chi-square. What we reduce is the number of degrees of freedom. And if we reduce the number of degrees of freedom, we can increase the probability, the Q probability, but still should be extremely low. If the chi-square is much larger than 1, the probability is very low for any number of degrees of freedom large enough, some larger than 20, for instance. So it's not a question of taking into account the covariance terms. This should change the calculation of the probability, but the conclusion should be the same. The conclusion is that these data are not compatible with each other. It's not only a question of the chi-square test. It's also the distribution of the dispersion of the data with respect to the average value. Here I plot the frequency, that is the probability to have a number of sigma deviations with respect to the weighted average. In the x-axis, we have the number of sigma deviations. In the y-axis, we have the probability, which is the frequency. And then we compare with what is expected if the errors were Gaussian, a Gaussian distribution. You can see that the frequencies of the dispersion are much higher than the prediction of a Gaussian distribution. For instance, if you take the number 3 sigma, you see that the probability to have 3 sigma is larger than 10%, which is incompatible, totally incompatible with a Gaussian distribution that gives you a value much lower than 1%. And this happens in any number larger than 0.5 sigma. Clearly, the only possible interpretation for this analysis is that statistically, in most of the cases, the error bars have been underestimated. Historically, always have been underestimated. It's the only explanation to make this compatible. Or the other solution is that they are measuring different things. But assuming that this Hubble constant are measuring the same thing in the same universe, it's impossible to make compatible this data with these error bars. Again, in this, I'm examining data before the year 2019, before the claim of result for the Hubble density. My conclusion is that there were always Hubble densities. It is not anything new. We have not discovered anything new in the last 5 years. We can make a simple exercise of how we should normalize the frequencies of the observed frequencies of the deviation of the Hubble constant in order to be a normal distribution. Here we have a simple bit in which the equivalent number of sigma, which is x EQ, the equivalent number of sigma, as a function of the observed number of sigma is this formula by which, for instance, if we have a 4.4 sigma deviation, the number that was given in the paper by Reis et al. In 2019, this is equivalent to a 2.1 sigma in terms of frequency, because the probability, historically, the probability to find an event of 4.4 sigma deviation in this kind of analysis is around 3.6%, much larger than what is given by our distribution. In the same way, if we claim that we have a 6 sigma deviation, don't think that this is something impossible with a very low probability. No, indeed, the analysis of the frequencies, historically speaking, in the last 50 years, show that the probability to have a 6 sigma event is over 1%. So it's equivalent to 2.5 sigma. Again, I insist, the only possible interpretation of this data is that they have underestimated the error bars. The question is, why so much noise with the Hubble tension after the publication of the paper by Reis et al. Claiming that there is a 4.4 sigma? If we know that the 4.4 sigma was something very usual in the last decade. My guess, I'm not totally sure because I'm not examining all the techniques of reducing the data and the calibration of the supernova, the space and so on, but my guess is that there is some missed measurement of the error bar. There was some systematic errors have not been taken into account. As a matter of fact, very recently, this year, an expert group in the measurement of the calibration of the distance of the galaxy using different techniques, with surface or other standard candles, led by Friedman et al. A very expert group in this kind of measurement. They have just published new measurement of the Hubble constant, and in this case, the error bars are large enough to make it compatible with the Planck value. So, according to these new values, there is no Hubble tension because the new measurements are compatible with the Planck data. This may be interpreted as an estimation of errors in the Reis et al. Papers. However, Reis et al. Has replied very recently, one or 2 months ago, that the Friedman et al. Analysis represents a biased subsample of their most complete sample. Well, maybe, but the question is why the subsample gives different values with respect to the more general sample. So, parallel analysis is necessary here. Whatever it is, the explanation, we should be aware that possibly there are some problems here with the estimation of the error. Again, I asked the question, why then so much noise with the Hubble tension claimed by Reis? And why not the same noise with the tens of Hubble tensions in the last 50 years? For instance, I have mentioned before, the value of 61.7 plus minus 1.2 derived with supernova also by Late et al. In the 2008. which represent a tension of more than 6 sigma with respect to the average value after the year 2000. I have only one possible explanation for that, and I think it's more sociological than physical. And it has to do with the trend of cosmologists to behave in groupthink dynamics following their leaders. In this case, Risk is a leader in cosmology, is a Nobel Prize, and whatever he says is taken with more attention than other papers, even if they are published in important journals like Astrophysical Journal, MOND, etc. Cosmology nowadays is a matter of confidence, and tensions have to be named by mainstream cosmologists in order to be recognized as such. This is true in many cases in cosmology, not only the Hubble tension, but here in particular it's curious that the same groups, the same big things in cosmology that were leading to the introduction of the dark energy in cosmology, the LCDM, 25 years ago, which are the groups of supernova and the CMB analysis, these are now the same groups that are leading the tensions in cosmology. And apparently, the community is waiting for instructions of their shepherds to guide the herd. Here I have a picture that represents very well the sociological situation in cosmology. This picture is taken from a book by Pavel Kroupa and collaborators, a book published in a serious publisher in Cambridge University Press, a different approach to cosmology. And they say, this is our view of the conformist approach to the standard hot Big Bang cosmology. We have resisted the temptation to name some of the leading views. So this is the first part of my presentation about Hubble tension or non-tension. Well, do we have now a more serious problem than 20 or 30 years ago about the Hubble constant? This is the question that I leave open. Let's go now to a second problem, another hot topic in cosmology, another problem in cosmology that we find apparently galaxies which are quite old at the beginning of the universe, when the universe was at high rest. There are many observations that indicate, in some sense, that galaxies at high redshift, at redshift larger than 6, should belong to a universe which is old, a universe older than maybe 1 million years. For instance, here I list some of them. We find that at a high redshift, we find galaxies with metallicity equal or higher than the solar metallicity. This needs some time to produce all these metals in the early universe. Also, we have dust at high redshift. We have calcium-2 absorbers at high redshift, like similar to low redshift. Large rotational velocity and content of coal gas. Also, it was a surprise. Also, it was not expected to find these scenarios at redshift 6, 7, or even larger. Polycyclic aromatic hydrocarbons. It is believed that it requires 1 gigayear to form these polycyclic aromatic hydrocarbons, but they were found at the redshift 6.76 when the universe was younger than 1 gigayear. There are problems also with the reionization. Apparently it's earlier than predicted. There is excess of ionizing photons at redshift 11, measured very recently with the James Webb data. We are finding quasars with supermassive black holes at high redshift, black holes larger than 10 up to 9 solar masses at redshift 7 or 8, which is difficult to explain because the black holes need some time to be formed, all these massive black holes. Even we have found galaxies at redshift 14, confirmed spectroscopically. It's not only photometric redshift, but they have spectroscopic redshift. And one topic that I think deserves higher attention is that we find massive galaxies at redshift 8 with apparently with all stellar population. And this is also in tension, opposed with the scenarios including the standard cosmology and the standard models of galaxy formation. Remember that in the standard model, the hierarchical galaxy formation model, we need first to form the small galaxies, and then through some mergers, we create the massive galaxies, the most massive galaxies. But it takes a long time. This process is not immediate. So the finding of a massive galaxy at a redshift 8 is at least a surprise. I'm going to concentrate only in this last topic about massive galaxies at a redshift 8. I have no time to dedicate to all the rest of the topics, and I am not an expert in all the rest of the topics. But I have been working in the last 1 or 2 years in this last topic, so I will give you my reflections. Indeed, the problem that we have high amount of massive galaxies and high redshift was already realized since almost 20 years ago. Here we have a plot by Steinhardt of the 2016 that they call the impossibly early galaxy problem, in which it shows the abundances, the density of very massive galaxies in comparison with the expectations, with the predictions of the models. As you can see, especially at higher redshift, at a redshift of almost 10 or 8, 9, 10, the points are much larger than the lines, at least 2 or 3 orders of magnitude. So there is a serious problem how these massive galaxies were formed. Sorry, somebody is speaking there, please. Okay, the microphone, thank you. Okay, continue. With the James Webb data, last year, in the journal Nature, it was published a paper by Vyacheslav et al. Claiming that the discovery of many of these most massive galaxies at high redshift, around 8, when the universe is supposed to be around 600 million years old, and they give masses larger than 10 up to 10 solar masses, and in some cases even 10 up to 11 solar masses or stellar mass. This is almost equivalent to the Milky Way. So you can imagine galaxies like the Milky Way, like Andromeda, totally formed and with so much amount of mass already when the universe was 600 million years old. I consider that this is an interesting topic, and it would be important to know something else about the age, if we can determine the age of this galaxy. It's not an easy problem, as I will tell now, but we can do some analysis. Indeed, these galaxies were already in some way analyzed by the same author, Vaclav et al. These galaxies were selected from the survey made with the James Webb data in near-infrared and Hubble Space Telescope. In optical, with the constraint to have a double break in the spectrum at rest, a double break in lambda alpha and Palmer rate. So we have this characteristic V-shaped spectral energy distribution, which is due to the double break. We have a blue part near the Lyman alpha and a red part near the Palmer break. Moreover, they require no emission, no significant emission as far as ultraviolet, in order to avoid high contamination from ADS. There may be some contamination, but not, it is limited by this not detection in far ultraviolet. In total, they have 13 galaxies. It is well known that in the Palmer break, the red color indicates the all population. Is one possible interpretation. If the Palmer break is higher, well, the age of the population is higher or larger. Here we have, for instance, in the left panel, the Bruce, Schwartz, and Charlotte's spectral population synthesis models, in which they show, in the number, they show the age in gigayears, and they show the how different are the populations when they are young and when they are old. Steinhardt indeed has carried out the analysis only of the Wagner break and has shown indeed that there are some points in the Labelle sample that might be older than the age of the universe because the Wagner break is very large. Nonetheless, we have to say that the Wagner break alone is not accurate enough to determine the age of the galaxy because there may be some degeneracy with the amount of extinction in the stellar population. The extinction may produce some remnant near the Wagner break. So we need to combine the information not only of the Wagner break but also including the Lyndon Errol break and everything in order to remove this degeneracy between age and extinction. There is a possibility, making a spectral energy distribution fitting. This has been carried out many times by many different groups, but here is we are with very peculiar galaxies because of this V-shaped spectral energy distribution, and we have one advantage with respect to water analysis. If we have a very important Lyman alpha break and a blue part of the Lyman alpha break, this means that extinction cannot be very high, otherwise we would not see the Lyman alpha line. Because the extinction in ultraviolet is higher than in this. It is already discussed in many papers. Here I put another reference, my group, but there are other references in which they show that only with two stellar populations, one all component and young component were able to fit this kind of V-shaped analysis, in particular for this analysis. We may, we may have more populations, 3 or 4, but this does not improve significantly the fit. But if we use some exponential stellar formation history or other kinds of combinations, the fits are not so well. The fits are much better if we are dominated in mass by a high population and a small component in mass of that population. Indeed, with this analysis examined by Kao et al., between redshift 2 and 4, we have concluded that these galaxies with V-shaped are on average are between 1 and 2 gigayears. And surprisingly, for redshift larger than 2.5, we find almost no evolution. So apparently the age of the galaxy is almost constant between 2.5 and 4, which was something surprising in this result. What happens if we go now to redshift 8? If we go to the massive galaxy at redshift 8 with V-shaped. Well, if we do the same analysis, we find the surprising conclusion that these galaxies might be older than the universe because we get the numbers that we get is that they are around 1 to 2 gigayears within 95 confidence level. This means that we have some small probability to be younger. It's not totally rejected the possibility to have younger galaxies. But statistically, the most likely value is between 1 and 2 gigayears. I'm going to tell more in detail what we have done to get this result. Indeed, coming back again to the Labelle et al. Analysis, this group, Labelle et al., they have already tried this kind of analysis on the V-shape. They have included several populations, and in order to explain the red part, you see the red part is the right side part in this panel, in which you see an increase in the slope. It's a very red for one particular galaxy. Well, this red part, instead of using a whole population, they use a very high extinction. They use a dusty stellar population to explain this large Wagner break and the red colors on longer wavelengths. In my opinion, this is not correct, or at least very discussable. This would be only correct under very exotic assumptions, because we know that in our galaxy, in the local universe, the dust is also affecting the young population. We cannot put the dust only in the intermediate and young population and adding a young population without the dust. This would be a trick, a mathematical trick, in order to get a fit in your data. But physically, it has no sense. We don't know any galaxy in which the dust is larger near the all population than with the young population, because the young population is associated to star formation regions, and in the star formation regions there is dust. So this is not a physical solution. This is why we have carried out our own analysis, including some stellar population synthesis model, including a standard extinction model, and also including the same data, stacking all the information of the 13 galaxies. We have here the stacked spectral energy distribution coming from the 13 galaxies, once we know the spectroscopic or photometric resin. And recently we have also added some noisy points in the very in the mid-infrared, which are not very relevant, but just for consistency we have added here. The important part is the shape at rest between 1,000 and 6,000 Armstrong. This is the important part for the big part of the Well, doing this week, we get, as I said, that the age of the older population should be larger than 900 million years within 95 orbitals there. An update of this result, I have carried out just an update, including some more recent information that was published this year. Even I can get a stronger prospect, even can be larger than 1.9 gigayears, selecting only few data here and adding the big infrared data. In this analysis, we included only stellar population plus extinction plus dust, and also some star formation that we use some emission lines. Emission lines were included, but we have not included AGN. What happens if we include AGN component? Imagine that we have the galaxy, a hot galaxy, and in the center we have a black hole, which is also producing part of the continuum. Well, we have shown in the analysis in our paper that if the extinction of the AGN is lower than 3 magnitudes invisible, which is quite a large extinction indeed, we should have a very strong flux, a strong emission in far ultraviolet. Far ultraviolet, I mean below 800 Armstrong. Between 500 and 800 Armstrong, the models of AGN produce a too high emission. However, as I told before, our data show no emission in far ultraviolet. So, in case there is some AGN component, it should be relatively small. This was the conclusion that I obtained almost 1 year ago when I did the first analysis corresponding to the published paper that is now in 3 years. More recently, 2 months ago, some paper was published, some paper with the recent information, with spectroscopic information of the James Webb, and they did also some spectra of some of the data. From the 13 galaxies, there are 6 spectra that are available with the near-infrared James Webb telescope, and 2 of them present some emission lines, Wagner lines, which are broad. One of them is slightly broadened, so it's a very small black hole, but at least one of them, 1 in 13 at least, presents signs of important broadening of the Wagner lines. This paper, Juan et al. Have tried to fit this galaxy along and other galaxies, including, again, some stellar population up to 300 megayears in this case, and in order to explain the big Wagner break, they include AGN with a very high extinction, even much higher than the 3 magnitude. This is what we plot here in the left panel. As you can see in the left down panel, which is a magnification of the Wagner rate, this AGN, this red line, has an important contribution for the radiating in the Van break. So it will be a possible explanation for the Van break, and in this case, they don't need a so-called population. With a population up to 300 megayears, it will be enough to explain this Van break. However, and this is the problem that we find. Sorry, no, this not. However, when we read the Vyacheslav analysis, we see that they have used an extinction curve with many free parameters, and in the end, in order to get this strong ADN component, which is not affecting the ultraviolet part, they are using an extinction curve that, as it is plotted here, in the right side panel. The green line, the dashed green line, is the extinction curve used by Juan et al. This is just a mathematical artifact. What they have done is to produce a very, very high extinction, even 100 times larger than the extinction visible below 1,000 angstrom, in order to suppress the possible emission in the far ultraviolet. But this is not, again, this is not what we know. All the kinds of dust that we know from the local galaxy present an extinction as it is plotted here in the black line, the black solid line. Indeed, there should be a hole of extinction below 800 angstrom. This is well known in the analysis of far ultraviolet with satellites in the near universe. So this is the explanation why their data can be used to produce a very important remedy near the boundary rate, but without emission in the far ultraviolet. In our opinion, as I said, this is not correct. This is just a mathematical artifact they have used in order to produce nice fittings with the elements that they have of the standard cosmology. But this is a trick. In some way they are cheating because they are introducing an extinction that has no sense. Sorry, again, this is not the plots. Okay. I have carried out again the analysis of our data, including the new infrared, including the new information about the spectrum with data. And we found that in order to produce a fit of the acceptable fit of the boundary break and the line alpha break and everything, including a population younger than the age of the universe, which is around 600 megayears, 640 or so, we will need a very, very high extinction of the ADN, extinctions larger than 4, and even the fits are worse than the previous one, with dominance of the stellar population, and even so, the age of the other stars, as I said, are rejected to be with the age of the universe within 97 confidence level. So there should be more than 0.7 gigayears. Something lower, the limit of the age is lower than only with the stellar population, but only slightly lower. So still we have a summing up, and this is already finishing. We need some, what is called now, another topic, we need some exotic objects. In order to be in agreement with standard cosmology, we need these little red dots, exotic objects, to be very extincted ADN. But this is problematic because some people have observed this kind of little red dots, and they don't find the variability in far ultraviolet, they don't find detection in far infrared, even in alpha, which is more sensitive, which should be there, they have a lot of dust. They don't find detection in X-ray, and also we have the problem that if they are ADNs, they will be black holes with a massive, much larger than predicted by the external LCDM. So the problem is still a fascinating problem. It's not solved. I have not the solution. The question is that either these objects will be shaped are dominated in the red part by ADMs, and then we have a lot of problems that I have pointed, and even we are in the limit of the age of the all stars to be like the age of the universe or larger. Or the other solution is that the AGN is already a small contribution, but is dominated by a stellar population, and in this case, the stars should be even larger than 700 megayears, or 95% confidence level. Just to finish, my conclusion is that this still is a very interesting topic and a very promising topic, but further research is needed. Remember that these conclusions result from several approximations in stellar astrophysics, in extinction, so they should be taken with a grain of salt. And this is all that I have to say. Thank you.
Professor Zimin from Moscow State University.
Good afternoon to everybody. And today I'm going to speak about the so-called faint young sun paradox. First of all, I'd like to remind you that this paradox was actually one of the starting points of our series of conferences, Cosmology on small scales, which was started about 8 years ago. And now I would like to return the same topic and discuss some new ideas, which we obtained with my colleagues, Elena Krizek and Yurii V. Next slide, please. So, the so-called faint young sun paradox was clearly recognized for the first time in the late 50s, when the sufficiently accurate models of stellar evolution were developed. And the problem that was recognized after that was that, say, 4.5 billion years ago, when the Earth was formed, the solar luminosity was much less than its contemporary value. The first estimate gave the value of reduction about 41%, and the modern value, the modern point of view is it was reduced by approximately 25 or 30%. Therefore, from the view of geophysics, this means that the mean surface temperature on the early Earth should be much less than now. And in particular, the simplest estimate shows that all water would be frozen in the period over 2 billion years ago. But on the other hand, we have a lot of geological evidence for the considerable volumes of liquid water on the Earth at much earlier periods of time. Moreover, we should keep in mind that the low temperature below zero would be very unfavorable for the emergence and development of the life on the Earth. Besides, it was recognized recently that the problem of the frozen water is important also for months, since this removes a formation of the channels on the surface. Next slide, please. So, approximately from 1970s, the faint young sun paradox was recognized as one of important problems in astronomy and geophysics. This was done mostly due to the works by Carl Sagan and Hubble. Among all the possible solutions, the most popular was the so-called greenhouse. The problem back in that time was to keep the surface temperature above the freezing point of water. And the most popular explanation presented at that time was the so-called greenhouse effect. That is capturing the outgoing infrared radiation from the Earth by certain gases in the lower atmosphere. As was shown in a number of papers at that time, under the raw pictures of chemical composition of the early atmosphere, it is really possible to obtain a reasonable range of temperatures for the entire evolution of the Earth. unfortunately, there is of course a lot of uncertainties about the above mentioned chemical composition. Next slide, please. Moreover, the problem of the faint young sun became even more paradoxal in the last 20 years. Because in that period of time, we obtained a number of data of paleochemistry and paleobiology, which show that the temperature at the young Earth might be actually much greater than now. For example, in this group, you can see the most optimistic or extreme values. Here, gray curves show the temperature of the ancient ocean derived from some studies on the deposition of isotopes in the ancient ocean. And black bars show the data of simulations on the formation of ancient proteins. As you see from these plots, the temperature, for example, 4 billion years ago, is estimated to be up to 70 degrees. But in fact, the most of planetologists keep a more moderate point of view that the temperature was really greater than now, but it should be about 40 degrees instead of the modern average value on the Earth, which is 15 degrees. In fact, a much larger temperature should be also suggested at the early Mars, as shown from the recent space studies, which confirmed the traces of the ancient rivers on the Mars surface. This topic was particularly discussed in detail in a large report by Andrei Meider at our conference 6 years ago. Therefore, in fact, now it is necessary to explain not merely keeping a constant temperature on the Earth, especially, for example, the temperature above zero, but actually we need to explain that the temperature was larger in the past, and then it drops despite the increase in the solar luminosity. Next slide, please. By now, a number of various approaches were suggested to solve this problem. They are briefly listed in this slide. For example, one approach is a correction of the solar luminosity of the young sun, which is assumed to have a larger mass, which was subsequently lost, for example, by the solar wind. Unfortunately, this effect, as follows from the quantitative estimates, this effect is rather small. Another suggestion is a reduced elevator of the young Earth. This was actually particularly discussed in the report by Professor Fuller at our first conference in 2016. But as follows from aerobic analysis, such effect, such induction is also insufficient. For example, the elevator of the modern Earth is about 30%. And to solve the problem, it would be necessary to remove this elevator completely. Besides, it was suggested that there might be unaccounted additional energy sources, such as the geothermal flows and dissipation of the lunar tides in the Earth body. But quantitative estimates show that although they can produce some contribution to the balance of energy, but it is not so significant. As I told above, the most popular and widely suggestion to resolve the faint young sun queries is the greenhouse effect, which was suggested by Sagan and Pullen in 1970s. I'll discuss it in more in the subsequent slides. Yet another very interesting suggestion was done about 10 or 15 and Krizek and Fornax. They suggested that this problem can be solved by the reduced radius of the planetary orbits in the young solar system. And then these orbits are expanded due to the local Hubble expansion. I'll also discuss this mechanism below. Next slide, please. Next slide, okay. As regards the greenhouse effect that is given the outgoing infrared radiation from the Earth's surface by certain gases in the atmosphere, it is the most popular mechanism, as I said already. However, it encounters a number of serious problems, and the main of them is that the concentration of greenhouse gases in the ancient atmosphere is strongly constrained by the mineralogical data on the deposition of such gases in the rocks. This is actually the main obstacle to assume a sufficient large concentration of such gases in the atmosphere of the area. However, as was shown recently by my author, Elena Asencio, this problem could be well resolved by the assumption of existence of a thin oil film on the surface of the ancient oceans. Such a film would be well formed even at the prebiotic stage of the Earth's evolution. And next, it provides an efficient barrier for the exchange of the greenhouse gases between the atmosphere and ocean. But so, in other words, the concentration might be very high in the atmosphere, but these gases did not penetrate into the ocean and did not deposit in the rocks. Moreover, it is especially interesting that the same hypothesis of the thin oil film could resolve yet another long-standing problem of the biological evolution, namely a formation of the appropriate absorption spectra of chlorophylls. I'm no specialist in this topic and I'm not going to discuss it in more detail now, but you can read about this, for example, in the paper by Aggarwal, which will be published soon in the journal Solar System Research. At last, I should mention that as regards the factor controlling the efficiency of the greenhouse effect, this might be, for example, the solar activity. The solar activity means the non-thermal radiation of the sun, that is, sporadic fluxes of the corpuscular and hard electromagnetic radiation that are produced, for example, during the solar flares and so on. You can read more details about these issues in the paper by Aggarwal, which is published in Proceedings of our meeting. How can the solar activity affect the efficiency of greenhouse effect? There may be a number of possible ways. For example, the efficiency of condensation of the water vapor can be substantially changed due to ionization of the atmosphere by the harsh radiation. It is one option, for example. And a few other options were also discussed in the literature. So I'm not going to discuss this in more detail now because I'm not specialist in this subject. But you can, if you are interested, you can get more information from the works by Aggarwal. Next slide, please. As I told before, an absolutely new approach to solving the quite young standard operators was proposed about a decade ago by Michal Krizek and Lawrence Solomon. Namely, they assumed that increase in the solar luminosity with time would be compensated by the increase in Earth's orbital radius due to the local Hubble expansion. For example, at the value of the local Hubble expansion, which is here about 0.53 of the intergalactic value, the solar radiation on the Earth, as was shown by Michal Krizek, remains constant with accuracy greater than 1% for the entire period of biological evolution of the Earth. That is about 3.5 billion years in the past. Therefore, as a physical conditions within the so-called ecosphere remained constant just because of the local Hubble expansion. Here you see the corresponding numerical estimate where L is the so-called solar constant, that is the flux of radiation per unit square of the Earth's surface. Next slide, please. I'd like to mention that the concept of the local Hubble expansion can be well applied also, for example, to the description of excessive extension of the stimulus from the Earth, as was discussed in a number of my own papers. Besides, it will be this hypothesis can be applied, for example, for explanation of some other anomalies in the dynamics of other planets in the solar system. The main problem is unfortunately that the value suggested by Vyacheslav I to resolve their faint young sun parents is very different, both from the standard intergalactic Hubble constant about 70 kilometers per second per megapascal, and from the value which is a bit less value which is required to resolve the problem of anomalous reception of the moon from the Earth. This is just the problem which, on which I worked very much before. One option to resolve this discrepancy is to take into account the fact that the global Hubble expansion should be formed both by the dark energy, that is the number term, and by the average contribution from the gas-like matter, as is written in the formulas below. Unfortunately, as you can see from the corresponding numerical estimates, this formulas give us a connection about 50%. That is, this is a reasonable connection, for example, to resolve to explain the local Hubble constant, which is necessary to solve the problem of anomalous reception of the moon from the Earth. But it is evidently insufficient inconsistent with the local Hubble constant, which is required to resolve the faint young sun parameters. So, which is yet another idea how these values can be reconciled and how their solar mechanism can be refined, is to take into consideration a high temperature of the young Earth, which was already mentioned before in my report. Let me repeat that the original idea by Vyacheslav I was that the temperature kept constant during the entire evolution, but actually, according to the recent data, it was higher in the past, and this should give some contribution. Next slide, please. Okay. To resume the attributed solar mechanism, we need to consider the equation of heat balance of the Earth written here. Here R capital is the Earth's radius, K capital is the so-called solar constant, that is the flux of energy per unit square of the Earth's surface. A capital is the algebra of the incoming visible radiation. Alpha is the algebra of the outgoing infrared radiation. T sub S is the Earth's surface temperature, and sigma is the second Boltzmann constant. So, in the left-hand side of this equation, you can see the flux of radiation from the sun encountered across section of the Earth, and on the right-hand side of the equation, you see the thermal flux emitted from the entire surface of the Earth with the correction for the greenhouse effect described here by the coefficient I. Next, we should, in the framework of different processes, we should take into account the fact that the solar constant will depend both on the solar luminosity which changes in the course of time, and on the induced square of the radius from the sun to the Earth, which also increases with time. Next slide, please. Next, if we assume that the local Hubble expansion is formed solely by the dark energy, for example, then the radius of the Earth orbit will increase according to the exponential function with constant parameter 8. And combining the above written formulas, we can easily get either the Hubble constant H as function of the variable solar luminosity A and temperature of the young Earth T sub C given by the middle formula, or it may be convenient to express the Earth's surface temperature as the specific value of the Hubble constant, as is written by the third formula. So, if we perform the numerical estimates using these formulas, we can easily find that if temperature on the, for example, on the early Earth 4 billion years ago was about 70 degrees, then the required potential Hubble constant to compensate the increasing solar luminosity should be about 130 kilometers per second per megapascal. That is extreme relativity. If we take the value of the surface temperature of the area, for example, 40 degrees, then we get the local value of the Hubble constant about 87 kilometers per second per megapascal, which is evidently also rather overestimated. On the other hand, if we specify the reasonable value of the local Hubble constant as, for example, 70, then we can easily find that the temperature of the early Earth should be around 30 degrees. Next slide, please. So, in view of the above discussion, we can draw the following conclusions. First of all, I'd like to emphasize that the faint young sun barriers remains an important problem of both astronomy and geosciences, which is still unsolved convincingly by now. As that was clear, why we discussed the suggestion to solve this problem, as I told before, is the greenhouse effect, of course. Unfortunately, there is a lot of uncertainties in our knowledge about the chemical composition of the ancient atmosphere, and concentration of the greenhouse gases is strongly constrained by the data of mineralogy. However, as was shown recently by my author Kroupa, these constraints can be well lifted by the assumption of an oil film at the surface of oceans, because this film serves as a bridge between the atmosphere and the the second interesting approach is the Vyacheslav mechanism, which is based on the idea of local Hubble expansion. But as I told you in the end of my report, the required value of the local Hubble constant remains rather uncertain, particularly if we believe that the Earth's temperature must be permanent in the course of time. Then the local Hubble constant turns out to be very small as compared to its intergalactic value. On the other hand, if we employ the recent data of paleochemistry and paleobiology on the high temperature of the young Earth, then the local Hubble constant is estimated to be too large. So the situation remains actually unclear. And finally, I would like just to mention that all these conclusions, of course, are very sensitive to a number of ad hoc assumptions introduced in our models. Particularly, this is the term intended for both the visible and infrared radiation and some other assumptions. So thank you for your attention, and I'm waiting for your questions. And you can ask questions not only to me, but also to my co-authors. If you, for example, if you are interested in the hypothesis of modification of the greenhouse effect by the oil field, you can immediately Елизавета Храмова, please, your questions.
Are there any questions?
At first, I sent the organization submitted for this possibility to present my report with my co-author, Konstantin Prokofiev, also from the Institute for Nuclear Research. And we will discuss the problem of the images of the holes, which are all connected to the problem, especially the problem of the image. As you know, one of the problems in cosmology is that we don't have no possibility to verify the applicability of general relativity in cosmology at large redshift, because we don't know the validity of Einstein gravitational theory in strong field approximation, when gravitational potential of the order of the light velocity square, and we will use the light velocity equal to 1, and this is a great problem for verification. In the nearest future, I will discuss that the only possibility to verify the validity of some Einstein theory in a strong field case by considering the source of images of the world. And now I will start. Okay, with my co-author Konstantin Prokofiev. The form of black hole image viewed by a distant observer or some telescope in the cosmological local universe provides indication of the presence of black energy. The specific feature of the whole image is the dark spot viewed on the celestial sphere projected inside the position of classical black hole shadow. I will discuss the problem of classical black hole shadow below. And the form of this black hole spot depends in particular on the presence of dark energy. In the nearest future, it would be possible to search for indication of the presence of dark energy as the images of supermassive black hole Sagittarius are star in the nucleus of our native nuclear galaxy, and the supermassive black hole M87 star in the nucleus of giant elliptical galaxy M87. By observation, this projected International Space Observatory millimeter with a nanosecond angular resolution. So, we start with some short presentation what is the Kern human metric. And the Kern human metric would be throughout all my report. You see the square of the interval and the two important designation are delta large, this one, which providing the event horizon radius and plus and Cauchy radius outside the whole horizon. This is the formula. And the other important is the function omega, which at the event horizon, we see that this event horizon rotates as a solid body, that is independent on the polar angle theta with this angular velocity. And the specific of this metric is that it is stationary, but actually symmetric. And there is some very important presentation of this metric with the form of Boyer linkage. And Bragg and Kroupa provide the famous paper in 1968 years ago, for the 20th century, very old ago, that there are following integrals of motion in this metric. This is mu, the particle mass, the total energy, because the metric is stationary, and A is the particle azimuth angular momentum, because the metric is actually symmetric, and there is specific constant Q, which is called the current constant, and I will discuss this especially below, which defines the non-equatorial mode. And there are two radial potentials, R over radius, and the polar potential will depend only on the polar angle M. And particle trajectories in Kerr-Newman matrix depend in general on three parameters: on the normalized energy, normalized azimuthal angular momentum, and on this square root of constant factor T. For massive particle U equals 0, like suppose there are only two parameters, lambda and Q small. And now these parameters, lambda and Q, are related with the horizontal alpha and vertical beta input parameters of the symmetrical sphere for distant observer, which is placed on some polar angle theta 0 theta observer. This is the formula for relations of these observed real input parameters. These are the parameters in Kerr-Newman theory. The famous paper of Bragg and Carter 1968 contains the equations of motion. This is the great discovery because Kerr opened his metric in 1963, and 5 years the most famous mathematicians around the world cannot obtain the equations of motion. Only 5 years ago, after the discovery of Kerr metric, Bragg and Carter obtained these equations of motion. They have some integral representation here. It is this specific designations. This is from mathematical point of view, is the integrals along the particle trajectory. Tau is the time on the some proper time of the particle. T is the azimuthal angle. T is the time which is absorbed by some distant observer. And now I will explain this integral. These integrals monotonically grow along the particle trajectory. And is the sum of monotonical paths of these these integrals along the trajectory starting from the starting point, maybe very near the black hole, and at the finishing source, which is the telescope. And this is equations for the motion, for the direct motion of from the particle starting very near black hole and reaching this comes over. If there are no some reflection points, and for example, if there is some reflection points in angle theta, so this complex integral has such representation. So this is at left the integral over radius, and at right is the sum of two integrals. First integral is from the source to some theta minimum, the point of reflection is in theta direction, and again the second integral is the integral from this point of reflection in polar direction to observer. We use these equations in our numerical calculations of photon trajectories, starting in the vicinity of Kerr-Newton Newman black holes and finishing at position of distant observer, very far from black hole is the Newtonian digit. And we numerical calculate these equations by using Mathematica as the personal computer. The calculations of this equation, numerical calculations, demand approximately 2 days. After 2 days, computer with Mathematica provides the solution of this equation. If there are more reflection points, for example, like in this case, you see the trajectory, the yellow is calculated with Mathematica, with all trajectories in my report was calculated by using Mathematica numerically, and you see one turning point in polar direction, there's another point in turning point in radial directions, minimal radius, and the second point, reflection point, and after that, photon goes to infinity. And Mathematica provides the solution approximately in 3 days, and this is the solution, which is the parameters of photons lambda and Q, which start here and finishing at distant observer. The blue one, this is solution for direct trajectory, and this magenta one is the solution for the so-called second and other trajectories which are called light errors. Because there are very many turning points in winding around the black holes. There are many large amount of images. Okay, I will go. And then black hole shadow may be derived equations from this simultaneous solution of these equations, parametrical solutions for parameter lambda and Q, and we can provide even the analytical form. And this is the graph for the classical black hole shadow. At last panel, we see the shadows for our orientation with respect to supermassive black holes in our Milky Way galaxy, so GPRs are star. And you see that the vertical size of the shadow is independent of the angular momentum of the hole, and is equals 5.116. as in the case of extremely far-reaching black holes, as of the foreign Schwarzschild black holes. At the time, Pavel sees the corresponding form of classical black hole, showing the case, for example, when spin parameters is equals 0.65. This is the form of the shadow. This is the projection of sky, the black hole rotation axis, and this is the form of the exact black hole event horizon in the absence of gravity, in equilibrium, the space without the gravity. And here, for understanding, you see the numerical simulation of constant spherical probe, very small. For example, this is like our sun rotating at a radius 20 around the very fast rotating black hole. And you see the images of this star in discrete time, winding around the black hole. This is the prime trajectory, and this one, which is very close to the classical black hole shadow, is the first solar echo, and the more close around the black hole shadow is the second echo. And now I will try to see for you the cinema with this presentation. You see the cinema?
Yes.
Do you see the cinema?
Yes, yes.
I know here.
Yes,
Results with someone. You see?
yes, we do. Can I? No, zero.
Yes, I will try how to do this. How to do this. I'm sorry, fine. You don't see the material, yes?
Black screen, I use black. But it doesn't move.
Okay, let us resolve the cinema. I will close it. Okay, never mind. I will return to my report. Okay. Okay. In any case, you see them moving along the trajectory. You see that there is redshift and Doppler redshift, because at this point star will moving along the trajectory in direction opposite to the position of the observer. And left, you see again the blue shift, because the stars coming and moving towards the Earth, and this pictures take into account only also the gravitational redshift and the modifications of form of the star, not because it's the tidal deformation, but due to deformation in the strong gravitational field. Okay. Okay. It would be possible to reconstruct the silhouette or image of the event horizon of the black hole event horizon for The case here, so orientation with respect to black holes, trajectories are when observed placed a little bit above the equatorial plane of the black hole rotation, and the nearest hemisphere of the event horizon is projected in the light colored part of this picture. And this is magenta. This is the inner part of the classical black hole shadow, which is projected on the celestial sphere but is invisible. And inside of this shadow, you will reconstruct the form of the whole globe of the black hole horizon. For example, you will find the trajectory starting from the very, very near to the North Pole, coming to the distant observer. And point this again as the North Pole. The same from the South Pole. Again, I remind that all these trajectories are numerically calculated in computer. And you see also the trajectory starting in equatorial plane of the globe of the event horizon, and one trajectory coming here in this part, and all is coming throughout there. One minute, please, 1 minute.
Where is he now? He left the room.
I am very sorry for interruptions. I will go on. And the dark blue is the dark side of the globe of the event horizon, and you will also track the meridians of this image, and you see that you see the black hole event horizon from both sides. The dark side, which is directly outside of the position of the observer, and the nearest hemisphere. Okay, classical black hole shadows provide some example which is verified in recent observations of the supermassive black hole M87 star and the Sagittarius R star. And these observations qualitatively said that Einstein's theory is valid from the qualitative point of view, because very poor resolution of the event horizon telescope, which had the angular resolution a little bit smaller than the event horizon size. This is example of some 3D picture of the orientation of supermassive black hole F87 with the proposed in parameter x of 1 surrounded by spin accretion piece, with this accretion piece, which is supposed to be non-transparent, that is, not the spin. And the largest closed curve is the outer boundary of the classical black hole shadow, the purple one. And two numerical calculated Platon trajectories are started from the inner boundary of the accretion disk in the vicinity of the black hole event horizon equator, and finishing far from the black hole position of the distant observer, and inside of this black curve you see the black spot on the image, which absorbs the event horizon. This is a composition of the event horizon telescope image. In the case of the observation of supermassive black hole, our Milky Way center, with a numerical model dark spot corresponding to the gravitational length image of the event horizon globe with spin r equal 1. This is black spot. It's very far away from black hole. The closest part of Earth is the outline classical black hole shadow. Classical black hole shadow, which is invisible, but this image of black hole is projected inside of the classical black hole shadow, which is invisible. And magenta arrow is the direction of the rotation axis, and this is the cycle. Magenta cycle is the form of the event horizon of this black hole in the absence of background in Euclidean imaginary space. The form of this black spot, in the case of structure, may be calculated even in part analytically. You must calculate these equations, and these equations, in this equation taken into account as the turning point, second minimum, which is this expression, and the right-hand side integral with this, the second minimum equals to this values, and the resulting numerical solution of the integral solution with this value of right constant integral is the radius of the event horizon, which is this one, and which is 4.457 in the case of Schwarz. And now in these figures which I demonstrate you, we show the numerical solution for the gravitational branching event horizon images in the case of Schwarzschild and in the case of extremely far rotating black holes when spin equals 1. In the case for the black hole in our Milky Way galaxy. And what is very important that the event horizon globe of the black hole is rotating with the angular velocity as a solar body. This is angular velocity. The other figure, this figure represents the similar one pictures this superposition in the case of supermassive black hole 87. In the case of spin equal 1 and spin equals 0.75. In the case of event supermassive black hole M87 star, the dependence of the black spot with very small with respect to the spin. Because so it is very, this is depends on the inclination of the black hole. It is very difficult to set what is the spin of the hole in the spin. And here you see the gravitational length image in discrete time interval of some probe cosmic ship, for example, a neutron star, for example, emitting gamma or again gamma quanta, which is moving with a zero angular momentum in the equatorial plane of the black hole and plunging into fast rotating black hole. In the case of Schwarzschild black hole, this would be a direct line coming plunging into black hole. But in the case of fast rotating black hole, when this plunging through, approaching to the event horizon, it must start to rotate with expected black hole rotation. And this is the form of this star in discrete time by taking into account the deformations and Doppler shift and redshift. And you see here that there is the red shift at the right part and there is blue shift. And you see this images in discrete time. It must be said that when images going around the black hole with low event horizon equatorial plane, the flux is very small, approximately 10 orders smaller than the direct image. This is very intriguing and very interesting situation, and this some radiation, the flux will diminishing according to the equations of motion exponentially with time. And my discussions and conclusions, the possible form of black hole images viewed by a distant observer are calculated here based on general relativity and equations of motion in the gathering geometry. And black hole image is a gravitational length image of the black hole event horizon itself. Images of astrophysical black holes may be viewed as black spots on the celestial sphere projected inside the possible position of classical black hole shadow, which is in astrophysical conditions are invisible. And it must be stressed that the form of discussed black holes are independent on the distribution and emission of the gated plasma, and instead of the corresponding form of black holes are completely defined by properties of black hole gravitational field. And what is following from this? From this is following the last conclusion. In the nearest future, it will be possible to verify modified gravity field by observation of astrophysical black hole with international millimeter spray observatory with a nano-arc-certain accuracy. Thank you for your attention.
I'm grateful for organizers for letting me talk here. Nonlinear partial differential equations for systems advance unknown interactions. There is a problem with singularities of solutions. It's believed that general relativity stops working near singularities, and another quantum theory of gravity is needed. In absolute parallelism, there are four classes of compatible second-order equations of Frank field, Vyacheslav I, and only one exceptional equation, non-tangent, apparently free from singularities of solutions if d equals 5. The Brownian symmetric equation gives a four-pocket gravity with corrected stress-energy tensor. It follows also from the Lizard action principle. The cosmological model of expanding brane universe appears in this theory as a spherical symmetric single longitudinal wave acting as an optical waveguide for almost tangential waves of different polarizations. Well, special relativity unites space and time, also electric and magnetic fields, but does not explain the existence of any field of particle. General relativity relates gravity to space-time curvature, but the other field particles remain unexplainable. Einstein was not content with general relativity, and later he explored the frame field, a symmetric of square matrix. And here the quadratic form the magic, and eta b is Minkowski magic. And second order equations with which symmetry unites symmetries of both special relativity and general relativity. Here's the total symmetry group, including global scale transformation. Lorentz group acts on Latin indices and coordinate diffeomorphism on the Greek ones. While its net shows trying to split environments into yet smaller parts, as Einstein put it a bit solemnly, an intellectual looks at the world through a microscope. This process of division, at least in imagination, ends if we reach indivisible further parts. There are points that should form a sort of continuum. As Einstein said, abandoning continuum is like trying to breathe in an airless space. Newton was sure and intellectual. He even manufactured magnifying glasses, hence Newton's rings. And Newton proposed the simplest picture he could, that there are just two types of points, empty and rare material points. A couple of centuries later, fields appeared, electric and magnetic, Maxwell's equations and special relativity, and the points seem to become infinitely diverse. However, there were problems with gravitational field in special relativity. Normally, general relativity across space-time let bodies of different masses move in the same way along the basics, as Galileo had found in his experiments on the Pisa Tower. The new peculiar symmetry of GR, general covariance, pure group of diffeomorphisms, means that in vacuum GR, any 2 points per set in zero jets are indistinguishable, because the metrics can be made equal to the Minkowski magic. Sure, if these points are regular, not singular. Instead of quantometric G mu arc, we can use minus of cometric. These are multilinear expressions like the determinant. And vacuum GR equation can be written in this way, where this is the current 3 minus of cometric, and R is the Riemannian Cauchy tensor, which is, and this index is linear in first derivatives. And so the regularity of principal terms holds for one degenerate frame, for metrics. In absolute realism, almost all equations also remain regular for one degenerate frame matrices, cross singularities. There's only one exception, the exceptional equation. This equation does not limit dimension 4, and we should choose d equal 5 for the absence of other sort of singularities, converse singularities. In absence of singularities, the Hegel's thesis that being is identical to non-being can be formulated in a bit more concrete form, that in a point in zero chess, while we do not go to vicinity, all points are identical. Points of being or non-being. A single compatible equation of absolute parallelism looks here, where lambda is free-rank tensor, schizometric and 2 indexes. The use of semicolon is the usual covariant differentiation with symmetrical connection. And this identity ensures the compatibility. The linearized simple equations, and this is evident lambda identity. Square bracket is total skew symmetrization. Well, a linearized equation looks as a default Maxwell system. So the number of polarizations, degrees of freedom is d times d minus 2. And this is larger than the number of gravitational wave polarizations. The other divergence, if you differentiate a contract different way, gives a Maxwell-like equation. This contracted lambda identity, and this current should be consolved. This is the other identity necessary for compatibility, and according to the theory in the book by Pomaré, this identity should be automatically valid. And how to check and explain this? Any p-secondary equation can be separated on symmetric and skew-symmetric part. This skew-symmetric S is totally skew-symmetric part of lambda tensor. This is symmetric part where we separate the Einstein tensor, and here the other linear term. This was part at differentiation, the divergence give two Maxwell equations, which currents should be identical. Otherwise, we arrive to a new irregular first-order equation. But this current is trivial because it's divergence of the skew-symmetric tensor. It's so evident that the conservation of this current is automatic. Evidently, the only exception is tau equals 0 and sigma not equal 1. And there is the only non-Lagrangian exceptional equation. And current is trivial too, and yes. Note that this simple equation also admits singularities, and the principal terms can be written in a polar linear form using 2 minus of full metric. Yes, and this is the that exceptional equation can be written in this form where L is skew-symmetric in 2 indexes, mu. And the trace part of this system loses principal terms if d equals 4. The other quadratic terms do not vanish, so this becomes irregular first-order equation. So d equals 4 is forbidden, and we should choose dimension 5, d equals 5. This is a skew-symmetric part. It's very simple, just divergence of tensor S, and this is symmetric part. And here we have linear terms. So the problem with the energy momentum tensor, it's not this positive energy, but the correct stress energy tensor appears in Prolon equation, fourth order of this form, where T mu F is of electromagnetic form, on F components contribute to energy momentum, and tensor B has images of the remaining tensor, and these terms give no contribution to d momentum or angular momentum. It's important that this equation admits solutions with F equals 0, because the current here also vanishes if F equals 0. Compatibility keeps. But these solutions with no energy are of 0 measure. Some interesting features of this exceptional equation are not stationary. Explaining spherically symmetrical solution can look as a single longitudinal wave in splitting gas, no gradient catastrophe. Other polarizations do not survive with symmetry. This wave conserves the cosmological shallow waveguide for tangential short waves. And heating polarizations, d equals 5, differ in amplitudes very much, on many orders of amplitude, and functions, and we can separate 4 classes. Differentiating the lambda identity, we can arrive to this evolution equation for lambda tensor. The Lamberian and here the linear terms. F waves serve as a resonant force for linear growth of 3 unstable, linearly unstable polarization, which are from zeroth class. And longitudinal non-gradient symmetry for vector 5 and 3s polarization belongs to the first class because the source currents depend on lambda square terms, where zero class polarization take part. On this and this one, this is the skew symmetric, totally skew symmetric part of lambda identity. And this is skew symmetric part of it. And F and gravitational vectorization belong respectively to second class F polarization. Here the current depends on first class and second class, and to the third class. Its gravitational waves are more strict, and the generation is provided by energy momentum, like in the general relativity, but situation is a bit different in the scale, traditional scale, very different from this natural one, which depends on very small polarization, which only contribute to energy momentum, F waves, second class. Interestingly, Landau in his classification of physicists used logarithmic scale, and to zero class he placed Newton, Einstein, a few other, but he placed himself to the second and half, and later to the second class. We see that here the second class polarization are very important because they're the source of growth of nonlinear polarization or unstable polarization. And nonlinear localized field configuration can carry digital information, topological charges, and for symmetrical configuration, quasi-charges. One can deform metric to an impulse Q1, and hence the frame field to a field of rotation matrices. Both also can be removed, and the topological charge group pi x pi 1 no symmetry is pi 4 is absolute homotopy group. Pi 4 of SO4 equals Z2 plus Z2. One can parameterize the group SO4 with a pair of unique quaternions. One act on general quaternions from left, the other conjugated act from the right. And with accuracy to the total change of the sign, plus minus. The symmetry of cosmological background cosmological wave is this one, or 3 times inversion of all coordinates. And white particle corresponds to symmetries, which is a subgroup of this cosmological symmetry. For example, cylindrical symmetry gives this topological quasi-charge group. SO3 symmetry gives zero quasi-charge group. That means that elementary particles with spin 0 are absent. One can add discrete symmetries partially in the following way. For color quasi-particles, one should remove group SO2 with sub-dual or anti-sub-dual groups SO plus 2, SO minus 2, which contain where one quaternion is unit. And many features of the standard model of elementary particles can be understood in this way. A phenomenology looking like a quadrature theory can emerge through averaging along the huge extra dimension, the length L bits of cosmological wave. And we need auxiliary four-dimensional field, quantized avatar field prone to superposition, because F waves responsible for energy momentum are almost tangential, for phenomenological counting topological quasi-particles. Well, the proper strategy tensor, where all the polarizations play the role, appears in the prolonged fourth-order symmetrical equation, this one. So we have a fourth-order gravity. And this equation can be derived from Lagrangian, which is quadratic in the very equation, symmetric part quadratic. excluding the total derivative. It's hard to go along. Yeah, I don't understand. The scale is a solution parameter, and L reduces with the Planck length while multiplying by a tiny factor related to amplitudes of Earth waves. A variation of this term gives this tensor, which divergence is identical to 0. Variation of this gives this one, and variation of this gives this 0 terms. In main quadratic terms, okay. Well, and we can well, the Lagrangian of four-dimensional general relativity can emerge as approximation in this form where Q is the scalar curvature of cosmological solution. It depends on the amplitude, which can be of different sign, of proper sign, and on the thickness of this wave, single longitudinal wave. Well, so one can consider for the equation of Laplacian squared, I missed the slide. Important thing that here the connection to Newton force can start with a regular term, but we can vanish it by arranging A and B to some relation. And then correction starts with quadratic term. And if we take into account the second order equation, Laplacian phi, and here quadratic lambda squared terms of waves of 0 class, they should rearrange somehow near a massive body. And this arrangement is smaller if we vanish the regular term. But this means that parameter A is not 0, and at large scale we should have asymptotic 1 over R. This is calculation for some modeling distribution along the extra dimension, and the scale L is taken as the unit, as 1. Okay. It seems that L should be about a few kilo AU, anomalies in wide binary data, and some of it. Well, and in paper and proceedings, you can read this formula, a model of shallow waveguide, and you can describe the motion of mass M in relativistically expanding brane by this simple Lagrangian, because deviation from cosmic space is not large, quite small. Caps letters relate to absolute observer in the center of the sphere shell, spherical shell, which our brain is expanding. And small t and phi are t relates to observers of the brain, commoving observers. At rest, their relative radiation is isotropic. And it turns out that the brain radius, B caps, T caps, much larger than the current time, by the factor gamma, one spectrum of expanding brain. Yes. And this is a sort of detailed coordinates. We can consider this decomposition in series. Note that first the terms form full derivative, which doesn't matter. And first the correction proportion to the Hubble parameter is further correction. Yes. Velocities in the solar system are quite small, but there are stars which orbits the very massive supermassive black hole, Sagittarius A star in the center of our galaxy, and their speeds about up to 5% of the speed of light. And somebody says that call these stars forever young. Say that they somehow think new methods, new hydrogen, and they suggested that this is absorption of dark matter particles near the center, which convert to ordinary matter. But some people doubt the existence of dark matter. Also, we know about quasars, which generates perhaps also new baryons, much more energy. I miss this, skip this. Artyom Astashenok. One can assume, this is a picture illustrates the spherical shell explaining relativistically. One can assume that during partial cataclysm, a new quasi-particle generated, but topological charges generating can appear in pairs as charged particles should be closer to the slope of the brain. So maybe some topological perturbation can leave the brain, and this arrows show the photons moving in the brain, and those perturbations leave the brain inside, can further intersect it and change and break the symmetry, and maybe produce some transformation, generation of new quasi-particles. This simple equation for estimation of Z in my paper and proceedings. So I now switch to these guys. A number of authors, geologists, engineers, suggested that our Earth is growing. As Vitaly Grinov, his paper, reference in my paper, Vladimir Vlavin, also his paper, he suggested, following the ideas of Fred Hoyle, that our Earth captured many hydrogen, and Earth's core, inner core, is from metal hydrides and of very large density, about 20 grams per centimeter cubic centimeter. And after decomposition, the density decreased and our Earth grew. But still there are some indication that mass also should grow. And this is Ivan Yarkovsky, who in the end of 19th century suggested that the celestial body can grow through absorption of ether in regions of high gravity. And this is Anatoly Chirikovsky. He has a few videos on YouTube, and Giancarlo Scalera and his book on the subject. And a few pictures to see the map of ridges, ocean ridges. And this is the map of age map of ocean floor. Only tiny regions of old ocean floor, which is over continental crust, not beneath, and sediments, and so. And this graph shows the distributions of ocean crust on age, and we see the exponential growth. You see appearance of new ocean crust near Atlantic edge, the velocity about 2 centimeters per year, and much more velocity wider Rex brand in Pacific. And this is this place where rich go to Iceland. Well, it's other Africa has one ridge from one side and the other ridge, but still Africa is breaking in Great Rift Valley, upon depression, going to the Red Sea. And this is the data of gravity increase, a free fall acceleration, where gal is centimeter over s squared. Well, and this picture from the site hydrogen future, and this is a sort of hydrogen jets, and their appearance, they are just forests, and here real structure with a storm and fallen trees 2 years later. Very fast processes. Well, and then the last slide is that motion of photons in expanding brain is very simple. This equation, we can integrate it and find the Milne diagram, or the Hubble diagram, which can be compared with the Milne diagram. This one here, the plot, and green balls is this plot. Well, discovery of optics, this large Z by James Webb Space Telescope, for some challenges to standard technology. Many authors give preference to models in which the scale factor grows linearly, like in the cosmology I was talking about, so-called Austin cosmologies. Some people, including Fuller Melia, with his RH equals CT universe. In this model, the universe redshift about 12 has sufficient time, about billion years. And perhaps the growing Earth and other growing things, eternally young stars in the center of the galaxy, require some process of appearance of new baryons. And I hope that the theory I was talking about can give some insights in this direction. And thank you for your attention. This is a new monument to Newton, and pedestrians can feel the weight of this monument within this river. Thank you.
My talk is devoted to evolution of perturbations in the model of size holographic dark energy, and I start. 25 years ago, it was discovered that the universe expands with acceleration, and this required a new company in the universe called dark energy, which has now Dear colleagues, I can you are see my presentation and help me?
Yeah.
Or no?
Yeah, we see your presentation.
And help me. And help me with my voice.
We can hear you. We can hear you. We can hear you, and we can see your presentation.
Yes. This accelerated expansion requires a new component in the universe called dark energy, which has low density and only interacted with gravity. The simplest way to model dark energy was to use Einstein cosmological constant or vacuum energy. This resulted to the so-called ΛCDM model, which is a standard cosmological model today. Despite of the good agreements with observational data, this model has some problems on the theoretical level. First, there is a problem of smallness of cosmological constant
from consideration based on quantum field theory, it follows that vacuum energy should be approximate to the Planck value, which dramatically contradicts to the observation. And secondary problem is so-called coincidence problem. Why is current matter density is close to the value of vacuum density? There are other classes of dark energy models, such as holographic dark energy, which are based on the holographical principle from black hole thermodynamics and string theory. This principle states that there is a connection between the infrared cutoff of quantum field theory and the largest distance of the theory. From the cosmological viewpoint, it means that everything in the universe can be described by some quantities on its boundary. And we start from basic equations. In initial model, the density of holographic dark energy is assumed as equation 1, where say is a constant and L0 is some scale, and for L0 the different choices are proposed. The simple variant is the Hubble horizon. Another possibilities include this particle horizon or Yurii horizon. And the last possibility is physically natural and agrees with the observational data for cosmological acceleration. We consider this choice in our work. For universe with Friedmann limiter of Robertson-Walker metric, I'm sorry, we consider the some modified model of holographic dark energy, which is based on formula derived of size for entropy of black hole, where dark energy density is assumed equation 2, where some parameter gamma is introduced for classical model of holographic dark energy. Gamma is equal to 1, and we can consider another values of gamma. Gamma is so-called non-additivity parameter. And for universe with well-known Friedmann limiter Robertson-Walker metric for flat space, Friedmann equations take the following form. We use natural system units as usual. Rho m means matter density. We neglect radiation density because we don't consider far past when radiation is dominated. And we considered therefore universe field holographic dark energy and matter. We also had the well-known equation for matter density. This equation is so-called continuity equation. And solving this equation and equation for L sub 0, we can obtain evolution scale factor with decline. But we consider first evaluation of possible perturbations of dark energy, and the main difficult for any dark energy is problem of that square of sound speed of fluctuations of dark energy is negative, and therefore perturbations of dark energy are unstable. And for holographic dark energy, at first glance, this conclusion is valid also. But one needs to account that holographic dark energy is given by the scale horizon of future horizon, and therefore perturbations of dark energy should be considered globally. For simplicity of our analysis, only scalar perturbations of matter are considered, and therefore we use in Newtonian gauge we have the following expression for metric equation 6, where function phi depends not only from time but also from radial harmonic coordinates. The physical distance for horizon from observer located at 0 point of R is given by equation 7, where L small is the coordinate distance to the future errant horizon. This equation 8, and L sub 0 is common unperturbed distance to errant horizon. From this equation, we can obtain the fluctuation of the future errant horizon for observer located at 0 point, and use equation using equation D. Using equation 9, we can obtain corresponding fluctuation of holographic dark energy density. This equation 10. And now we can consider standard equation for function phi, equation 11, and we can solve this equation. For simplicity, we will analyze the solution of equation 11 all 8 times when dark energy dominates, and one assumes that fluctuation of matter density is 0. We use the following expansion for function phi. We using agent function and represent spatial part of function as function sinus. And after substances in equation, we can obtain the following equation, very huge equation for function phi sub 0k. This equation for function pk should be solved with equation for L sub 0 and Hubble equation. Firstly, we consider perturbation in the case of Tsarist holographic dark energy without interaction between matter and dark energy. For gravity, we omit index k from P. Our calculations show that the dependence of P not significantly depends from value of k. And from calculations, we can see the following features. On this picture, we can see evolution of perturbation in units of initial value at current time, some initial value p sub 0, and we see evolution as function of scale factor on left panel for c is equal 0.8, and on right panel for c is equal 1. And we consider various values of parameter gamma. And it can be see that for c is equal 1, perturbations drop down, or gamma is less than 1, but for gamma is greater than 1 after some growth function here synthetically tends to the constant. Our analysis shows this possibility. There is no another picture demonstrates the same for C is equal 1, 0, 2 for various values of parameter gamma. And we can see there is no unambiguous dependence between value of gamma and growth of perturbation for C less than 1 and C greater than 1. It can be seen that for gamma greater than some value, the growth rate of perturbations decreases. And numerical population allow to conclude that in some interval of gamma, perturbations grow infinitely for C which is less than 1. And the critical value of gamma for this C depends from value of C. Now we turn to the Polar equation and consider contribution of matter perturbations to this evaluation. Possible evaluation of scalar perturbations deserves to be studied not only at its current stage, but in its distant past, because in distant past the contribution of matter is huge, and therefore we cannot neglect it. In this case, one needs to account perturbation of matter in right-hand side of equation, corresponding equation for P. The following additional term in equation for P is equation 40. And assuming that for relative rotation of matter, the following representation is valid as for function P, we can obtain the modified equation for metric perturbations. We need to add to this equation for relative fluctuation of matter density. It's the following equation on slides. And we, in this consideration, for this equation, we neglect perturbations of dark energy expression for A and S, and assuming that this value, this function, takes relativity simple form. And we investigate evaluation of matter density and corresponding metric fluctuations from early times when initial scale factor is smaller than current scale factor 100. And we take the following initial conditions for relative matter perturbations. And one needs to account that there is no scale invariance equation for metric perturbations. And for illustration, we take the following initial conditions for P. And we can see the following results. We integrate equations from initial R to distant future when R is tens greater than current value. And we found P's at current value of scale factor and consider the relation as function of redshift in past and as function of scale factor in future. And we can see the following results. We see that the evaluation of major perturbations doesn't depend significantly from parameter C in this case. But value of non-additivity parameter affects considerably on synthetical value of relative major perturbation on large times. On this picture, we can see evaluation of major perturbation in past left panel as function of redshift and in future right panel. On this picture, the corresponding evaluation of major perturbation is given for past and future. And we see that relative major perturbation tends to constant, and this constant is depend from non-additivity parameter. The same, but for C is equal 1.2, we see in principle the same picture. And in conclusion of my talk, I consider observational data for sigma 8 at very small. We can obtain from redshift space distortion measurements the factor F sigma 8, which is defined by equation 19. For considered cosmology, we need also rescale the results with respect to assumed distributional cosmology. For this, the Popachinski correction factor is used, equation 20. dA is the angular diameter distance, the standard abbreviation. And we consider the following equation for major perturbations, where A is dimension as Hubble parameter. And we use the data compilation from various sources. For this compilation, we can see the following work from physical D. And we calculated the square parameter for statistical analysis. We count that the sigma A data are not dependent from current Hubble parameter. We use 66 points for various redshifts. Some details which is not and results of statistical analysis are given in table. We see that for C is greater than 1, the data for major perturbations is described slightly better than in comparison with standard cosmological model, but the difference is very negligible, of course. For C is less than 1, the concordance with observational data is worse in comparison with the Syrian cosmology. And I go to conclusion. For illustration on this picture, one can see dependence of sigma 8 data on redshift for best value of C from considered values, and for some values of gamma in comparison with LCDM model. We see that dependence from holographic dark energy model is very close to LCDM, but some deviation for Z is greater than 1 take place. And then finally, I give some conclusion. Evaluation of major perturbation doesn't depend significantly from parameter C, but value of non-additivity parameter affects considerably on the synthetical value of matter perturbation on large times, or smaller values of gamma, the limit for matter perturbations decreases. Evolution of matter perturbations significantly changes in comparison with case when we neglect matter perturbations. For all values of C matter fluctuations freeze with time in future, but the growth of fluctuation depends strongly from non-additivity parameter. And the dependence of sigma E data is very close to that in standard cosmology, but some deviation takes place only for large redshifts. So there is no significant difference between models with various gamma or given constant sigma. Thanks for attention.
Okay. Good afternoon again to everyone. So my second report will be more closely connected to the traditional cosmology. Its title you can see here. Can the quasi-oscillatory structure of low multiples in the CMB spectrum be associated with the domain structural record? Next slide, please. So, of course, all of you know that studying the temperature fluctuations of the cosmic microwave background became now a powerful tool for testing the cosmological models and deriving the basic cosmological parameters. However, while the spectrum harmonics at the sufficiently small angular scales, that is, large scale, are well explained by the irregularities of matter distribution in the period of recombination at the so-called surface of the last spectrum, and a perfect agreement between the theory and observations was achieved, as you can see in the figure here. A much worse situation takes place at the larger scales, at very less than 30, for example. One can see here considerable deviations of the theory of the observations from theory, and which are especially significant for the lowest multiples, approximately below 10. And moreover, you can see here some kind of oscillatory behavior, which is shown in the right upper corner of the figure. Next slide, please. As it's known from mathematics, considerable oscillations of amplitudes of the sorry, there is a request to share the screen, but it's not mine. I cannot do this. You should ask Aganestis. So, as you know from mathematics, considerable oscillations of amplitudes of the Fourier harmonics in general are a manifestation of the sufficiently sharp jumps in the original spatial distribution of the respective physical parameters. Therefore, it is reasonable to assume that the above mentioned anomalies in the CMB spectrum might be just an imprint of the domain structure of the physical vector, which is expected in some kinds of the elementary particle series with a spontaneous symmetry gradient. Next slide, please. Since, of course, we do not know detailed characteristics of the underlying scalar field, for example, Higgs field, which commonly appears in the elementary particle theory, we cannot formulate any quantitative relations between the values of the scalar field and the amplitude of the resulting electromagnetic fluctuations in the CMB spectrum. However, we can make a very general assumption that the electromagnetic perturbations depend monotonically on the values of the scalar field in the symmetry broken phase. And then the large-scale geometric structure of the microwave background should be some kind of imprint of the spatial distribution of the domains. This is illustrated in the figures here. So you can see that the domain structure of the scalar field is transformed to the electromagnetic fluctuations by some transformation function f greater. We do not know this function, but we can assume that it is monotonic. And then, although we cannot say, of course, anything about the amplitudes, we can conclude that the positions of maxima and minima will be the same. That is, the pattern of electromagnetic CMB fluctuations will be some kind of imprint of the respective variations of the scalar field. Next slide, please. Now, let me remind some fact about the topological details. As regards the simplest case of such details, that is domain groups, they are commonly formed in the field theories. For example, the particular scalar field theory possessing a discrete symmetry group and whose Lagrangian includes the non-trivial potential term with 2 minima, for example. And then such field in the high temperature phase is symmetric, but when the temperature of the universe drops down, the field relaxes to one of the symmetry grouping phases, either plus, for example, or minus, as shown in the middle curve. And since this relaxation takes place independently in the remote spatial variations, the values of the field in general should be different, and there will be some transition regions between such domains shown here by the green lines, which are called the domain groups or kings. So as a result, we get the pattern of domains with different vector states, as is shown on the right. Let us mention that emergence of the domain structure of vector was predicted by Bogoliubov approximately in 1964-66. That is just after the appearance of the first elementary particle models based on the spontaneous symmetry breaking, such as the electroweak theory by Weinberg, Salaman, and Bletchley. A detailed mathematical study of the relevant issues was subsequently undertaken starting from the middle 70s, first of all, starting from this paper by Hubble, and discussion of the domain rules in the cosmological context was initiated by Zitovich, Klopfer, and Kroupa. At last, I should mention that study of temporal dynamics of the domains was started in the paper by Zurich scientists. Next slide, please. It is another type of the topological details, which is discussed even more frequently, asymptotes of strings. They are formed in the case where the field is complex and therefore possess a continuous symmetry group. Again, with the same kind of Lagrangian with the non-trivial potential term, but in this case, this potential depends not on one value, but on two variables. And as it's written, as it's drawn in the left panel. So, while the field again is symmetric in the high temperature phase, in the low temperature phase, we get its relaxation to one of the symmetry broken states with different phases, as shown in the left panel. And but in the case of continuous symmetry group, such a domain structure with various phases is unstable, and finally, it relaxes to such type of the topological detail as the string shown in the middle. It should be mentioned that in general, the string groups should also affect the spectrum, and this topic was widely studied in the late 90s and early 2000s. But you should keep in mind that the string groups tend to shrink during the cosmological evolution and thereby attack the spectrum at the smallest stage, that is the large molecule. And in the books we formed about 25 years ago, it was shown that the effect of the spin groups of the sufficiently in the same spectrum and the sufficiently large multiples is rather small and in general insignificant. As distinct from the next slide, please. As distinct from the cosmic strings, the lattice of domains expands with the Hubble range and thereby affects the CMB spectrum at the largest scale, that is the lowest multiple. Here, the symmetry breaking phase transition occurs well before the recombination. The corresponding correlation length shown in this conformal diagram should be much greater than the correlation length formed due to the plasma irregularities, which develops evidently already after biogenetics. So you can see in this diagram that the red triangle formed, for example, after the baryogenesis is sufficiently small as compared with the black large angle triangle compared of perturbations compared after the phase transition. So the characteristic length of perturbations caused by the symmetry breaking phase transition should be much greater than any perturbations formed after the period, after baryogenesis, for example, already during the plasma recombination. Next slide, please. Starting from these ideas, we can perform the following empirical estimates of the number of domains in the observable part of the universe. As was shown in the plot with data of the Planck satellite, the most pronounced low multiples in the CMB spectrum are 3, 5, and 7. Then it is it can be clearly understood that the number of domains and domain groups in a typical one-dimensional cross-section should be 6, 10, or 14 respectively. And then we, from the quantitative geometrical relations, we can find that the number of domains of the entire sphere of the last sketching should be, for example, 3, 8, or 16, and the number of domains in the entire observable volume inside the sphere of the last sketching will be given by these numbers for 17 or 46 respectively. Well, in fact, this is, of course, it's quite trivial empirical estimate. Next slide, please. A more important additional question is, of course, how much is the probability of formation of the domain groups and the respective peculiarities in the CMB spectrum. To answer this question, we can consider the simplest two-dimensional model in which the sphere of the last sketching of electromagnetic radiation is reduced just to the surface of the last sketching, as shown in this figure. For simplicity, we assume also that all segments of this circle with different vacuum states are of the same size, while the domain groups are of zero thickness. Besides, we should take into account the energy E concentrated in the domain groups, since the probability of formation of the group in general should be suppressed by the Gibbs factor, written here, exponent of minus E over T, where T is the temperature of the phase transition. And the effect of such Gibbs factors should take place if a sufficiently long interval of the conformal time preceded the phase transition, so that the entire state of the field was well thermalized. So in this approach, you can see the results of simulations. Our simulations where we calculated the average amplitudes of the Fourier harmonics, which were formed in the above-mentioned model. So different colors show the cases of different ratio, E over T, ratio of the domain of the energy to the phase transition temperature. Of course, when the energy of the domain is sufficiently large, the Gibbs factors will suppress all the domain groups. And this situation is shown by the red and magenta line. So in this case, actually, there are no domain groups in the low part, low multiple part of the spectrum, and we have a cut maximum at equal to 0. However, when this ratio E over T is not so large, for example, 0 or 0.51, we can see a rather pronounced peak. By the way, it is interesting that at the first sight, it seems that the amplitude of this peak should decrease monotonically with increasing this ratio. But because the gives factors should suppress formation of the domain groups. But in fact, in the simulations, we got a quite complex interplay between the increasing statistical weight of the configurations with the non-trivial domain groups and the separation by the gives factors. As a result of such competition, it was found that, in fact, the peak becomes most pronounced not at 0, but at some value of E over T about 2, as shown in the plot. Sorry, next slide, please. Here is the plot. The plot I'm thinking about is every entities of the harmonics. So, red magenta cross, okay, show the case of complete separation, and okay, I finished. And the blue curve show the case when the peak is most pronounced. So what is the main idea of this plot is that compared to the real 3D simulations, but it can show that in principle formation of the additional peak due to domain groups and low levels is very possible. So here are discussions and conclusions. In fact, I would like to repeat that in the first part we just performed some empirical estimates of the domain groups in the global part of the universe. And in the second part, we used the simplest leading model, which illustrates that the probability of formation of the additional peak can be really quite large. Thank you for your attention. Excuse me for time limit, but I started 5 minutes later. Thank you very much.
Good afternoon. I'm going to deliver a presentation on the topic of science theoretical energy model and the theoretical data. First, I'm going to talk about how Fornax principle applies to dark energy, but Professor Astashenok has already discussed this issue, and I use it. Then I will make some notes on observational data. We examine the physical of the universe field with the Titled Chapter dark energy. We compare Titled dark energy model for some particles C and gamma to standard terms in cosmology. Using observational data such as the magnitude redshift relation for type 1a supernova, using Fornax Clus dataset, variable calculation with this dataset, and the Hubble parameter redshift relation. We calculate the calculation of E square for various dataset in the case of fixed C and gamma allows to estimate the magnitude. The relation between supernova's distance models and redshift are often used to constrain the parameters of the energy model. The theoretical value of distance modulus for some supernovas can be calculated as the following form, where Z, C, D, and G L are the positive microwave background array squared and our heliocentrical relative optical knowledge. The luminosity distance dl is given by there where r is the corresponding common distance. Here a is the dimensionless Hubble parameter. We will restrict of yourself to the case of the flat space time. Then I make a equal 0. And so the general best-fit model parameter corresponds to maximum of the total log likelihood function. Here, some correct matrix which given by dataset. Baryon acoustic oscillation gives the values of acoustic parameter A as function of redshift. And the corresponding vertical value of this parameter is following form, where dV is the distance parameter defined as, and here C is the sound speed with the over the dimension. And finally, for Hubble parameter test, the most recent data set of Hubble parameter as a function of redshift consists of 36 measurements. Hubble parameter can be determined due to difference between age and redshift of couples of spatially revolving galaxies. Assuming we assign distributed errors sigma, we can find the best fit parameter by maximizing the log likelihood function. And the results, the table shows the results of our research. Here you can see the results for best fit parameters T0 and omega D. In the first line, we represented the LCDM model results, and the following lines show the results for standard photographic dark energy models with some C and gamma from various data sets of observations. The corresponding values of P squared, for which data set also are also given. These results can be compared with standard LCDM model. And we see that the standard photographic dark energy model with better can better perform than LCDM model. And the best parameters we highlight in both. For example, for supernova, with standard photographic dark energy with C equals 1.2, and non-negative parameter gamma equal 1.2, better than LCDM. On this slide, you can see two graphs with 1 sigma and 2 sigma errors of exceptional parameters and likelihood contrast for omega D and A0. The green area is Hubble parameter test, the red area is baryon translation test, and the blue area is Supernova's type 1A test. On the left figure, we present the result for LCDM model. On the right, result for standard photographic dark energy model with C equals 0.7 and gamma equals 1.2. Well-known Hubble tension problem illustrated here. Intervals of acceptable omega dark energy from H data and phantom plus overlap, but best fit H differs
significantly for an LCDM model. For self-correcting the energy model, the situation changed, although the problem remains. This slide shows similar graphs demonstrating results for self-correcting the energy with C equal 1 and gamma equal 1.2 on the left, and results for self-correcting differential model with C equals 1.2 and gamma equals 0.9 on the right. Also, the results of joint analysis of observational data are represented in this table. Consideration of all data allows us to conclude that value C equals 0.7 is perfect, while in the case of C equal 1 or C equal 1.2, the likelihood of self-correcting energy models is significantly less. Also, there is no substantial dependence from parameter gamma. The correcting energy model with better performance in comparison to LCDM model is highlighted in both. Here you can see 1 sigma and 2 sigma errors of acceptable parameters American energy and H0, and likelihood models from combined analysis for LCDM model. The optimal values of parameters with 1 sigma and 2 sigma errors are highlighted in the box. This slide shows similar graphs demonstrating the results for silence correct data model with C equals 0.7 and gamma equals 0.9 on the left side with optimal values. And result for silence correct data model is the same C and gamma equal 1. In conclusion of our analysis, we consider interaction between matter and dark component with the following interaction. The following interaction is proposed, Q, where alpha and beta are dimensional constant. We investigated some variants shown on the table. Without the interaction, the result for value C equal 0.7 turned out better, but the interaction saves the case C equals 1. For some alpha and beta, always gives observational data is quite effective. The progressive direct energy model, progressive model with better performance is quite difficult. On the right side, you can see the likelihood orders according to the parameters which provided with the vector. And our conclusions, our considerations were based on data concerning different redshift diagram for 1A type 1A supernova, depending on other parameters from redshift and baromacoustic oscillation data. The population of each square provided as I said in the case of XT and gamma allows to estimate the likelihood of self-productive antibodies in comparison to each other and the other pathology. Analysis of Fornax Clus dataset demonstrates that self-productive energy satisfactorily describes the data in a wide range of C and gamma. For C more or equal than 1, the performance is while Y is supernova that are relatively better than for the LCDM model. On the other hand, they see 2024 data and Hubble parameter data favorable C less than 1. The best p value for H0
zero strongly depends on C, while omega dark energy change this also depends on the parameter of non-additive gamma. Also, the analysis of combined data set allows us to define the optimal value of parameter C and rule out the case of C more or equals than 1. For which the concordance with observational data gets significant in comparison to LCDM model. However, inclusion of the direction between matter and quadratic range in simple form expands the allowable interval of C. For interaction in following form, here the case C equals 1 for some alpha and beta is valid from an observational viewpoint. We note also that best peak value for Hubble parameter is larger for silent quadratic dark energy in comparison with the LCDM model. Therefore, Hubble tension problem looks not so dramatic in quadratic paradigm, although puzzle remains unsolved. It's all. Thank you for the attention.
Oh, thank you, Aleksandr.
Greetings from California. My name is Yash-Hemu Aggarwal. The paper I'm going to present today is an original piece of research that has neither been published nor presented at any conference. It's presently under review. It, in my opinion, solves the long-standing dilemma or enigma of the origins and growth of supermassive black holes. I begin with what is known. We know that, or it's currently accepted, that supermassive black holes grew from seeds formed in the very early universe. But the questions that remain unanswered are: how large were the seeds? What were their formation mechanisms? And how did they grow by several orders of magnitude in less than 1 billion years? So, I submit that I found an empirical relationship based on supported by theoretical considerations that solves the problem. I'll begin with this theoretical basis. The commonly used salpeter relationship, that is that where a black hole's mass MBH is a function of its seed mass ms, its age t, the inception time of the CTS, and a parameter gamma. It's a non-dimensional parameter that's a function of duty cycle delta, Eddington ratio lambda, and radiate efficiency epsilon. Recent work, including my own and others, have shown that all these three factors that define gamma decrease as redshift decreases. Hence, gamma must be an inverse function of age t, and we can define it as gamma is equal to beta multiplied about 45 over t to retain its non-dimensional character. And the challenge is now to find the value of beta and ts, the origin time of the seeds. I found the values of these two parameters using data for 91 supermassive black holes less than 1 billion years old. The next slide shows you the distribution, the mass versus age distribution of these 91 black holes. Note, those black holes denoted by blue rectangles have masses, very similar masses within a factor of 2. Those denoted by red circles or red triangles have masses either lower or higher than this group of 60 black holes. The conclusion I draw is, and it is explained in the print version of the paper, as these 60 black holes had very similar sized seeds. Hence we can write 60 equations with one variable, age t, that's the age of the black hole, and 3 free parameters. And what are those 3 parameters? Beta, the proportionality constant, ts, the origin time of the seeds, and ms, which is the seed mass common to all these 60 black holes. Now we solved the 60 equations. I solved the 60 equations and subsets of it, and came to the conclusion that the best values for beta is 14.6, and for the origin time is roughly 100 million years, or z is equal to roughly 30. And substituting these values in the previous equation 3, we get equation 4 that expresses the mass of a black hole as a function of its seed mass ms and age t. So hence, knowing a black hole's mass and its age that we know from observational data, we can ascertain or determine the seed mass or the mass of the seed for any black hole. So, first thing I did was to apply this relationship to the 91 black holes, the high redshift black holes. This figure shows the distribution of the seed sizes or seed masses as if against the black hole mass, and you could see that it's almost a linear relation. Not exactly, but almost. It's a log-log plot. The symbols are the same as in the previous figures. What is important here is to note the 2 red dots at the bottom left-hand corner that fell outside the bounds in the previous figures. These are for GNZ11 and Sears 19, 2 AGN that were recently discovered. What we can conclude from this figure and the previous is that the entire suite of black holes, the high redshift black holes, their masses can be accounted for with seeds ranging in mass from 20 solar masses to roughly 30,000 solar masses. Okay? And we can reach the conclusion that these 2 black holes at the highest redshift, including another one, UHZ1, at a redshift of 10.1, they do not require heavy seeds. Their masses can be explained by light seeds less than roughly about 400 solar masses. The next what I did was to test the universal applicability of this equation. I applied to a suite of 132,446 AGN or supermassive black holes listed by Kozlowski at redshifts of 2.4. Most of them are greater than 10 million solar masses. The figure shows the distribution. It's a histogram showing the number of seeds as a function of the seed mass. Each bin has a width of 50 solar masses. There are several things to note here. First, you note that initially there is an increase in the number of seeds before it starts declining. It declines monotonically. These seeds represent 90% of the population of the 132,446 black holes. 90%. The rest of the 10% are not plotted. They are given in table number 1 because their numbers are so small that it will not be visible in the figure. What I did was to look at this distribution in figure 4 and in table 1 and compare it to the results of simulations performed by a number of authors. Hairon et al. Is one of them. On the basis of these, I'm not going to go into the details because time is not enough. You can look at the paper and find out who the authors are. What I concluded was that 58% of the seeds can be classified as light, that they are less than 400 solar masses. Roughly 39% can be classified as intermediate size, ranging in mass from 400 solar masses to roughly about 3,000 solar masses. And the rest, roughly 3%, I call them heavier seeds in contrast to heavy seeds. And they range from 3,000 to 30,000. And mind you, those larger than 10,000 represents a minuscule number of seeds in this population of more than 100,000 black holes. So what are the conclusions we can draw? That majority of the seeds predominantly were light to intermediate size. There is a very small number of heavier, and then a minuscule number of heavier seeds. Heavy seeds, not heavier, but heavy seeds. That is more than 10,000 solar masses. In fact, Kozlowski lists 540 black holes larger than 10 billion solar masses, but their seeds do not exceed the previously determined maximum of 30,000 solar mass, except 5 whose masses are not well determined. Another conclusion that we can derive is that the DCBH mechanism, or the direct collapse black hole mechanism, is not required. The entire population of seeds can be explained by light to intermediate sized seeds and heavier seeds formed, the light seeds formed by collapse of the first massive stars, the intermediate sized seeds formed by hierarchical growth or merger of black holes of population 3 remnants. So that's the exciting conclusion of the results of the study. So having concluded as to what were the sizes of the seeds, what might be the likely mechanism, now we can look at how did these black holes become so massive in such short times. Now, differentiating the earlier equation number 4, respect to time, or we get equation number 5, where the instantaneous accretion rate m dot is expressed as a function of the black hole's mass, mbh, and its age t, or redshift z. Note that in standard cosmology, 1 plus z raised to the power 3 scales as the ambient gas density, or the gas density of ordinary matter, or matter in fact. That's what it is. So we can conclude that the accretion rate is a function of the black hole's mass, meaning gravitational reach, and the ambient gas density, and nothing else. Does not depend on anything else. Now this figure 5, shows the accretion rate as a function of redshift for a seed of 1 solar mass. And it can be linearly scaled up to any size that you want. You can determine the seed size for any black hole using the previous equations, plug it in, and you can determine its accretion rate at any time in the history of the black hole. What does it show? It shows that initially the accretion rate increases exponentially. This is a log scale. It reaches a plateau or a maximum between 8.5 and 6, and thereafter it decreases steadily until z is equal to 0. It is important to note that this plateau, the maximum, during which the accretion rate is the maximum, hence the luminosity of the black holes is maximum, corresponds to the period that we now know corresponds to the period when reionization of the universe took place. So data from here can be used in order to investigate the contribution of black holes to the reionization. It is beyond my expertise to do so, and it's not within the scope of this paper, however. On the basis of figure 5, we can further conclude that initially the gravitational reach of the black hole increases faster than the decrease in ambient gas density. As a result, the accretion rate increases, but it reaches a plateau where the two factors reach a parity, and thereafter the decrease in density overtakes the gradual increase in the black hole mass or its gravitational reach. There are two additional conclusions that are discussed in detail in the printed version of the paper. One, on radiate efficiency of black holes. It is found to be a function of redshift and black hole mass, and the current practice of using a standard value of 0.1 is not acceptable. Radiative efficiency can vary by a factor of 10. This paper shows that it increases as a black hole ages, meaning that a black hole becomes less sufficient in accreting gases as it ages. Secondly, sub-Eddington accretion is the norm through much of the life of a black hole. But during the first 150 million years or so, a black hole may have experienced super Eddington accretion, or one or the other, or the radiant efficiency during that interval of time was less than the standard value of 0.1. This finding that the radiant efficiency could be very small in the very beginning of the lifespan of a black hole is consistent with the findings or suggestions by Wythe and Loeb and Pacucci et al., who suggested that when a black hole is immersed in high density, very high density, the radiation pressure is minimized. And at very high redshifts, you expect the ambient gas density to be very high. So thank you for listening. This is basically the end of the talk. If you have any questions, I'll be happy to answer them. Or you can send them by email to me at haggarwal@hotmail.com. Thank you.
This presentation is on a paper which was published about a month ago, and I believe in new timeline. So it's a big topic. There's about 16 published papers on it. And let me introduce new timeline briefly. And what I'm really interested in is this theory predicted in 2016 a relationship between dispersion measure and redshift before we had the FRBs. And now we've got 23 localized FRBs. We can test it and visit it, and it gets it right. Let's have a look through. Okay, with the history. New timeline. First of all, like in 1996, it was 30 years ago. Started off on internet forums with astronomy and so on. Lots of discussions going on, and that enabled us to formulate the actual theory at the start. Since then, as I say, it's been presented at several conferences, several peer-reviewed journals, and conference others. Like distant galaxies being absorbed before emitted by the electrons in the intergalactic medium. And these recoil on absorption and emission. Some of the energy of the photons transferred to kinetic energy as a recoil of electrons. And so the new photon emitted but less energy, lower frequency, long wavelength, it's being redshifted. Now, the Hubble law becomes photons of light from a galaxy twice as far away, make twice as many photon-electron interactions, lose twice as much energy, get twice the drop in frequency, and twice the increase in wavelength. It's as simple as that. Now, NCR provides numerical predictions which can be tested. And so this one in 2013, Cornwall Galaxy. We know the distance to the Cornwall Galaxy, Greenwich redshift, and I use that NTL here to predict it, take the distance, predict the redshift, and it gets it within about 6% of that that's measured. The problem here was that we didn't know exactly how many electrons there are per cubic meter, the electron number density. It was published figures were between 0.1 and 1, and what I took here was I took it at 0.5. And 0.5 got me as within 6% of my prediction. Okay? Now, full algebraic proof, the book, which I put at the beginning, has as an appendix for all algebra to get you here. It gives us that the redshift Z is the exponential of h(e) over speed of light, e the distance, h Hubble constant, -1. And h in terms of electrons is 2 times the electron number density, Planck constant, classical radius of the electron divided by the mass. If you use any 0.5, you get h of 63 kilometers per meter parsec. Okay, but the problem is that n. Now what I've got here is, we'll start again. Again, we can do it again from first principles, taking a photon and tracking its journey to the universe, and again it will get to the redshift. But the problem remains about this electron number density, just exactly what it is. And then we have excitement upon excitement. We've got dispersion measured from past radio bursts. Okay? And so you realise then I didn't need the electron number density, because dispersion measure, and we'll look at it in a minute, is caused by interaction with the radio waves with the electrons in the intergalactic medium. Redshift by tide light is due to the photons interact with these same electrons, and so we get a relationship between them that didn't need the electron number density, because it increased D and Z. It reduced them both. But the problem here was that we don't have any FRBs localized. There's no centric variable in that galaxy. So you don't know the distance there. You could get the electron number density, but finding the distance, what we were doing here is getting the distance from the actual redshift that put us around this circle a little bit. So let's look at dispersion measure. The signals are delayed, just as we get dispersion in glass, when the white light travels through glass, red travels the fastest, violet the slowest. As the radio signals travel through the IGN, then the different frequencies take travel at different speeds. So when you get a signal pulse of a fast radio burst, they're all happening at the same time, but when you arrive here on Earth, they come in a procession, one frequency after the next. And by looking at the graph, the frequency against time offset, and you can see that the lower frequencies are taking longer to arrive than the shorter ones. And if we there, you see dispersion measure of quantity radio astronomy that makes the column density of free electrons between the observer and the pulsar of fast radio burst. Nuclide light is the interaction of photons with the same electron, which should be a relationship. When it's nearby, then we use the top expression. Dispersion measures the integral d of electron number density with distance. Now, this is what confused me a little bit before, but when we get to this fast radio bursts, which are a long way away, we're working on weighting the dispersion measures for expansion. So the intrinsic factor is weighting factor of 1 plus Z. So if we're going to use the data from dispersion measure, we've got to remove that weighting. We have to process them. So let's then have a look here. In a static universe, electron number density will be the same everywhere. So the dispersion measure really comes down to this, electron number density times the distance, which is quite nice. Okay? And for NTL, I can rearrange my formula there to the expression to D C over H log n log plus Z. Or it's inserting my values for the constants for H, D, n massive electron times speed of light divided by 2 times the number density by constant times the radius times log n1 plus z. And if I rearrange my dispersion measure to final d's, put the two equations together, then that will give me the top line there. You can see both have got electron number density as the denominator, so it cancels. And so I'm left with my direct relationship between dispersion measure and redshift by new tide light. But if I plot those, I get a straight line graph through the origin, simply, and the gradient will be mass of electron times speed of light vacuum divided by 2 times Planck constant times classical rate of the electron. There are no adjustable parameters for dark matter, dark whatever it is. It will be mc over dh through hre, no matter what. That's the interesting thing. Now I'm going to go to SI units, and the value of that constant is 7.318 times 10 to the 25 meters to minus 2. Okay? And that's what we're looking for. Now let's start applying the data and test it. Does it work? That is, does it work? Now when we've got the measured dispersion measure by our telescope, there are 4 components. There's a dispersion measure in the Milky Way, a dispersion measure in the VM halo, there's a dispersion measure due to ITM, and then there'll be a contribution from the host galaxy. Now we get the first two, Milky Way and halo. There's 2 electron number density bubbles known as NE 2001 and YNW16. Okay, now the problem is, and this is where some of the uncertainty comes in, you need different values, especially when you get around the halo. And so some workers take the average between the two. But we're going to get some uncertainty coming in because of that. The host, if you believe in the expanding universe, causes a problem. It's basically you don't know whereabouts within the host galaxy that FRB is. And so it's going to break, but also when we start doing weights, they have to take into account the redshift, but that is back to 1%. Okay, so it makes it very complicated. Some workers just leave it in there. So assume we've got a value 50 to 100, and then weight it for redshifted. Right, so we have to contribute those to get back to what we want, which is the dispersion measure due to the IGA, intergalactic medium. So there we go, that. We'll take the measured dispersion measure, subtract Milky Way contribution, halo contribution, and that then will equal my GMICM. But then I've got to, well, I'm trying to put that weighting back in. So whatever in my corrected dispersion measure, that's where I've taken the weighting out. Well, if MC over 2HR, log n 1% plus the mean host galaxy. And because we're not weighting the redshift, overall, that's going to give me my intercept. So the intercept to my graph will no longer be 0, will be the mean host galaxy contribution. But the gradient will still be MC over 2HR. Okay? And we can't say enough, but this isn't any gradient. These are constants that depend on the electron and the photon energy. Electron, N and R, photon energy. Well, we've got that in there, we've got C anyway in there from the photon. So it's not any old relationship. This is predicted by a relationship where redshifts are formed by photons interacting with electrons. So at the bottom, we've got our full volume here. So what we've got on there is what we're looking for. But remember, I've had to take out the weighting for expansion. Well, this is our list of data that we've got there, all the redshifts down there. There are 23, and at the moment at the time of doing this. One of them are removed because it actually came through the outer layer of the galaxy on the way. Now, some people make an estimate of what that contribution will be. It's only an estimate, so I've sort of taken that one out. These are all straight things coming towards us. So correcting BCM, let's have an example of how we do it. Taking FRB 121102 from the top of the lid. Host galaxy redshift 0.19273. For the weighted BN 557 centimeters cubed. Remove from that the galaxy in the halo, which is 188,
giving me a big number 369. Both of these, and that includes the host galaxy. They've both been corrected by expansion, so that removed that. So they've been corrected by dividing by 1%. So now we've got to multiply by 1%, you know, to put that weighting back in to get the true value that you'd get in a static universe. No, that'd be 440 part x-2. Okay? Now, what we've then got to do is convert it to SI units. Otherwise, we can't compare it with the SI-MC over 2HR rating. Now, why is the cosmologist use these weird units? I don't know. But R.P. Kirshner in the book of Travel with Universe says, particular form of units keeps the physicists at a respectful distance to avoid contamination. We're going to use SI units. We're going to convert it to SI. And there's our results for all our things. The dotted line is from the data, the trend line from the actual data, and the orange and red line is that was predicted by nuclear light. And you can see they are within 9% of each other. And I think a pretty good fit from there. Okay? And that's what works on nicely from here. And we've got on there, if the 9%, and so again, that gradient is ME or MC over 2HRE. This combination of universal constants. No dark matter, no dark energy, no adjustable parameters. It is MC over 2HR. Now, even if anyone does not believe in nuclide light and says this is just by coincidence, then why is it MC over 2HR? It's too much of it. For me, anyway, it's too much to do by chance. It shows that they are related. Redshift by electrons and photon, DM by electrons again. Okay, now as the paper is being published, another FRB was found in the whole galaxy, 1.016, and it's redshift. Let's sort of put this in, and it's the other 23 were listed as well. Determining host galaxies. This is just one that came in. But if I include that, you can see the top of 0.7, little bit up, but now instead of being 9% below, it's 11% above. It's all varying around about that entity over 2HR as you put them in. And so the interesting thing will be is as more and more FRBs are localized, I want to keep completing this look. And let's see how it gets on from there. Now let's then have a look at what an expanding universe does. What an expanding universe does, you get the time here, not too bad yet. There's a formula and quark relationship, that formula on the top left-hand side. I'm not going to tell you what all the terms are, just to point out that there are two adjustable parameters in there for how much dark matter there is, how much dark energy there is. And because it may or may not exist from there. Now, what that boils down to is for up to about redshift of about, a redshift between 0 and 1, then that roughly comes down to about 850 days. So the reference of this graph should be 850. When you do that, it comes out to be 1,100, so a difference of 29%. That's way, way off compared with neutron bodies. Okay? So, in conclusion, now I have got some more later, we can go for questions if you like. NTL explains redshifts in the static universe, interacts with photons with light and electrons IgN. Present methods called by radioactive interact with the same electrons. I did this in 2016 and said exactly what that relationship would be, and that the gradient would be MC over 2HR. And when we've now got 23 IFRBs identified, we both the dispersion measure on redshift and test it, because at least 7.39, we're just, we say those 9% out. So this is what we've got. Now, would you like me to ask some questions, or you want me to talk about the IGN and why it doesn't flare?
Yeah, thanks. I'll ask now if anybody has questions, striking questions about tire life.
Anyone? No? Right, well, Alex in the room, if I may.
No, there's a question.
So, hello, I'm Pavel Kroupa, and that's very interesting, but if you have a static universe, how would you explain the evolution of galaxies, right? So that's a problem in this scenario.
The problem of evolution of galaxies, I think, is the problem is not with the problem is with the new telescope, James Webb Telescope, which is finding galaxies where galaxies should not be. And what they're now saying is that we have to look at the whole physics of galaxy formation, because the James Webb results are showing that it doesn't agree with present physics on this. And when we look at those, then we're going to have to look at how to get the evolution of galaxies, because it's not agreeing with the James Webb Telescope.
Any other questions? Anyone? Okay, so thank you, everyone. Right. So let's move again to expanding the universe after the talk of President Paul with also Lyndon about static universe. So I'm trying. This is the work done by my master's student, but unfortunately she doesn't write her name in the slides. So I am talking on behalf of her. So we are trying to solve the treatment equation for normal slash universe with both minimal and maximum length. So why? This is the main topic of the talk. Why how generalized uncertainty principle, and how do we use the generalized uncertainty principle to modify treatment equations, and how we try to solve them. So why we generalized uncertainty principle? Because we have some great easy fundamental theories like theories or all the quantum field theory singularities. So because we have a lot of theories, extension of quantum theories leads to modification of the Heisenberg uncertainty principle. So like from non-commutative. We have also transparent problem, and also string theory conjecture that the string cannot interact at distance less smaller than its size. So this is why we have a minimum length, and why we have defined uncertainty principle in quantum theory. We need it. So there is many. How we say it, many ways to put generalized uncertainty principle at the minimum length. The first one was done by Kent and Gamma in 1995, and this is the first one. There's also another version of Adidas and Vyacheslav I, and Petra, first I love the Petra way because it gives maximal value for energy also with a minimum value of the distance, and that is the generalization of the Petra way, which is a Perevola-Rockus, which gives minimum length, maximum length, and minimum value of energy, and also maximum value of energy. So why we need maximum length here? Because I want to put it in cosmology, because the essential motivation comes from cosmology, because we have maximum measurable length of the universe. So let's use them to modify the Feynman equation. So how do we connect this quantum with Feynman equations, which are some way classical according to quantum physics? So we need correspondence, and here we have the correspondence between Poisson brackets and the Dirac brackets. So we go back from Dirac brackets of quantum physics to the Poisson bracket and modify here the Feynman equations. So how all of you knows how we get Friedmann equation. We use how we get the Friedmann equation. We have the first one, second, and third, and how we combine the first and third equation. We get the first Friedmann equation, and we use the second one to get second Friedmann equation. This is the orthodox way to get together. Let's use this way to get the modified Friedmann equations. So we modify the Poisson brackets, we add them to the two equations seen before, and we use the same procedure to get the first Friedmann equation and the second Friedmann equation. What we get here, what we write is the analytical form and the approximate form when the law is perturbative. It is perturbative to the second order of the deformation parameters. The alpha is coming from the maximum length of the maximum length gap, and the beta is from the minimum length gap. So this is the first equation, second equation, and also the modified distribution parameters. So here we see that the gap contributes to the acceleration of the expansion of the universe because of the minus sign in this equation, the minus sign here. How can we? It's just a remark here because when we write the two equations to the first order, we see that the first contribution, the first one here, to the first Friedmann equation, to the second Friedmann equation are the same, are here, as you can see. So they can be compared to the lambda parameter, which is the cosmological constant. But here, what we need a non-flat universe because we need a tape. We need a non-vanishing tape. So in flat universe, we cannot interpret the generalized conservative principle cannot be seen as equivalent to the cosmological constant. Now, how do we solve the Friedmann equation? We will use a procedure which is perturbative, but it is a classical perturbative that is comes from quantum perturbative methods. So here, what we look for is the early universe, where the radiation dominates. So we have the analytical solution, and if we add non-flat, non-zero geometric constant, and we also add matter and vacuum. But in the early universe, we know that the proportion of matter over radiation are less than 1, and also vacuum over radiation is less than 1. So here also we can use perturbative method. All these computations are used to validate the perturbative method in order to have used. What is the perturbative method? It is you know the solution for certain simplified equation. So we write when we have complicated equation, it comes from quantum method. We write the solution, the new solution as the known solution plus a parameter plus a new term. When we put it in the original equation, we get the new equation with the new term, with only the new term. We can solve this new equation with this new term, or analytically or numerically. Here we use it for this combined early universe dominated by radiation with some proportion of matter and vacuum, and we get the solution. This is to validate our method, and it supports for the expansion parameter and also for the Hubble constant for all these parameters. But this is without a gap. This is without using the gap, the generalizer asymptotic principle. Now, if we put the gap, this is what we get. We get, this is the modified, we have modified equation, and this is the solution. The solution, but without the matter and vacuum. So here also, we have the analytical solution and the particular one with the contribution from the maximum length parameter and the minimum length parameter also. And here we plot the straight parameter according to time, but here we have to mention that time, it's, how do we say, it's time over, I don't know how to say it in English, because it's t over t still, where t0 is the actual age, the age of the universe. So it's, I don't know how to say it in English. So it's t over t0, this t. So A also is A over E0, A0, but A0 is actually 1 in this stage. So this is we plot here, and we can see that the maximum length parameter have small contribution, but the minimum length parameter has large contribution to the scale parameter. But if we get to the Hubble constant in the real universe, here we are speaking about the real universe, we can see that the minimum length parameter doesn't affect the Hubble parameter. The only contribution that we can see is coming from the alpha parameter, which is which characterizes the maximum length parameter, which is proportional to the distances of the observer universe. So this is we are still working on because we have when we take the minimum length parameter, the maximum length parameter, and also some combination of matter and vacuum, the equations are a little bit complicated. We get the solution, but we are still working on it. So it's not the work is not finished. But what we can say is that if we take a normal structure geometry, just non-structured universe, but with this very small scale, we can explain the lambda constant, of the lambda LCDM universe using the minimum length gap. Also, if we take flat universe or normal flat universe, the maximum length parameter can explain that the patience, the Hubble constant, is modified in the early universe according to the generalized asymptotic principle. So this is the main conclusion that we can make according to our present computation. So the gap diminishes the deceleration parameter. The gap minimum length is equivalent to cosmological constant, but here for non-flat universe, if you have k equals 0, this is not true. The gap minimum length is negligible for radiation dominated universe, but the maximum length dominates. The minimum length dominates in vacuum epoch, in our epoch. Now, the gap maximum length is relevant
in all eras, and especially in early universe, when relativity dominates. Because of the exponential solution are exponential. They are not polynomial, they are exponential. And we can have maximum mass affects effects on our concept can contribute to solve the Muslim problem. This is our main results until now, but okay, thanks. Thanks, Mustafa. All right.
Okay, Michal, would you like to say some ending words?
Yeah, sure.
Mustafa.
Thank you. And tomorrow we will meet at 9 o'clock in front of the main door. Yes, maybe the door will be open, so you can be at the yard because it's pleasant, more pleasant than at the street. So thank you once again for coming.